Welcome to the second day of the General Assembly. We are very happy to be in this amazing room with all of you. Thank you to be here. And yesterday we had several successful achievements, a lot of positive messages, and the events of the end of the day were a great success. I think that you all agree on this. So today will be also a day with successful achievements, and we will start the day with talks from the Copernicus Marine producers. They will present the achievements and plans for the blue, the green, and the white oceans regarding the models and the observations and the satellite and in-situ data. There will be 7 presentations from the production centers. These presentations are multi-author presentations. They synthesize the work all of the producers during this last year. So we will start. Can I have the agenda, please? Yes. The agenda? The slide before, so the one of, okay. So we will have 7 presentations. The first one will be the blue ocean observations. Regarding the satellite data, this will be presented by Isabelle Pujol. After, we will have the blue ocean in-situ data presented by Dominique Aubaton. After the question, we will have a time for question and answers. We will have also a presentation on the blue ocean model that will be presented by Emanuele Clementi. A presentation on the green ocean observations that will be presented by Vittorio Brando. And a presentation on the green model, green ocean model, the green ocean model that will be presented by Marie-Laure Grégoire. After will be a time for question and answers. And the 2 last one will be about the white ocean observations and the white ocean model presented by Cécilie Dewet and Laurent Bertineau. After there will be again a time for questions and answers, and then after there will be the break, the coffee break. So now we will start with the presentation on the blue ocean observation satellite that will be presented by Isabelle. So Isabelle, I let you the floor.
So hello everybody. I prepared my presentation with all the leader and deputy of the Blue Ocean Tags. So I will start with a quick overview of what are the Blue Ocean Tags for the Copernicus Marine Service. Then I will give you a status of the integration of the Sentinel mission in our production, and then a summary of the evolution that we implemented during the last 2 years, and an overview of what we plan for the next years. So the Blue Ocean Tags aims to process all the satellite observation and also in-situ observation in order to deliver ready-to-use and added value products for the MFCs and also for end users. Our products are multi-missions, and one of the main processing that you apply consists in the coarse calibration that allow us to homogenize the measurement from different sensors and merge them without problems. We deliver products in real time or near real time for many applications, but we also deliver long time series homogeneous that can be used for climate application or for different studies. And we deliver products for the global ocean and also for some regional areas with an improvement of the processing. The blue ocean, we are 5 tags in the blue ocean. 4 of the tags deliver surface product deduced from measurement from different satellites. There are the wind, wave, sea level, and SST tag. And the last tag is a multi-ops tag, and it merges the measurement, the product from the previous tags with in-situ measurement in order to deliver other added value product for the surface and also for the 3D ocean. And these products are used by the model forecasting centers for assimilation or for validation of their systems. So now a status of the integration of the Sentinel mission in our production. So the Sentinel-1B, Sentinel-3A, and Sentinel-3B satellite were integrated a few years ago yet. This was presented during a previous General Assembly, so I will not detail that. What is new here is the integration of the Sentinel-6A mission. These measurements are used in the production of the wave tag since November 2021 and for the sea level tag since April 2022. When the Sentinel measurements are not directly processed by the tags, they can be used for validation or calibration of the systems. This is the case for the wind tags that use a Sentinel-1 measurement for validation. The contribution of the Sentinel mission in our production is important. First, thanks to the high quality of the SAR measurement, especially for the sea level and the wave. Then because the Sentinel mission are used as a reference mission for our production. For instance, Sentinel-6A is a reference mission for the sea level, also for the wave combined with in-situ measurement, and Sentinel-3A is a reference for the SST. This means that these missions ensure the stability of the sea level, wave, and SST at climatic scale. And the contribution of the Sentinel missions is also very important for the gridded level 4 production. If we consider also JSON-3, we have 2 interleaved couples of missions that are optimized for mesoscale. And this is very interesting for the sea level. And altogether, these 4 missions contribute for nearly 65% of the level 4 production in the low latitude. The contribution of Sentinel-3 is also very important in the Arctic area, since in this high latitude we have a few missions that sample the sea surface. And Sentinel-3 also significantly improves the quality and the spatial coverage of the SST field. In addition to the Sentinel mission, we are also using other non-Copernicus missions. There are opportunity or collaborative missions, and they also significantly contribute to the quality of our production. They can be European, American, Chinese, or Indian, and maybe other countries in the future. And you have an overview of the number of satellites that we use in our production on the table. So it's very important to maintain the link between the tags and the space agencies that feed us with the upstream from this mission to continue to use them in our production. So now an overview of the evolution that we implemented during the last 2 years. So first kind of evolution consisted in upgrading the product existing on the catalog in order to improve the quality of the product. For instance, the sea surface salinity and density fields were improved by using the measurement from the SMAP satellite and also using a multivariate optimal interpolation methodology that allowed to merge the SSS and SST fields and so improve the space and time resolution of the product up to mesoscale. For the wind, the level 3 near real-time product were improved by using additional measurement from the Chinese A1, 2C, and 2D satellite that provide a measurement at all time of the day. And the wave product were improved by using a new calibration against in-situ measurement. This calibration was proposed by Dode and Piolet last year. And by doing that, the wave tag improves the consistency between their product and in-situ measurement and also between the near real-time and multi-year series. They also improved the fireworks of the wave by using the measurement from the CFOSAT satellite, especially the North Atlantic area where it's now covered by this satellite. And for the SST, the quality of the product was improved also using new sensors, VIRIS and METOPSY, for different regional and global production. And the SST tag also improves the estimation of the uncertainties associated to different products. We also added new products or new data set in the catalog. For example, for the sea level, a new along track product defined with nearly a 1 kilometer posting rate was added to the catalog last year for the European area. This is a level 3 5 Earth product. Compared to the conventional 1 Earth product, it allows to better observe the small mesoscale and also to better sample the coastal area. For the wind, a new level 4 neural time product was added to the catalog. It is deduced from the ECMWF wind field model, corrected from different persistent local bias. You have an example of this product on the map in the bottom, and also an example of the bias that are applied as correction. For the sea surface salinity products, 2 new products were added to the catalog. The first one is a level 3 product for the neural time and multi-Earth series. It is deduced from the SMOS satellite measurement, corrected from different effects. And a level 4 product was added for the multi-Earth series. It combines the SMOS measurement with in-situ measurement that allow also to correct residual large-scale bias. And the SST added 6 new products to the catalog. A level 3S product for the multi-Earth series for different regional area, a level 3S neural time product for the Atlantic area, and a diurnal level 4 product for the Baltic Sea. Now, what we plan for the next few years. So here again, we will try to continue to improve the quality of our product. And the first way to do that will be to use measurement from new sensors available. So all the TAC of the Blue Ocean will try to do that by using a measurement from mainly non-Copernicus mission in the future. And for the MOB-TAC, where they will also use new fields like the high frequency current signal or the stock drift current. Another way to improve our product will be to work on the processing and different methodologies that we can apply to produce. And here again, all the TAC, we try to do that. For example, the wind TAC is working on a new methodology that we allow to better retrieve the winds closer to the coast. The sea level and the wave are working to improve the processing that is based on the upstream 20Hz product and that allow to produce the level 3 5Hz product. So we continue to improve this processing, and they also work on different mappings technique to improve the level 4 products. For instance, they test a mapping technique, a multi-scale mapping technique proposed by Obelman and Tal a few years ago. The SST and MOB-TAC also are working on new mapping techniques. Here mainly based on artificial intelligence techniques with the super resolution algorithm for the SST or the machine learning approach for the MOB-TAC. And the MOB-TAC will also use outcome from the work ESA R&D project. So by doing that, some tags will be able to increase the resolution of the different products that they propose in the catalog. For instance, sea level and wave will propose a level 3 5X product for the global ocean. The SST will also improve the resolution of the level 4 product for the neural time in some areas. You have an example on the two maps of the impact of the super resolution algorithm. That better resolve fine scale structures. And the MOB-TAC will propose the CFOSAT salinity and density fields with a higher resolution than the current version. And they will also increase the temporal resolution of the surface current and the different 3D fields. During the next year, we will also continue to develop the catalog with new products, dataset or variables. The SST already started this a few months ago with a release of Level 4 Odyssea product, and they will continue in the coming months with a release of Level 3X multi-year global product. The wave and the sea level, as I said before, we start to deliver the Level 3 5X product for the global ocean. They will also declare new dataset to deliver the Level 3 product for the new sensors that will be used in the processing. And the MOBTAC will propose new variables for the Ekman currents or also uncertainties for different variables that are already available. And the last main evolution will consist in deliver full reprocessed multi-year series. So this will done by the wind, sea level, and SST TAC, for different multi-year products. So I will conclude with a few numbers. So for the blue ocean, we are 5 TACs. We are using currently nearly 35 satellites for our NRT production, a little bit more for the multi-year production. And we are maintaining 15.8 products on the current catalog, plus 27 OMIs. And these products are used by the MFC and many external users. During the last year, we upgraded our product in order to improve their quality. So 35 products were upgraded. And we also added 10 new products or datasets in the catalog. And we will continue the evolution in the next year, as I just presented you. I just finished with a few words about the Brexit issue. That is impacting the SST TAC. Indeed, part of the Level 4 production was previously ensured by the Met Office, and it is transferred to the other production unit of the SST TAC, and this work will be completed by the end of 2024. So that's all for me. Thank you.
Many thanks, Isabelle, for this presentation, very clear on the achievements and plans for the observations. Just a few words. We have some issues with the sound online. So we are trying to resolve this. So sorry for this. And now it's okay. Okay, so I will let the floor to Dominique. She will present the blue ocean observations in situ.
So good morning, everyone. So I am Dominique Baton. I work at Ifremer, and I'm also the leader of the in-situ TAC. So I've done this presentation with different people, many people, and also other initiatives and other partners from other data integrators, let's say. So I start with my presentation. So why in-situ observation? And the answer is to know and understand the ocean first, to validate the satellite and model data and product, that the in-situ data can be used or are used as initial and boundary condition to the numerical models, and also are used for assimilation in the numerical models. So each year, more observation, more in-situ data are integrated within the in-situ product, and additional and sustainable in-situ observation is and will be needed over time to understand better the ocean and to follow its evolution. Okay, so now I go to the organization of the in-situ TAC and the product that we have in the Copernicus Marine Catalog. So within the in-situ TAC, we are a consortium of 15 partners from 8 European countries. And within this consortium, we have regional leaders and thematic experts. We work in close collaboration with various network and initiative. So at international level, this is done through the Global Ocean Observation System, EuroGOOS, and at European level, this is done through EuroGOOS and the regional rules. And of course, we also work in collaboration with the different in-situ data integrators. So at the European level, it's CDataNet, Emodnet, and mainly Emodnet physics, chemistry, and gestion. And we also work with Rheticus, who is dealing with coastal data. So before focusing on blue ocean in the sense physical variables, I'm going to present a little bit the in-situ TAC. So in-situ TAC, it's a multi-platform approach. So this means that we have data at measurement points, so it is discrete data, so it's a bit not at all as the modeling product, and it's a thing. It makes the thing complicated to manage the data, to gather the data, and so on. And we have different kind of measurements, so we can have vertical profiles and trajectories, and all variables are taken into account from the sensors. So we don't have on one side the blue ocean, on the other side the green ocean. We recover and we register all the variables from the sensors. So for the blue ocean, in the sense of the Copernicus, with its physical variables, and it is mainly the essential ocean variables, so the temperature, salinity, current, wave, and sea level. For the green ocean, it's biogeochemical variable with chlorophyll, oxygen, nutrients, which has nitrate, silicate, and phosphate, and carbonate system. So I'm not going to talk about this part. This part will be highlighted by during the next presentation by Vittorio. And we also, when we have them, have atmospheric variable, we have wind, and so we also register wind, record wind. So now if we focus on the blue ocean and the essential ocean variable, within the catalog, the Copernicus Marine Catalog, in terms of in-situ product, we have 7 regional multi-parameter products. So it's one for each region, so Arctic, Baltic, Norway Shelf, Iberia, Biscayne Island, Shelf, Mediterranean Sea, Black Sea, and the Global Ocean. So it's one for each with multi-parameters and from near time and back to sometimes to the past. And we also have 2 global, let's say, less 1 or 2 parameters product, which are the temperature and salinity product, and a current product. And then in terms of multi-year product, we have global product, and it's one by 1 or 2 parameters. So we have 5 global let's say 1 parameter product. So one for temperature, actually it's 2 for the temperature and salinity, 1 for the current, 1 for the wave, and 1 for the sea level. And among all these products, we only have 2 of them that are gridded. Okay. So now, this product that we have in the catalog, the in-situ product, it's a generic product, because sometimes when you say product, it means many things compared to data. We don't have all the same definition. But actually what we have is generic product. It's gathering in-situ observation independently on the platform. And most of them, okay. So from various sources. And so the data, as I said, are measurement points. And the multi-year products start from 1950 for some of them. There is a strong quality control for the in-situ product that is made within the in-situ TAC and across TAC and MFCs with the coordination of Mercator Océan in the Product Quality Working Group. And in addition to this generic product, we have ocean monitoring indicators that involve some of them only in-situ data, and some others that are made with in-situ data and some satellite data and modeling product as well. Okay, the main achievement during the past years. So I'm just going to give 2 examples. So the first one is the new multi-parameter sea level global product that we have released last November. This is the first time that we have this product within the catalog, and it is the best available version of in-situ coastal sea level observation at global scale. And it was done by means of the centralized delay mode validation and reprocessing of historical time series. And another point that I wanted to highlight is the important integration of drifting buoys that has been done in 2022. So we have integrated more than around 10,000 drifting buoys, so it's more than 50% more than the previous year. So it's mainly temperature and salinity variables, and it comes from a global reprocessing of drifting buoys and metadata, which were buoys which were deployed between 1997 and 2010. And this was done thanks to a project financed by the European Environmental Agency. The major evolution till end of next year. So we have something that is important and is connected to link to all our product, is that some technical data management. So we are going to change the format of all our product to adopt the last, or one of the last international last update of the metadata conversion version, so the version CF1.11. So that's some work at the end for the end of this year, and some and another work for other kind of product at the end of next year. And for the multi-year product, we are going to have the temperature and salinity product that will be validated until 5,000 meters. Now it's done up to 2,000 meters. The current product will be enhanced by advanced quality control for the drifters datasets and the HF radar dataset. Concerning the sea level product, we will have datasets which will include the astronomical tides and non-tidal sea level. And the wave product, for the wave product, we'll have a hourly homogenized wave data. Okay, so now if I go a little bit abroad by the in-situ TAC, so just to have a look at the physical in-situ observation at the European level. So as I said, and as you know, there are 3 main in-situ data indicators in Europe, and I've tried just in few bullets to highlight the specificities of these 3, main specificities of these 3, let's say. For CDataNet, it's a European platform for national providers, researchers, to put their cruise data, mainly their cruise data, homogenize it with metadata, and give access to it. So this is done through the national ocean data centers that go to this platform to manage their data and to make them accessible to the users. And it's done for all European countries. And CDataNet, it's also propose catalogs of metadata references. That's, for example, the SDN P01. And this is done with the BODC, the British Oceanographic Data Centers, and all is very well referenced within the BODC and with this CDataNet. So this CDataNet proposes tools to homogenize the data. And then when the data are homogenized, they are proposed in an open access to the users. Then we have Emodnet. So Emodnet portal, it's a European portal for marine in-situ observation. and with 7 thematics: physics, chemistry, biology, geology, seabed habitat, bathymetry, and human activity. And it's open access to users. And then we have the Copernicus Marine Service, which is something different, with a marine component of the 6 Copernicus services, as you know. And it's a European portal for marine in situ, but also satellite and numerical models, with a commitment to ensure an operational services. So there are some commitment, which is not the case for the other in-situ data integrator in Europe, in terms of availability and delay. And all the products are provided through a unit access point in a homogenized way. And as the others, it's open access to all users, to users. So how do we work together? So we work together within Emodnet and CFOSAT through the with others through EuroGOOS, and there is what is called the Data Make Working Group, which is a working group on data management that allow to work together and to exchange ideas and also common sense, something like that. And for the moment, for example, we have proposed the EuroGOOS data policy, which is under validation and which is based on the international one from the IOC. And we also work with the data network and the EuroGOOS task team. So, for example, and these networks are, for example, Argo, gliders, tide gauge, buoy, fixed platform, HF radar, and vessels. And thanks to a project like the EuroOOS project, it's possible to get some budget and to work together from the data, for the measurement, not for us, but for the network, to the data management and to the data integration to Emodnet, CFOSAT, and Copernicus. And we have also another working group, which is called the Marine in Situ Collaboration Working Group. That was the first meeting was last year. It is issued from in-situ TAC and the management, the governance on in-situ TAC, and gathers from the stakeholder board of the in-situ TAC, and it gathers people from EuroGOOS, experts from EuroGOOS, Emodnet chemistry and physics, and in-situ TAC, and we have biannual meetings. And the idea is to avoid as much as possible confusion when we go to the provider, to go in one voice, and then to integrate the data in the different data integrators, and to better work together. So other EU initiative, so I just give 2 examples. So the Blue Cloud 2026 project, which is a European Horizon Europe project, and which objective is to provide access to a large span of data and to allow the partners to work on the virtual research environment space. And some of the so it has started the beginning of this year, and some expected output at access to a large span of data. So it's from physics to biology, and it includes genomics. And the development of use cases taking account on this large span of data and expertise and use cases. Using the virtual research environment that is proposed by the project. And there is also what we call workbenches, which are kind of pipeline to allow a better qualification of large or very large data set coming from various sources, to have at the same time, at the same place, the data set, the data, and to work on this VRE. And the other project I wanted to to say a few words, it's the COINS project, so it's a support to Copernicus in-situ data coordination. This is a delegation from the Copernicus, the European Union to the European Agency, to the European Environmental Agency, and to highlight the in-situ product from the different services. So it's a cross-domain approach of in-situ observation from marine, land, atmosphere, climate, security, and emergency. So it's another view, which is interesting, with the aim to provide awareness of cross-cutting requirements, to improve the access to in-situ data, and to answer some specific questions from member states. So to improve access to in-situ data, it also means to have some data that are highlighted or used in one service to be used in another service. So it's not, it goes to existing data. It's not to go to do some measurements. It's a panel or a mapping of existing data. Conclusion and perspective. So I will start with each year we integrate more and more data, so this is going to continue and this densify our product, let's say. There is a need of sustainable in-situ marine measurements, more data, and in the time, and to close the gaps within the ocean. So, this is true for known platform and platform type, but also for new platform and new data. And we also need, even we have done already a lot, we also need to enhance data management, to have more harmonization, to have a better interoperability, and this thing like that, for all the data and across data type and data network. So, and to conclude, we need also, of course, to continue the collaboration with other initiatives as Emodnet and CDataNet for the blue ocean, but also for the green ocean, of course, with the objective to clarify the offer in relation to each other and to ease the understanding of a user and to ease the access to a user to these in-situ data. We also are going to enhance the work with other initiatives as Jericho, and Danubius to have blue ocean data by the coast and on estuaries, and also taking advantage of, especially for Jericho, the scientific expertise that they have in the qualification and validation of the data by the coast. And this is a proposition to initiate also systematic cross-validation and qualification between in-situ and satellite data. So this is something that perhaps we can start within the Copernicus Marine Service. And something that is also very important, it's to ease access to in-situ, which is discrete data to all users, because it's a bit more complicated than for the model data. And it's something that is ongoing with Mercator Ocean. And this is the last slide where it's all of us. So it's during our last in-situ General Assembly in September. And it was the full consortium with Sylvie Pouliquin and Loïc Petit-Lavellon, the previous leader and deputy of the in-situ TAC. Thank you very much.
Thank you very much, Dominique, for this clear presentation on the in-situ data, on the achievements. And now, if you want, we have a session, a time for some questions. Is there any questions on the room? So if no, we continue our presentation. Yes, sorry, Laurence. I don't know if you have me.
Thank you. It's a question for you, Dominique. We know that there is a lot of data, in-situ data, which is collected by the industry. And I'm wondering what we could do to better centralize this data into the database we have in Copernicus?
I'm probably not the best person in the room to answer this question, but if there are data somewhere, and if they are, I mean, long enough in a period of time, or the efficient coverage, we are always interesting. So if we can write to me, or I will tell you who to write to, and we'll be happy to, if they're open, we'll be happy to go and get them. That's for sure.
Okay, thank you, because it's not always obvious, I think, for them to know how to do it, if they want to do it. So I think we need to improve this.
Yeah, just to add to the answer, we are also working with Emodnet ingestion, and Emodnet ingestion is a way for the person who have data to submit this data to Emodnet ingestion, and then through Emodnet ingestion, it will be integrated in thematic database, and then will be available through the main data integrators. So it's also a way for the people who have such data to provide them.
Thank you, Laurence, for this question. And thank you, Dominique and Stéphane, for the answers. Any other question in the room? Okay, so now I let the floor to Vittorio. It's not Vittorio? Right, sorry. Emanuela, sorry. I let the floor to Emanuela to present the Blue Ocean model.
So good morning, everyone. I'm Emanuela Clementi, and on behalf of experts from the physical and wave models for different MFCs, I'm going to present you the Blue Ocean modeling systems. So, brief introduction. Why do we need numerical model products for the Blue Ocean? We have just heard how important are the observations to monitor the ocean. In situ can provide sample and sample the water column, but they have sparse coverage. On the other side, satellite can cover a large part of the domain, but at the surface. And then comes the numerical models, which can provide a time evolution of the three-dimensional properties of the ocean at a defined resolution. And observations are fundamental because we are assimilating observations in order to correct the model solution and to provide analysis fields. And best initial conditions are then used to initialize our models and provide forecasts that in the Copernicus catalog are up to 10 days in advance. An added value here is the operational numerical modeling systems, which provide in operationally routine and fully supported production and delivery of the numerical data. The data are used on a variety of downstream applications serving the marine resources, maritime safety, coastal and marine environment, for example. And we are organized in 7 monitoring and forecasting centers covering the global ocean plus 6 regional seas, starting from the Arctic, the Northwest Shelf, the Baltic, the Black Sea, the EB, which is the Ireland, Biscay, Iberian area, and the Mediterranean Sea. All these monitoring and forecasting centers are providing 2 types of products. One product is covering the past period, called multi-year product, that is composed by reanalysis, covering which are homogeneous reconstruction of the past, up to month -1 with the interim extension, and the near real-time data, which instead provides analysis for the previous 2 years and the forecast for the following 10 days. The Blue Ocean variables consist of physical and wave variables. For the physical variable, we provide information at different time frequency, from monthly, daily, hourly, and in some cases less than 1 hour. And for the wave, we produce data at hourly instantaneous fields. I'm trying here to give you a brief overview of the characteristics of the near real-time systems, which have an horizontal resolution of 1/12 of a degree for the global ocean and high resolution for regional models ranging from 1.2 to 1.5 to 6 kilometers, and the vertical resolution from 1 to 500 meters with a high resolution at the surface. We are using NEMO community model as hydrodynamic model for almost all the systems, plus ICOM, and VAM, MFVAM, and WaveWatch3 for the wave models. All the monitoring forecasting centers are going to evolve towards the latest modeling code versions in 2024. For data simulation, most of the systems are implementing Kalmar filter and 3D VAR, assimilating temperature, salinity, sea level anomaly, sea surface temperature, and ice. And for wave, most of the systems are implementing optimal interpolation for significant wave height. In 2024, all the physical systems are going to assimilate both in situ and satellite data, and all physical and wave systems are going to improve and use additional observations, especially higher frequency or our higher resolution data. Atmospheric forcing fields are coming from ECNWF, high resolution, and in one case also from a high resolution limited area model. River forcing, the runoff especially, is from observations, models, or climatologies, depending on the area. But we are going towards a more homogeneous, let's say, forcing fields using EFAS data from the Copernicus Emergency Service and also EHYPE. Similar characteristics for the multi-ER systems, because we try to keep alignment between the near real-time and the reanalysis system. So similar resolution, slightly lower for the regional ones, similar model and data simulation. For the atmospheric fields, we are using here ERA 5 at 1/4 of a degree, and consistency with the near real-time also in terms of river forcing. Last year, we had a common effort for physics and waves to ingest Sentinel-6 data. Sorry, this was the following one. We are implementing physics and wave interfaces. So different MFCs have applied different strategies. We have forcing fields or coupling fields. In some cases, such as the one listed here, the wave model are forced by physical data, mostly surface currents, and in some cases, sea surface height and sea ice. In other cases, the two systems are exchanging fields. In the Norway Shelf, there is this coupling between the physics and wave exchanging online, the fields. In the Mediterranean Sea, the physical system is coupled with an external wave model and then provides information to the wave. But in 2024, there will be a common effort to achieve improvement in the near real-time system, especially for a wave current coupled systems. As anticipated, last year we had a common effort to assimilate the Sentinel-6 data, a sea level anomaly for physics and significant wave height for waves. This has led to a generalized positive impact, so we are now ingesting more data, and this has reduced the error in sea level anomaly, but more details will be given later in another presentation. Now I would like to show you several major upgrades that have been achieved and also that have been planned for the coming years. Starting from the physical system and the Baltic Sea, several improvements have been achieved and are going to be implemented in terms of additional observations to be ingested from sea surface temperature, from vertical profiles, and in the future also the sea ice. This has led to a reduction of the bias. In particular, here you see in the bottom level the improvement at the specific buoy station. In the EB area, again, an improvement of the data simulation here to assimilate sea level anomaly in shelf areas has provided a series of improvements in terms of reduction of root mean square difference for sea surface height, temperature, and salinity. starting from the orange, which is the previous system, to the red, which is the first attempt to assimilate sea level anomaly in shelf areas, and then the following improvement of the systems up to the final one, which is the latest system, which has provided a lower error. In the Norway Shelf, thanks to the deployment of 2 gliders in the North Sea, this data has been assimilated by the system. This is an important region because of the North Sea inflow, and because there, due to the low topography, there are only few Argo observations available. This has led to a sustained, widespread impact on the surface salinity and on the bottom temperature, with reduced bias. In the Mediterranean Sea, the ingestion of additional sea level anomaly data has led to a reduction of up to 10% in the sea level anomaly root mean square misfits. In the Black Sea, an operational system in the Marmara Sea and covering the 2 straits, the Dardanelles and the Bosphorus, has been implemented operationally thanks to this unstructured Turkish Strait system, which is now providing lateral boundary conditions in the Marmara Sea to run the Black Sea model. And in the coming months, by the end of this year, also data from the Marmara Sea will be provided through the catalog. The global ocean has achieved a big improvement, a big change in the modeling system and in the data assimilation scheme with an update of the modeling version and many other improvements by last year. These changes, all these changes, has led to an improvement of the representation of the water masses with weak biases. And here you see an example for the temperature from the previous system. You can see that there is a huge reduction of the error, especially in the surface layers. Then coming to the planned evolution for physics for the Arctic, this year it is planned a huge update of the modeling system, new model code, doubling the resolution, horizontal resolution from 12 to 6 kilometers, also including higher resolution in the vertical, and many others updates of the system. This is providing a better representation, as you can see here, of the small-scale dynamics for sea surface height, for example. On the left, the previous system, on the right, the following one, and also here an example of the sea surface temperature. Also in the Mediterranean Sea, a huge improvement of the system is planned for this year, so new modeling version for NEMO and Waywatch 3, but also an improved coupling between currents and waves. So additional fields will be exchanged, and more wave-current interaction processes will be implemented. Moving to waves, in the global ocean, the major system upgrades includes the assimilation of directional wave spectra from CFOSAT mission, and also assimilation of Sentinel 6. This can be seen here has led to a remarkable improvement of the scatter index, and also to a significant reduction of the bias in the Southern Ocean, especially for the high significant wave height. Similar evolution for the EB area. And here you can see an example of a comparison between the model and observation in a specific buoy at Cadiz. And you can clearly see the good agreement between the model in black and observation for significant wave height, but also for the peak period. Moving to the Baltic Sea, here the major upgrade has been the implementation of the exchange from NEMO to the VAM model of sea level and sea surface height. Of course, this has an impact, especially in the coastal areas, but considering that the Baltic Sea is a lower tidal region, this has generally a low impact, but it can be important and significant in specific events, such as the one represented here, where you can see that there is an increase of more than 1 meter in the sea, in the significant wave height in the coastal area. And here, for the Black Sea, I apologize, but the figure here is not well produced. You have to trust me. The major upgrade has been the improvement of the consistency between the near real-time and the multi-year system. That has also led to the implementation of the data simulation in the near real-time system. So now the near real-time and the reanalysis systems are sharing the same model grid resolution. They are implementing consistent data simulation and also the same model physics. And finally, for the Mediterranean Sea, again, an update of the modeling system with tuning of wave parameters, plus the estimation of the maximum wave height has been implemented, again, with the validation of this new variable, which shows here a very good agreement between the model and the observations. Additional improvements regard the data simulation with more assimilated data and improved with gaseousness parameterization, which led to a quite product quality increase, so some improvement of the scale for the significant wave height and for the wave period. So a few messages. Here, the Copernicus modeling system for the blue ocean are constantly ameliorated, following user needs in order to improve the accuracy of the product that we deliver. We are evolving following common objectives in order to keep and achieve always a stronger alignment between the systems. We put large efforts in the assimilation of new observations, Sentinel 6, but also directional wave observations in the case of the wave models. In addition to that, we are continuously moving towards improved interfaces and coupling between the hydrodynamics, so the circulation model, and the wave models, and also to improve the boundaries between the different and the neighboring monitoring forecasting centers. So this was my last slide. Thanks a lot, and thanks to all the experts who contributed to the presentation.
Many thanks, Emanuela, for this very clear synthesis on the blue ocean model. So now I let the floor to Vittorio to present the green ocean observations.
Thank you, and thanks everyone to be here. Thanks for the opportunity. Vincent, I know I gave you my slides late, but do I click just? Okay. Okay. So I will be presenting the green ocean observations on behalf of the three thematic assembly centers that do green ocean. So the in-situ TAC, the ocean color, and the multi-observation TAC. And so the first point to make is what are these green ocean thematic assembly centers? We do provide overall within the Copernicus Marine Service time series for the essential ocean variables related to biogeochemistry and the carbon cycle, starting from 1D in situ discrete data points, 2D satellite fields derived from ocean color, and then there is a three-dimensional integration mainly based on data fusion techniques at the end of this sequence. So the outline of my talk is I will provide you some details on the structure of the TACs and the evolution since the onset of the Copernicus Marine Service, with a focus of this current phase. And then I will highlight some of our achievement in the last year and a half, mainly focusing on upstream product and variables and enhancement in our processing, and then draw some conclusions. So the in-situ TAC has been already introduced earlier by Dominique. This is just a summary of what the in-situ TAC does, with a focus on the green variable. As we heard before, the in-situ TAC is a multi-platform approach, holds a multi-platform approach, and data are measured as points, and they are the discrete whether they're vertical profile, data from buoys and or trajectories. Of interest in terms of the biogeochemistry are the chlorophyll, oxygen, and the nutrients And all, as we heard in details before in Dominique's presentation, there is year after year an effort to improve the data sources, the kind of products that are available to provide a denser and more homogeneous data field across all the regions. And there is also an effort to engage more and more new data providers so that all the data can go and can be ingested within the service. So this is an overview of the evolution since the onset of the service. An important point is that there are near real-time multi-parameter products that include chlorophyll, oxygen, and nutrients. And in this phase, there's been an effort for a quality control upgrade for oxygen, nutrients, and chlorophyll, which is coming 1 year after the other. Then there is the multi-year global biogeochemical projects, and as you know, the multi-year is an effort where all the data can get as much as possible reprocessed and reanalyzed in a consistent way. So there is a further quality control and homogenization in the data set. And again, here the effort continues to be on the quality control in this phase. The important point is to look at the multi-year global carbon product, which will see the inclusion of the Emodnet chemistry data next year. Then we go to the Ocean Color Thematic Assembly Center, and the aim of the OSITAC is to provide all the ocean, or as many as possible of the essential ocean variables that can be retrieved from the ocean color. So in this moment, we do the chlorophyll concentration, we do the optical properties, we provide the data on phytoplankton functional groups and community structure, and we provide primary productivity. The important point to make here is that the aim is to add value from the products already available to the user community from the space agency, and so products are provided at a global scale and at regional scales across 4 resolutions. We have multi-sensor products that are at 4 kilometers from the global ocean and 1 kilometer for each of the European regions. Then we do have the Sentinel-3 OLCI A and B data sets at 300-meter resolution across all of the coast of Europe, and a buffer of 200 meters in the a buffer of 200 meters along all the coastal waters globally. And then we have what is still our new product, which was only introduced at the end in 2021, which is the Sentinel-2 data from Sentinel-2 A and B at 100-meter resolution, so that really takes us towards the coast and the interaction, like in the example you see here of all the river plumes and how the interaction, the land-ocean interaction. This is an overview as the OSITAC portfolio in the last few years, and the main point to take, there is a lot of information here, is that from the upstream, we've been moving more and more from scientific missions that were available in the past to the operational missions that are based on Copernicus, the Sentinel-3, and from the United States, from NOAA being the VIIRS platform. So it's been a shift from the scientific missions of the past years, and with the introduction of the Sentinel-2 based radiometry data, we also use what they are defined as land imagers. So again, here there is a change of upstream. What do we have in terms of the activities that we did in the last we did in the last couple of years? A major effort was, and I'm going to give you some details later. We underwent a catalog organization last year, which was a massive effort, and I need to thank you everyone at Mercator and within my consortium, because it was really a lot of work. And then Mainly the rest of the activities for these 2 years is the slow introduction of more accurate and more products in terms of the phytoplankton properties, being the phytoplankton functional type and the primary productivity that are coming along in 2023 and 2024 for as many regions as possible. Going to the multi-observation tags, this is where, as I mentioned before, we do take together the 1D and the 2D observations, the satellite and in situ, and with data fusion techniques, we get the 3D fields. And the products are presented here are the ones that are of the green ocean, so the carbon and biogeochemistry, and all of them are multi-year products, so they are all of them reanalyzed in a consistent fashion by using all the possible data stream. There is not a real-time need for this kind of product, and there is an effort to take advantage of the strength of the global ocean observing system and to be as close as possible to observation. So there is a manipulation to create this 3D field, but with an effort to preserve as much as possible the observation, and to provide a stable and long time series, and here is to provide a complementary approach to the data that is produced for these variables by the marine forecasting system, marine forecasting centers. The multi-obs TAC is still a new TAC in the fact that it was introduced only at the middle of the Copernicus 1 cycle, and along the three lines of products, the surface carbon, nutrient profiles, and the 3D particulate organic carbon and chlorophyll A, the main effort in the since last year has been the addition of new variables, as an example of the dissolved inorganic carbon and others for the surface carbon, the introduction of a third ocean molecular indicator being the PhD trend, and I'll show you a slide later on. And the effort is for the next couple of years to increase the resolution and to also add a new near real-time product which was missing for the nutrient profiles. So let's go and have a look at some of the main achievements for the last couple of years. For the last couple of years. As we, going back to the in-situ TAC portfolio with a focus on green ocean, so to be complementary to Dominique's presentation earlier, one of the main achievements has been the introduction of, for the oxygen, of a change of the vertical units so that they are easily understood by and used by everyone. And so there is the idea, the use of micromoles per liter and micromoles per kilogram, so that they are used because different communities like different things. It's easier to provide them from our side. And again, there are also the basic data set with the original units as provided by the data provider. So this effort that Dominique highlighted of trying to be homogenized, there is an effort within in-situ TAC along this line. There is also an improvement of the quality control procedure for oxygen across all the regional products. Important is in the moment there is an effort of getting data from several sources and from several integrators, there is an important effort to avoid duplicates in the data. So there is an effort to identify and reduce the duplicates data at regional level, and again here making sure that the river where high nutrients are at the river mouths get identified so that are clear for the users. So the plans for the next year and a half of this thematic assembly center are on improving the quality control procedure for the nutrient and chlorophyll in near real time at regional products, and being as consistent as possible with the multi-year products provided by the TAC. And again, this is based on interactions with the marine forecasting centers and with feedback based on the vertical profiles. There is also an effort to use the biogeochemical Argo profiles and compare them with other instruments so that it's possible to use synthetic profile in a better fashion. And as we mentioned, there is the interaction with the Emodnet chemistry to within the carbon multi-year product. Then I go to the Ocean Color Thematic Assembly Center, and as I mentioned, we do provide data across 3 different scales from the 3 different data streams that we serve. So we go from the multi-sensor 1 kilometer and 4 kilometer across all the regions in all the regions in Europe plus the global oceans, and then we have the Sentinel-3 data at 300 meters across in the same again globally in the coastal regions, and we do have the Sentinel-2 data at 100 meters across only for the European scene only, but is anyway a really big amount of data. As I mentioned earlier, we underwent our catalog in Copernicus 1 was growing and was becoming unwieldy to manage for us and for the service, but most importantly, it was difficult for the user to understand where everyone was. So we made an effort to organize the data sets and the products in names that make more sense. All of them, they have a coherence, and I know, and we also reduced the number of products and data set, even though our data volume has not changed dramatically. It's really more how you find the data to make sure that you get the information you need easily. So let's go to one by one on some of the main characteristics of the Ocean Color dataset at different scales. An important point to make here is that we do serve nowadays in all the basin these what we call blended chlorophyll datasets. And this means that across all of the basins, the most appropriate algorithm is based on a pixel, is chosen on a pixel-to-pixel base to ensure that the appropriate algorithm caters for the open ocean and coastal waters within each basin. And also, so this one depends on the kind of water type present in that pixel and in the bioptical characteristics of each of the regional basins, because we do know that ocean color suffers from how the biogeochemistry makes the color of the water. So as an example, this is an overview of what are the algorithms, the different regional algorithms that we do have for the 1 kilometer resolution data. And as you see, several of those algorithms are recent. So in the last 3-4 years, we made an effort to improve regionally all of the algorithms available for the basic chlorophyll product, which is the mainstay of our catalog. Similarly, if we move to the Olci 300 meters, you may have noticed that some of them remain the same. This is because there's been an effort to homogenize the data across scales, even though we do suffer from the fact that the radiometry of the sensors are different. So even though we apply the same processing chain, the algorithms are not, the final product differs, and that's one of our standard questions from the users. Important point to make as well is that for Olci, for the global product, we do offer the level 3 of the standard product without regionalization from the ASIS of the level 2 that get delivered by EUMETSAT within the Copernicus system. And we are the only place where to get level 3 within Copernicus for Olci. And again, this is the Sentinel-2 data at 100 meters, where for the time being is only served at the near real time since inception, so since January of 2020. And these are served as coastal stripes of 20 kilometers for the European seas. Because of the way Sentinel-2 acquires, that is acquired only every 5 days, so it's a bit different and a bit difficult to use them as we are used to global ocean observers. But there is a lot of details in the images, and they're useful. They're becoming useful for the coastal interfaces and are being picked up slowly, but they're being picked up a lot by the user community. We do serve suspended particulate matter turbidity and scatter, so property of the sediments, and we have a chlorophyll concentration algorithms. In this moment, we do have one pan-European algorithms for across European water. The effort is to improve them to make it regional, to make it regional as we have for the other ocean color. This is an example of our monitoring indicator. So in the monitoring indicator, we've been providing every year the trend for the chlorophyll trends. And this one is an example of the one that was delivered last year, so up to 2021. It gives a chance to see how the different basins are behaving. And similarly, this is the regional anomaly by using all the regional data sets at 1 kilometer resolution. The overview for the catalog, the main point is that there is an effort in the word, you see the word continuity a lot in this slide. So we were trying to make sure that there is a continuity across near real time and multi-year processor. There is continuity in the use of the on the same algorithms across the multi-sensor Sentinel-3 and also the Sentinel-2 datasets. And there is also the introduction, as I mentioned earlier, of the phytoplankton and primary production property in near real time and in for all the basins. Going to the multi-obs, this is the new product, which is the global surface ocean pH trend, which is provided as an ocean monitor indicator as well, and as a mean surface water pH, a total scale, a global integrated surface downward flux of CO2, which can be retrieved, and this is used has been used, for instance, as a way to assess the global ocean carbon sink in the recent global carbon program. The nutrient vertical profile has a new name, and again, as I mentioned earlier, this is an effort to take 1D observation, in this case, the nutrient and carbonate variable from the bioArgos, and with the neural network that makes with the neural network, there is the effort to produce a 3D field across the global ocean. The other product, which is the 3D chlorophyll and particular organic carbon plus the scattering of particulate, this is an effort where the neural network is trained on bioArgo, on biogeochemical Argo floats, and is applied to the satellite product with matchup. That's how the training was done, and then is applied on all the satellite data to produce a consistent 3D field of these variables at 1/4 of a degree resolution. So the perspective for the continuation is we do an effort to continue to integrate and validate the biogeochemical data and to try and widen our view towards ocean health, and to be able to contribute as much as possible to the improvement of the biogeochemical modeling and data simulation capability, particularly in view for the future digital twin of the ocean, which is close to becoming a reality. Important point to make is that we do continue the integration of whichever are the new ocean observing capabilities that are becoming available in our space, in the biogeochemical space, and there is an effort in the coastal and polar regions. This responds also to the hubs that are coming, the coastal and polar. And so the effort here is to improve the accuracy of the current essential ocean variables at basin level in the coastal areas, and paying attention to the shelf and the coastal zone, and to include, again, new biogeochemical EOVs related to the carbon cycle for in-situ and satellite. Thanks a lot for your attention, and we are waiting for you at the poster session to attend any of your questions.
Thanks, Vittorio, for this presentation. Now I let the floor to Marie-Laure to present the Green Ocean model.
Okay, so good morning, everyone. So I will try in a few minutes to show you the main achievement of the, the first slide. Oops, okay. I will try to show you in a few minutes the main achievement of the, sorry? Oh, yes. The main achievement of the Marine Forecasting Center as concerned the biogeochemistry. So the main point of my talk would be first to describe what have been the main evolution of the Marine Forecasting Center as concerned the bio for 2022-2023. Then I would like to highlight what was the impact of this evolution on the product quality with some example, and in particular how the data assimilation has improved the quality of the products. Then we'll move to a description of the system evolution for 2023-2024. Okay, so first, the system evolution. So here you see by bullet points the different evolution that have happened during the last 2 years for the different marine forecasting centers. So if I want to help you and to describe a bit what were the main direction of improvement of this biogeochemical forecasting center, you can see that we have mainly improvement in the data assimilation system, with essentially we move from only the assimilation of chlorophyll from the satellite to assimilation of nutrients and oxygen as well. Then we also have an improvement of the physical system that we use, moving to a new version of NEMO. And so that's what we have here, also nesting capabilities. Then we also have new model formulation in terms of representation of biogeochemistry, and essentially for the last 2 years we had improvement of the representation of the phytoplankton groups, but also of the radiative transfer modeling for some marine forecasting center, especially in the Mediterranean Sea. Then we also deliver new products. Zooplankton going to be common. It's a new product that most of the MFC are delivering. And we also have an important product, which is the plankton functional types. Okay, and then we have new simulation, which are described essentially by an extension of the multi-year products that we are producing. Okay, so now I will show you how this evolution have impacted the quality of the product with some example that I asked to my colleague. First example, it concerns the Iberian Shelf. Okay, yeah, but it does not work. Yeah. Okay, for the Iberian Shelf, what you can see, so we have an improvement of the physical system, as Emanuela has described just before, and the idea was to see what has the impact of the improvement of the physics on the biogeochemistry. And you will see that the impact were important and were positive. On the left, you can see the impact on the oxygen, and on the right, you can see the impact on the alkalinity. So on the left, you can see that moving to the new physical system has improved the representation of the oxycline. Oh, yeah, okay, but yeah, I have to be close. Yeah, it's not possible. Okay, that's okay. So of the oxyclines, that's the graph that you can see here on the left. You see that the model, even without data assimilation, can improve much the minimum oxygen concentration. And this representation of the minimum could be quite important, because when the oxygen has below some threshold, which is not the case here, you can have switch in the biogeochemistry. You can also see the impact if you look at the Hofmöller diagram of this new version. The V5 is on the top and the V6 is at the bottom, and you can really see the reduction of the minimum oxygen concentration. This improvement is also translated in an improvement of the nitrate, but it's not shown here, and in the chlorophyll gradient over the shelf, but it's not shown here as well. On the right, what you can see is the improvement of the alkalinity. So because you better represent the salinity on the shelf due to the physics, you also improve the representation of the alkalinity. And these two graphs show you the comparison of the model with the IC's data as concerned the alkalinity. And you can see that the graph on your right is much better compared to the previous system, the V5. On the bottom, you also have a comparison of the two versions of the model with the data. So the black curve represents the old version of the model, while the blue represents the data, and the red represents the new version of the model, and you see the improvement. So improvement of the carbonate system, which is also important if we want to speak about pH and about acidification. That's good to have a very good representation of the alkalinity. We move to the global ocean here. And here again, we want to see the impact of improving the physics on the biogeochemistry. And sometimes it's not obvious that because you improve the physics, you will improve the biogeochemistry. Sometimes it's the reverse because you need to retune your parameterization. So here in the global ocean, we compare the impact of using a new physics on the chlorophyll on the left and on the nitrate on the right. And so what you can see here is the first row, you see the data, the BGC data for the chlorophyll and for the nitrate. And the two lines below are the new version of the model, and the last one is the old version of the model. What you can see is the model data at the model information at the data points is the first column, okay? And on the right, the second column is the bias of the model estimated at the point where you have data. And so what has been found is that you have no impact of improving the physics on the nitrate, but on the chlorophyll, sorry, but on the nitrate you have an improvement, especially in the Southern Ocean. Okay, here it's an example of the Baltic Sea, the Gotland Basin. You also have a new physics, and you also have a data simulation in that case. And on the left, you see the previous near real-time system. This is the oxygen concentration. On the right, you have the new near real-time system. And if you can see it, I'm not sure, you have the data that are superimposed to the graph. And so you see that as concerned the oxygen, you have a better representation of the observation in the new version of the system. If you want to quantify that, you have the statistics of the error here at the bottom. And what you can see, if you look at the RMSD, is that the improvement is even better in the water which are located below 30 meters. You see really an improvement of the skill of the model. Now we move to the Black Sea. In the Black Sea, you have a deep chlorophyll maximum starting at the end of spring until the end of summer, early fall. This deep chlorophyll maximum, the depth of this DCM is very difficult to obtain. And in the previous version of the model, this DCM was too deep. And then everything is moving downwards. The light was moving downward, and you also have the neutral plane that was moving downward. So we improved the physics, and we moved to NEMO 4 in 2022 with 59 vertical levels concentrated in the upper layer and in the layer of the oxycline and suboxic layer. And this improved the representation, the modeling of the DCM, as you can see if you compare the Argo data, which is the first row, the previous version of the model, the second one, and the last version of the model, which is the last row that you can see here. You also have the statistic on your left. And of course, it's still not perfect. You see that in the Argo data, we have in the Black Sea, it's seen in the Argo data, this double DCM. We have 2 peaks of chlorophyll. It's very much investigated in the Black Sea. We suspect that the deeper one, it's due to the nitrogen fixers that we do not have in the model, and probably for this reason, we are making some tests now. We are not able to represent this double DCM. We just have one DCM. But we are working on that because that's very important in terms of nitrogen budget to have the right nitrogen fixation. Now we would like to describe what's the impact of the data assimilation on the product quality. As an example, I took the Mediterranean Sea as an example here. You see here 2 figures that compare the impact of the data assimilation system. The impact is estimated as a kind of relative difference between the free runs and the assimilated runs. And you see here the spatial distribution of this impact factor in 2 situations. On the left, what you see is the impact of the assimilation when you assimilate the BGC nitrate in-situ data. On the right, it's the same. You assimilate nitrate data, but you use synthetic products that has been reconstructed using a neural network. that allow you to estimate the nitrate using Argo, TS, and oxygen. And so, of course, you have more data on the right compared to the left, and you see that the impact of the assimilation system is more widespread. If you look at the bottom, you see here the root mean square difference of the nitrate forecast in 3 cases and for different regions. The regions are shown here on the graph, on the figure here on the left. For this different region, you see the RMSD of the free run, which is the blue curve, and of the assimilating run, which are the orange and the green curve. You see that the orange and the green curve are very similar, but improve the performance of the model compared to the free simulation. And you can also see, if you compute the statistics, that assimilating the synthetic product improve a bit the performance of the model by 45% compared to the free run. And it was 40 when you assimilate the in-situ data. Then the Arctic Ocean. The Arctic Ocean, this is the assimilation of chlorophyll, and you see here 2 examples of the impact of this assimilation of chlorophyll for the Barents Sea on the left and for the Norwegian Sea on the right. The upper layer show you the free simulation, and the lower row show you the assimilated simulation. And so you see that assimilating the chlorophyll data allow you to better represent the timing of the bloom in the Barents Sea or the intensity of the bloom in the Norwegian Sea. Okay, the global ocean, last example as concerned the impact of data assimilation. Here it's new as well. What is assimilated is satellite products, the soda product, that provide DIC and alkalinity in space. So it's a satellite product that you estimate from space, the DIC and alkalinity. These data are assimilated in the global ocean model. And from that, you also retrieve the PCO2. Okay, and so now we would like to show you what's the impact of assimilating this DIC and alkalinity on the simulated carbonate system of the global ocean. So you see here, the first row show you the product, so the satellite product. The second row show you the simulation of the model. On the left, you see DIC. On the right, you see the PCO2. For the model simulation, you see on the left, it's the bias of the free run. On the right, it's the bias of the assimilated model. So if you look for DIC, you can conclude that assimilating the DIC and the alkalinity improve the DIC simulated by the model, especially in the mid-latitude and in the high latitude. In the tropical region, in the equatorial region, we have some discrepancy that are investigated. On the right, if you look at the PCO2, you see more or less the same tendency. You have an improvement in the mid-latitude, essentially, but also in the high latitude, and you have some difference in the equatorial ocean. What has been done also is the comparison of the spatial average error, and this is the last graph that you can see. And here, if you look at the spatial average, the blue curve show you the free run, the red curve show you the error of the assimilated run, and you see that there is an improvement in both cases. So why to do that? To do that is to improve the simulation of the carbonate system, and for instance, the pH, it's very important, but also the air-sea CO2 flux. And here, the team has started to investigate what's the impact of assimilating the carbonate on the air-sea flux of CO2, and the results seems to be encouraging, but they are under investigation. Okay, now, what are the evolution for 2023, 2024? Again, you see here all the bullet points. It's the details. If we want to go into the main tendency, you will have improvement of the data assimilation system. What are these improvements? We expect a kind of big improvement. There will be some assimilation of synthetic product, as you have seen in the Mediterranean Sea, using neural network for reconstructing synthetic product. We also move to optimization of parameters. Most of the assimilation system estimate the state. I guess that the Arctic is stimulating the parameters, already know, but it will be generalized to other marine forecasting center in the next phase, or at least it's, the testing will be ongoing. Other development is assimilation, as you have seen, of additional variables, and now the carbonate variable are starting to be assimilated. And we're also moving to ensemble approach. Okay, the new physics, so we continue with improvement of the improvement of the physics and two-way coupling with the physics. New model formulation, so you have a generalization of the use of radiative transfer model in the different MFC, but you also have improvement of the zooplankton, for instance. New products, zooplankton, and also the oxygen demand units. New simulation, extension of the simulation, higher resolution, you have the details there, and also interfacing with the other Copernicus service, for instance, with the camps, providing the nutrient at the atmosphere, and also the CO2, and also with the rivers, using the EFS data for the river discharge. So new boundary, that's the new boundary condition. You see that there are a tendency to improve, to go to the radiative transfer modeling. I show you some example why we are doing that. So here is what is done in the Black Sea, two-way coupling between NEMO, the biogeochemical model, and the radiative transfer model. You need, of course, to have information on the spectral radiation at the sea surface. In the Black Sea, we use an atmospheric model that computes this radiative information, and you see the validation of this model at the bottom compared to Argo flux measurement. And on the right, you see what you can have with this new model that simulates the reflectance. You see on the top the classic model that simulates the chlorophyll and comparison with the satellite product. And on the bottom, you see what we call the pseudo-chlorophyll, which is the chlorophyll estimated from the model using the same inversion algorithm as the one used by the satellite. And you see that this comparison, this pseudo-chlorophyll, is in better agreement compared to the chlorophyll simulated by the model. If you compare with the satellite, here just look at the deep sea, because we were only able to use the inversion algorithm for the deep sea and not that one for the coastal area, which is neural network. And my last slide, and then I have finished. It's for the Mediterranean seas. They are also moving to the radiative transfer modeling, as you have seen. At the air sea surface, they use OASIM for providing the spectral irradiance. And for the new thing that I want to highlight here is the use of HPLC data to go to estimation of additional plankton functional types. And so here you see the HPLC data. It's the figure on the top corner on the left. It's the data set from HPLC. The different colors correspond to the different plankton functional types. You see the data. On the right, you see the same transect from the model. You see a new validation thing. And on the left, on the low corner, on the right, you see the plankton functional type simulated by the model for the Mediterranean Sea at the surface. And so you see an additional information as concern the functional type that we have, and an additional way of validating them, because we move to an additional information on the radiative behavior of the plankton. Okay, and so that's it. And I want to thank all the BGC members who contribute to this presentation. Thank you very much.
Many thanks, Marie-Laure, for this presentation. Very clear. And now if you have some questions, we have time for questions. No questions? Oh.
Maybe one for Vittorio on, because we have been discussing for quite a long time on how to improve, I don't know where Vittorio, okay, yeah. The evolution of the ocean coral product for the Baltic Sea. So a lot of interaction with user on the quality. So could you comment on all the different evolution we'll have this year or next year for the Baltic?
Okay, so the Baltic Sea is clearly an issue of the optical complexity of the basin it is an issue, so it's something that we are struggling with, and And so we have a physical limit on the fact that because of the water are so absorbing and because of all the dissolved organic matter, there are limits how much ocean color can actually do. Nevertheless, we are still continuing to have a look at the neural network that we're using. And so last year we changed all the processing that we are doing for the Olchi datasets to make them consistent with the multi-sensor dataset that we used. And in there, we do need, as much as possible, use and feedback from the Baltic community so that we can engage and identify some of the issues. We do have in our consortium the Finnish partner, so it helps us on that side. But the Baltic is also not only optically complex, but also optically diverse. So there are a lot of issues there. So that's the main focus on the algorithm development. The issue there is in the way to put it as elegantly as possible. In all the other basins, we do have those issues really only close to shore in some gulfs where we have the optical complexity. The old basin instead, in there, it is like that. So the lower accuracy is due to that fact. And as much as we want to make changes, we are limited by a series of the physics of the signal is like this. So we work and we're trying to improve it. And we do welcome as much as possible if anything else comes from the community, so from development out, algorithm developments out of our current activities. We are welcoming, we are ready to uptake it. But for what I'm aware, in this moment, there is not other effort ongoing. So it is an issue that we know we are trying to face.
A question for Vittorio and Marilou. I see that data-driven models like machine learning are increasing the capability of extracting information from observation, producing gridded data for biogeochemical variables. On the other side, the biogeochemical model become more complex and resolve more processes like light penetration and optics. So I see that there will be overlapping between product coming from observation and from models like phytoplankton functional types, reflectance, but also gridded data, gridded product from nutrients. So I see from a user point of view, there will be the needs for clarify how these different products can be used or can be integrated. What do you think?
I think that these products are not overlapping. They can be complementary because they are used with different approach. And so we can learn from each other what are the limitations of the product. And I would say that always the challenge is to provide independent error assessment on this product for the users. And I think that's something that is very important to see what's the error on the product that we are providing. So, and we see that for the biogeochemistry, we have to be honest, for the biogeochemistry, it's always a challenge because the data are very limited. And sometimes we assimilate this data. So when you make the validation, maybe these data are not independent, and maybe for the other products it's the same. So it's good to have this increase of products, but I guess that we have to pay attention to have a very thorough validation using independent information, and to have a dialogue between the different approach to understand why these products are different. Because it's, since the data are not enough to tell you this one is better than this one, maybe it's good to have a dialogue and just to understand what are the discrepancies, because the methodology is the same. One is mechanistics and the other one is more data-driven, and both can be combined.
And also, if I'm complementing Marie-Laur's, take, I think there is also something else. You're mentioning that, for instance, in an in Mediterranean, you're trying to improve as much as possible how the light is modeled in the water column. And so in there, we also have a chance to, and as was shown by Marie-Laure, to compare different intermediate products and different variables, so how it affects the underwater light climate. So in there, we have a better chance to compare with the in-situ data from the bioArgo, from the 2D fields that we generate from satellite, the 3D multi-observation, still observation, grounded observation provided by MOB, and then on the other side, the effort that you're doing with the modeling on trying to reconstruct those fields. And in there, we're gonna there is still a lot of work to do, and we have a way to improve the deterministic processes that you're describing, and also to figure out how much the data-driven approach is working in reconstructing those fields, because that's exactly, we do know that that's a model in itself. So that's where going back to the original 1D and 2D observation to see how accurate the 3D model reconstruction work may also come from the modeled fields. So there is a need for a dialogue to make sure to understand where the truth is. Unfortunately, the truth, if we cannot observe it, it's a limit. So there is a lot of effort, and we are converging towards improving the description of the system, and that's really, it's taking, I think it's, to me, that's the way, what I see as a good outcome.
Just to add one thing, the modelers try to go very to the source of the data. We simulate reflectance to avoid an inversion algorithm, and the data, they do the same, they go to the model. So it's a kind of, yeah. There was another question, I guess? Yes? Two questions, c'est bien.
So you say that in your rate transfer model, you are using radiation at the surface at different wavelengths. Are these available product, or you run your own atmospheric model to get the radiation at the surface?
It's a very good question. So we have a kind of exchange with ECMWF to see if they can provide us this spectral irradiance, but since it was not yet available, so it needs some effort for them side, we work with them, in collaboration with them, to introduce that to an atmospheric model that we are running, and we are validating. So I don't know, it's there. We validate it for the North Sea and for the Europe, in fact, also for the land and for the sea, and I don't know how we can do that, but we do that in collaboration with ECMWF. We use the module. They have a module there. We use it. We put it in the atmospheric model, and we tune this module for fitting the data. So it's not so different, but it's because they were not ready to provide that, and we would like to progress a bit. So that's the reason. But it would be nice to have this as a forcing. We already discussed that, but yeah, it's a very good point.
Yeah, still are not available, but yeah.
Yeah, it makes sense, because so far it's not consistent. In the Mediterranean Sea, they are not using the same as us, so it's, yeah. And the question will be there, because all the MFC are doing the radiative forcing, the radiative modeling now, so, yeah. There was another question, I guess? Yes? Giovanni?
Well,
Really?
I'll go while Giovanni is walking my way. Okay, it is really good to see that a lot of models are moving to the EFAS system for the rivers, but I'm wondering, are there plans to improve the coupling with true coupling with hydrology, both in terms of observations and models? For instance, are we able right now to deal with an amazing extreme event in the Black Sea, this a few hours ago, the blowing up of the dam in the Dnipro River. That will unleash amazing amounts of water, you know, and what is going to happen with the ecosystem. And it is not the one-way thing just to put the amount of discharge, but, you know, from the Black Sea model as well as, you know, back, for instance, you know, if the winds are such that they're blocking it and it's going to be released later, are we able to really give answers immediately, near real time, to the society, huge society needs? And also, in terms of connectivity between different MFCs, using again the Black Sea example, very interesting that there is the TSS system now in near real time, but I heard only in terms of giving boundary conditions in in Bosporus. What about connecting to the Mediterranean MFC, for instance? And so this amount that's starting from, you know, the dam in Dnipro, this water will end up obviously in the Aegean and so on. So are we ready, and what are the plans to improve this kind of connections? Thank you.
Okay, this is a very good question, and maybe Pierre-Yves, you can answer some of them. But for the river, just to answer for the extreme events, so practically we can add this extreme event and to see what happened, but the validation of extreme events with the system is maybe not something that we have done yet very well. So it's more the forecast of, I would say, classic events, but extreme events, maybe you need to check that more thoroughly if we are able to simulate this type of extreme events. And yeah, so that's for the river side. But the river data, it's really a problem, and you know, we have service evolution project on that to try to solve that, but it's still on the. And for the coupling of the different system, maybe it's more Copernicus answer.
Maybe very short because we are running out of time on this issue of the coupling between the different services. So there has been a project dealing with this coastal flooding system, so in cooperation with the Copernicus Emergency Management Service on us, and we try to provide boundary conditions. This is the XFAX project. You can maybe discuss with Angelique at the coffee break on this. This is where we try to keep what we need to do at the level of the marine and make sure that we provide the required information for the other services. And you mentioned as well the link with ECMWF for this forcing for the radiative model. I mean, we are building, in addition to what we explained yesterday on Thematic Hub, also to develop this cross-service cooperation. And for flooding and for the coastal, this is one of the aspects.
Maybe just for the last question, for the Black Sea, now the unstructured grid model for the Turkish trace system is operational, providing lateral boundaries for the Black Sea. Next year, it will provide also lateral boundaries for the Mediterranean Sea. So then the Mediterranean and Black Sea will be connected through this, let's say, connector in between. So there will be more exchanges between the two.
I have a comment to Willy. I think the digital twin and the Dito Model Lab will make available this what-if scenario, that basically we will have the Black Sea system able to run with a what-if scenario of river input. So that's exactly what we are aiming to do in the Dito Model Lab, even if we didn't think about river that much, but the what-if scenario will be there. And I think we'll answer to these extreme events, let's say, assessment. My question was on the multi-OBS product, because I think we are still behind the state of art, meaning, for instance, there is this product on 3D currents extracted from satellite and in situ. I think we are really lacking of, let's say, quality, but especially we are not giving to the user the enough information to decide which is the right product. Why should use multi-OBS global 1/4 instead of a global reanalysis or global forecasting, which is high resolution with data simulation? So I think we should put more attention, and I'm not at all against machine learning, but this should be done within the MFC and within the TAC, meaning with the expert of the ocean 3D component with the physics.
I I need someone from multi-ops to answer you on this one. I can't.
Hélène, are you here? Yeah. Okay.
You should catch up with them over the coffee break.
Okay. Oh, it's here. She's here.
Can you just repeat the question, please?
Well, my point is that multi-ops quality is not compared with the model analysis, so we just give an estimation of the error, and I think, especially for 3D currents, it's missing a part of the physics that cannot be substituted by simply extrapolation from in situ and satellite.
Sorry. Yes, for sure. This is not what we call a total current estimation. So yes, a lot of physics is missing in the 3D velocity, and in the future release next year, we will improve the uncertainty estimation by providing these variables in the model. And yeah, we are open for any comparison and with the model and other 3D currents. But for sure, this is not a total current fully total current reconstruction.
Okay, thank you very much, Hélène. You are running on time, and now we have to switch to the White Ocean part. So I let the floor to Cecilie to present the White Ocean observations.
Yeah. Okay. Oh, wow. I don't know where you found the picture, but that's me running uphill race in Norway. Okay, so we heard a lot about the blue ocean and the green ocean so far, and basically all of the TACs and MFCs are involved in these. So for the White Ocean observations, I will present results from only 2 TACs. But still, the White Ocean is extremely important. So to use a cliche, if the Earth is a patient with a fever, then the sea ice is the pulse that you need to monitor. All right, so we are many partners. So the names are below here. As I said, I will present the CS TAC and the sea level TAC. So these TACs provide very important data for many different user groups. So as we've heard many times, Copernicus is very much user-driven. So we have users within climate monitoring and research. We also provide a very important input for data assimilation and also validation of ocean models. And also on a daily basis, our input is very important for tactical navigation and important operations and scientific research in ice-covered regions. So we have a very wide range of products. So today I will only provide you some highlights from some of them, not all of them. We have both near real-time and also multi-year time series of reprocessed data, representing different temporal and spatial resolutions for ice-covered regions in the Arctic, the Baltic Sea, and the Antarctic Ocean. So from the sea level TAC, we have polar sea level maps and trend maps. And then from the CS TAC, we have sea ice concentration, edge, and type. We have CS drift vectors. We have thickness of the ice, which is quite interesting. We have sea and ice surface temperature. We also have long-term ocean monitoring indicators, such as CS extent and trend maps for the sea and ice surface temperatures. So to start with the sea level TAC, they are currently processing sea level polar maps and also along track products from satellite altimetry. So it's quite interesting actually that sea level can be observed from satellite altimetry within fractures in the ice, which we call leads. So the sea level TAC processes echoes of both specular, which are leads, and diffuse, which are open ocean. These echoes come from different missions, such as the SARAL and Altica, the Sentinel 3A, and the CRIOSAT 2. And this covers the ice-covered and open ocean regions. So we have several prototypes for the Arctic. We see some examples here of the absolute dynamic topography for the Arctic and Antarctic here. So as for the plans for this polar sea level undersea sea ice, these are typically used for climate studies. So we are going to, or they are going to use new advances in altimetry processing to do retracking and corrections of data. They will also extend the product backwards in time and also forwards, so to come as close to possible as current date. And in 2024 and forwards, the sea level TAC is planning to ingest data from EUMETSAT to produce operational sea level anomalies in ice-covered regions for the MFC. So moving on to the sea ice TAC, we have had some important evolutions this year. So our Danish meteorological institutes have been working very hard with a deep learning model called DMI ASIP. And this has resulted in a very high resolution CS product on a 250-meter grid. Here we see an example from around Greenland. So the figures show on the top left results from the DMI ASIP CS concentration, and on the right top you see results from the normal sea ice chart. And then below you see the SAR images in different polarizations. We also had to move quickly in order to make a new product to cover for the exit of our British partners. So they had important Antarctic sea ice edge product. We have now replaced this with a high resolution sea ice concentration, which is basically the same as the previous slides that I presented, also based on the deep learning model, and includes sea ice concentration and associated uncertainties. In connection with this DMI ASIP product, it's pertinent to mention a service evolution product that will come, that we will benefit from in the sea ice TAC. We are going to develop a pan-Arctic sea ice product, so actually covering the whole Arctic, not only the European part. So this is a SAR-based high-resolution sea ice product based on this deep learning model. It will be on a 1 kilometer grid resolution, and it will include sea ice concentration, stage of development, basically meaning how old the ice is, if it's new first ice or multi-year ice, and also flow size information, so how large is the ice flow, and also associated uncertainties. So this will be delivered as an aerial time product, but there will also be reprocessing done. So this is quite a lot of work to be done, and we will release this next year in 2024. Another product that many people are very interested in is icebergs. So in Copernicus, we started out with iceberg concentrations, so concentration within a 10 by 10 kilometer grid cell. Now we are able to monitor individual icebergs, but we have to be very careful that these icebergs are not confused with ships in the area. So these days, ships are carrying an AIS device. So this is used to remove ships which might be falsely detected as icebergs. So we have an algorithm in place. So I can show a couple of examples. So I don't know how easy it is to see from the figures, but you can see from the figures 1, 2, and 3, you can see ship tracks. So it's possible to understand that if you have observations in a straight line, you understand that this is a ship probably, and then this is confirmed by the AIS device. So then this can be removed and you have a safer detection of icebergs. So here's an example of how this CS filter works using the DMI ASIP deep learning model along with the AIS tracking. So on the left you have the result there, where you can see that the ice edge extends quite a bit out from the coast, whereas perhaps with the manual ice chart and older iceberg detection, there will be made a lot of mistakes where you would think there were icebergs, but actually it's closer to the coast and not related to that. Then we have, excuse me, what we call a sea ice type product. So type just means classification of the ice, if it's older or newer. In the Arctic, we can have ice that is several years old, but we can also have newly formed ice from year to year. What we see is, of course, that the older ice is disappearing, and even though you might have observations of ice, it's not necessarily a good sign, because it might be just ice that's formed in the same season. So it's very important to have this sea ice type product, so we're quite proud to have an automatic product. Results from different projects have provided us this operational product. So plans for the future is to use more data as input for deep learning. So we're going to have a SAR combination, satellite aperture, synthetic aperture radar data, combination of small and large coverage from 4 bands, and also passive microwave data from the AMSAR2 sensor from 6.9 to 89 gigahertz. So we will then get more output data. So we will move from classification to regression. So what we have now as a single dominant ice type will be replaced with concentration of the 3 most present ice categories in a stage of development and form. So these are compliant with the WMO classification. So in the previous version of the sea ice type, we would use dual polarization SAR from 2 bands, then apply the deep learning algorithm and get an ice type. So in the new version, we will still have the dual polarization SAR, but now with SAR bands. Then we will include input data from passive microwave from 14 bands, apply the deep learning methods, and then achieve as an output the partial concentration, stage of development, and form of ice. So on the right there we see a typical kind of matrix that tests how informative the satellite data is. I don't have time to go into the details of these, but you can come and ask us afterwards. At Met Norway, we have also been working on the automatic CS concentration products using improved AMSAR2 passive microwave input data, using a sharpening algorithm to improve the accuracy. As we see from the figures on the bottom here, we see a much higher level of detail in the ice pack. So this reduces the land spillover effects in the coastal zones. And in addition, we have used a new weather filter to be able to discriminate between weather effects and what is actually true sea ice. I mentioned previously that we have Arctic sea ice thickness. We have this in both near real time and as long time series. So what I'm showing here is the merged product, which is a merger between the SMOS satellite information and the CryoSat-2. So this provides a regular operational product throughout the Arctic winter season. And by the end of this year, we will have a fully reprocessed time series of data covering 18 years. From Ifremer, we have the multi-year sea ice drift for the Arctic and Antarctic oceans. So these are sea ice displacements at low and medium resolutions, which are based on scatterometer data, but we also have a couple of data sets which are based on merged scatterometer and passive microwave data. So these will these are reprocessed. So using ASCAT products from EUMETSAT, also using CFOSAT. So this will be reprocessed back in time, so using data all the way back to 1992 and all the way up to 2021. The Baltic Sea, the Finnish Meteorological Institute are very active. The Baltic Sea is maybe a small region, but it's very, very important since so much of the transportation of goods to Finland and also Sweden is done by shipping. So I think around 60 or 70% of goods transported to Finland is by sea. So it's extremely important for them to know how the ice conditions are. So they have been very active in using Canadian data from the Rheticus constellation mission. They have been using Rheticus-2 and now also the Rheticus constellation mission. They've been working on an expand CS thickness algorithm, testing this now this season that has been. Will be evaluated, or probably has been already now in May 2023. They have included sea ice extent as a new data set. Multi-year data is updated annually after each season in mid-June. And they're doing their best to utilize as many available satellite data as possible for their ice charting. So here's an example of what we call a C-band SAR-based mosaic. So a mosaic is an image that you get by combining several days, perhaps, of data. So instead of having one swath, you get a map of the region. So you can see incredible detail in the northern Baltic and eastern, I don't know what it's called, but the fjord going towards St. Petersburg there. So plans for the Baltic Sea ice products is to have an operational expand SAR using data from CSK, TSX, and PAS for CS thickness, which will start at the end of this year. They will have this CS thickness mosaic combining C-band and expand CS thickness. This will be tested next season. And then they're also using now convolutional neural network science to develop a new sea ice concentration algorithm. So throughout the sea ice stack, a lot of effort is being used on or expended on using artificial intelligence and deep learning. Again, using as much data as possible from multiple C-bands, SAR and Rheticus-2 and Rheticus constellation mission. We'll see what comes in the future. Then they have CS classification or degree of deformation or CS age type is in an early development phase. So here we see some expand CS thickness examples from April this year. And again, we can see that it has a very high level of detail. You can see ice variation close to the coast, close to important cities in the north and east of the Baltic Sea region there. So that's basically what I wanted to talk about today. So here are our sea ice experts from both the sea level TAC and the sea ice TAC. Thank you very much.
Thank you very much, Cecilie, for your presentation. And now I let the floor to Laurent for the white ocean model. Thank you.
Thank you, Anne. And so I'm Laurent Bertineau, and I was not running like Cecilia at the top of the hill. I will present you results from the white ocean. So it's a solid ocean in that case. It's sea ice, and sea ice concerns 3 MFCs. And I have had contributions from a lot of people. So there's the Arctic Ocean, as you know. That's the MFC that I am leading personally. But there's also sea ice in the Baltic Sea, as you've seen before, and in the Southern Ocean. So this first a little threat of what happens if you don't use Copernicus services. This is, say, an example from November 2021 when some Russian 24 ships got frozen in the ice, and then the AIS of these ships have become the only in-situ sea ice data you will see today. So that's trajectories in the ice of a ship. As you see tides, nicely, anticyclonic eddies, maybe, or winds turning. So if you are not really well prepared, there's a very high cost to that. And so from these dramatic events, there's different levels on which the Copernicus products can intervene, and that's from long-term planning, when you want to know how much fuel you need to take on board a year in advance, not so much precision on the geography, to the tactical, as you heard before, information on that you need to follow on a day-to-day basis if you're navigating in sea ice. Sea ice is also important for the sea ice ecosystem, for the ocean, because of the coupling with the ocean. And you need to know multi-year products in order to have a climatology, to know if the conditions are normal or not. Sea ice models, a word about that. There's 2 things in sea ice models, the dynamics, so there's the mechanics of how the sea ice is resisting to the stresses, and the thermodynamics, and that's how much it's freezing and melting related to thermal stress. So the dynamics can be simple, or they can be brittle, that's the most advanced one, as you see this example here. And thermodynamics can be simple as well, and they can be very complex in terms of, say, subgrid representation of the ice thickness, or melt ponds, or snow on ice. And unfortunately, you cannot have both. It's either dynamics are complex or the thermodynamics. So what do we have in the Copernicus Marine Services? We have a range of, different models. Not going through that. There's both the simple and advanced thermodynamics and dynamics. The models will all be upgraded in the year 2024. In terms of data simulation, there's different techniques used, from OI, ensemble OI type of techniques, to ensemble Kalman filter, or nudging for the more advanced models. And the variables that are assimilated are the concentrations, thickness, velocity, motions of the sea ice, or ocean variables below the ice. And in 2024, there'll be improvements in terms of more systems will assimilate sea ice concentrations and sea ice thickness. The atmospheric forcings, they used to come from ECMWF and the UK Met Office, but we will lose this diversity with the Brexit, so it will be the ECMWF model for all the MFCs. And the resolution is also on an increasing trend, both resolution in terms of horizontal grid size, but also the resolution of the vertical properties of the thermodynamics of the ice. With more models, we'll use multi-category sea ice. You will see the details of that. And so the asterisk here is to mention that yes, the Brexit is a severe loss in the sense that there were a lot of competent activities in advanced models used in UK Met Office that will not be part of the next steps. And multi-year products is a lot of the same, but say there's no reanalysis with a brittle rheology, and otherwise the resolutions and the type of models are more or less similar. So a word about the rheology. You see that it's either advanced rheology or coupling to the ocean or advanced thermodynamics. And the horizontal aspect of having the advanced rheology is visible on the left when you see the standalone NextSim model and the large amount of fractures and cracks and whatnot. Whereas the more classical Topaz model has classical rheology and also has ensemble averaging, so that smoothes the aspect as well. Next, what has been done to the NextSim model in the past year, there's been a replacement of the assimilation of passive microwave data by the assimilation of SAR-based manual ice charts. That was a request by the European Ice Services because they wanted to know the forecast when the coast is ready for is clear of ice, and with the pollution of land on the ocean, this was not really simple to answer. And now that with the assimilation of ice charts, you see that now when it's frozen all the way to the coast. So that's an improvement. While we were doing that, the model has also added few variables, the albedo, so the whiteness of the top of the ice, and the type of ice, multi-year ice versus first-year ice. There's a next slide about that. First-year ice is flat. It's, multi-year ice is rough, has a lot of ridges and deformations. And on the picture taken by my colleague Espen Storheim, you can see both in the same area. So there's always a bit of a mix of the two, but in general there are areas where there's more first-year ice and more multi-year ice. This is not going the way I want it to be, but still. And but in short, the model now produces the areas of first-year ice or multi-year ice and the concentration of multi-year ice, and this can be validated against the ice type product that Cecilia has mentioned before. In terms of the Baltic Sea, there's been improvements, not so much of the sea ice models, even though the sea ice model has been improved by upgrading to the NEMO 4 SI cube model, sea ice cube. And what's been illustrated here is the effect of assimilating ocean data on the sea ice. So if the ocean has the right temperature, then the sea ice will freeze in the right places. And that's what you see here, with examples of relatively large ice cover in the Baltic Sea. In reanalysis, the same has been done. The new NEMO model has been used in the long, almost 20 years, 30 years reanalysis, and with improved ice extent compared to the previous version of the product. So that's the illustrations for the extreme ice coverage. And note that here the ice concentration is not yet assimilated, so that will be planned for later. The global near real-time forecast has been completely upgraded, as you've heard before, and this has also led to an improvement of the sea ice. So you see the time series of errors of ice coverage, and you see there were peaks in the austral summers and in the beginning and end of the summer in the Arctic with higher errors, and these peaks have been reduced a lot with the new system. So you can guess that the position of the ice edge is more precise now in the global real-time system, and this has also led to an improvement of the ice thickness. Jumping to the OMIs, the indicators based on reanalysis, there's indicators of the sea ice extent in the Arctic and in the Southern Ocean, and you also see that the reanalysis reproduced this, say, Southern Ocean increase of ice concentration and then sharp decrease after 2016 in Antarctica. And from the Arctic reanalysis, there's exports of the sea ice through the Fram Strait and through the Barents Sea. So as a rough measure, 10% of all the Arctic sea ice is flushed through the Fram Strait every year. So if there were not production of the sea ice, it will alone empty the Arctic through there in 10 years. And so that is monitored as well from the reanalysis. So the status of updates in the first year of the Copernicus, this phase of Copernicus. There's the assimilation of ice charts, we've seen that, forecast of sea ice types, upgrade the ice export with a new reanalysis that's been produced a year before. And the Baltic has been improvement due to ocean data simulation, and the LIM3 model has been replaced by the sea ice cube model. both in maritime and multi-year product. In the global, there's been a replacement of the CIS model, so the LIM2 with a simple thermodynamics has been replaced by LIM3 with an, advanced thermodynamical model. And in the global system, there's been the loss of the UK Met Office reanalysis and coupled forecast, and that's regrettable. Yeah. Next, we'll have assimilation of ice thickness in the next sea model. That's what is prepared for the entry into the service this year. And we'll also work for a standalone next sim reanalysis, so more details and advanced rheology in a long-term time series. We are working on the new version of the Topaz system for the Arctic ice-ocean coupled system at 6 kilometers. You've seen how it does to the ocean, and this will also have advanced thermodynamics with the size 5 model. It will also extend on the Pacific side into the Bering Sea. The Baltic will assimilate CIS concentration in forecasts with the Ensemble OI, with the PDAF software. For the global MFCs, you will have high-resolution multi-year products with advanced thermodynamics with LIM3 that will come in 2024. And there's an ongoing upgrade of other global reanalyses with the SMWF ORA6 and the CMCC SIGLORS systems. And these are experts from the Arctic, global, and the Baltic MFC. Thank you.
Well, it's great to see so many people and much more online. I heard about hundreds of them here to hear about the role of upstream observation in the Copernicus Marine Service for product and application, and where the Copernicus space component and the European observing system is heading to best serve the marine community needs. From yesterday, was clear that Copernicus Marine Service critically depends on the near real-time availability of high-quality in-situ and satellite data. During the first part of the morning, we have seen how our thematic assembling center ensure that observation products are state-of-the-art and fit for use for our monitoring and forecasting center that use them for analysis and forecast. So, the first question that will come to my mind will be, can we quantify the impact of this observation product on the final outputs of our systems? To answer to this question, we have invited here 3 experts who will try to shed the light on this topic, explain how the impact can be computed, and providing some meaningful result to convince us that the theory is valid. So, the first aspect I would like to invite on the stage is Lotfi Aouf. Lotfi is the principal investigator, science principal investigator of CFOSAT and responsible of the wave modeling component at Meteo France and for the Copernicus Marine Service. Today, he will present us the impact of Sentinel-1 and CFOSAT on wave models. The stage is yours.
Thank you. Okay, thank you. Hello, everybody. I'm glad to be here to show you some slides related to the wave activity on directional wave observation. So this is a very interesting and very important progress in the last recent years, so related to the wave forecast. Why we need directional wave observation? I tried to summarize some headlines to respond to these questions. And the first one is since EnVSAT and the Sentinel-1 and the CFOSAT, we have 2 concepts of radar. The first one is well known as the SAR measurement. And for this, from Sentinel-1, we have a really detailed description of the waves in terms of frequency and directions, which is really important to, for the wave model. So this information is really needed because it touched the heart of the engine of the wave model, and the correction of such information will give you the best part of the wave parameters. And as probably some of you know, that there is different scale of the wave of the waves. We have a newcomer in this configuration of satellite mission, and CFOSAT with his instrument SWIM provide a better scaling of this directional wave observation, which captures better the wind wave, and it's complementary with the SAR measurement in terms of wind wave and longer scale related to the SAR observed above 500 meters. So in the wind wave transition to swell, we have a very delicate transition, and where the nonlinear wave interaction are very strong. And this part of nonlinear wave interaction is really uncertain in the wave model. And such wave observation will give you the best corrections in terms of transition, and also the scaling of initial condition of swell propagation after severe storms condition, for example. And also this will give you the best sea state parameters in terms of coupling with the oceans, related to Stokes drift, related to stress, and also ocean mixed layer in the upper layers. So with CFOSAT and Sentinel-1, we have also noticed that we can get the best extreme wave conditions. We also will provide, with such use of this observation, the most reliable wave product for the users, and particularly for user application for the coastal area. Here I put some images related to storms, which can hit the coastal area, and directional properties is really important. So here is an example of verification that we are doing time to time for the global MFC, as we are using directional wave observation since Sentinel-1 and updated with CFOSAT. This is this year, January and February, we have a deployment of very original Met Norway buoy, which we call it OMB, and some of the folks are here were in the boat deploying such measurement. And in this area of the Agulas, shown on the left part of the slide, we can see the overlapping of the streamlines of the trajectories of the buoys, and the wave height coming from the CMAM's global wave system. And in this case, we verified the model in very strong and intense wave current interaction regions. This is given on the right side, when we can see the variability of significant wave height from the buoys. And on the bottom, we can see the comparison between the model and the buoys, which are giving the best the slope for a different scale of the wave height. This is really important and shows that directional wave observation is doing the very good job. Another point as an achievement is related to wave development in cyclone conditions. And this year we had a very intense cyclone called Freddy, one of the longest in the record in the Indian Ocean. So more than 1 month of cyclone life in this period, and ended by very big damages on the eastern part of African country and also Madagascar. And the example here I want to show, we captured. We were lucky to have a passing over CFOSAT track, and we captured some directional wave observation which were assimilated in the system by the model. And on the bottom, I show the polar plot of the wave spectra, giving you the energy and direction and the frequency given shown by the circles. And we can see on the left, on the bottom, we have after the assimilation. In the middle, without any assimilation, and on the right, we have the difference. Clearly, we can see that in the frequency spreading, it's different between when we don't use the assimilation and with the assimilation. We can see this in terms of corrections, showing that there is an underestimation for the high frequency part of the waves, which is more related to the wind, and also an underestimation in the lower part of the frequency of the waves, which is more related to the swell. So here, as a verification, for this case, we can see the variability of significant wave height in the cyclone Freddy from east part to south, moving just close to Mauritius Island and the French island La Réunion. And we can see the comparison by independent wave significant wave height from HY2B shows a very good agreement in the middle on the bottom from the model of CMAMS and HY2B. It's capturing very well the peak of the event with more than 8 meters in this comparison. So one of the places where the assimilation of directional wave observation is well represented and the most powerful is in the Southern Ocean, where we had the fiercest wind conditions, very high wind generating storms. And this is an example to show you validation in the winter time in the Southern Hemisphere. On the bottom to the left, we have, without data assimilation, a bias of significant wave height compared to independent data. On the top to the right, we have with only assimilation of SWIM, and on the top to the left, when we use SWIM and SAR, and this shows the complementary of these two sensors. And you can see clearly when we use CFOSAT, so we reduce strongly the bias in the Southern Ocean, and when we use both SWIM and SAR, we really remove the bias, particularly near in the marginal ice zone and also on the swell track in the Southern Ocean. To summarize this, we can see on the bottom to the right what's happening by comparison between the PDF with the assimilation and without assimilation. So that the model is really fast, is putting faster the moving to swell condition. So then this indicates that there is an underestimation for smaller peak wave period. And this is a kind of consequences to the longer waves, which is overestimated by the model. We also implemented the directional assimilation in the EB, and here's an example showing some very good, very spectral information given by a long track in the Gulf of Biscay, and the comparison shows in the coastal area, for example, in the French Basque country at Saint-Jean-de-Luz, comparison with the buoy given by the bars. And shows the period peak comparison. We can see clearly that when we use the assimilation in red and blue, it reduces strongly the scatter index of the peak period, and this is enhanced in the longer period. So, when we move from short scale to long scale of the waves, we have an enhancement of the correction, which can reach more than 30% of the corrections. So some of the MFCs are starting to do the job of verification of their model with the directional wave observation. This is an example of the Black Sea and preparing themselves to assimilate this in the system. Black Sea is really a very, there is a very strong uncertainty related to the wind field, and the verification with directional wave observation is really important. And this is an example of the Black Sea showing a very good comparison between CFOSAT directional wave observation and the Black Sea wave model. A very important and very, how can I say, outcome and finding for CFOSAT is the detection of rogue waves. Rogue waves is very dangerous seas, and it's really not easy to capture. In this case, I show here on the left to the top an example of ship container accident offshore Sydney, when we have a very damages, losses of containers, and on the bottom to the left, we have happily passing over CFOSAT track. And an example of the spectra observed by CFOSAT is shown on the bottom to the center, and we can see that in this case we have a very intense three-system, dominant system. One is wind wave and two swells coming from the southwest to the southeast. And also we have a very close frequency range between the wind wave and the swell, which meaning that there is a very intense nonlinear interaction between the wind wave moving to the swell. And on the top in the middle, we show the maximum wave height for this case, and we can see clearly that we are exceeding 16 meters in terms of maximum wave height. We can compute some indicators like the one which I show here on the right side, which is a crest to trough correlation, which is really dependent on the frequency spreading of the spectra. And you can see in this case, we have very high values of the correlation of crest to trough. This is really important and show that in this case, we have a very strong interaction, current wave interaction, which is enhancing the nonlinear interaction between the waves. This can be provided in the system and also improve the capacity of CMAM's wave product to predict rogue waves. Finally, I want to highlight here the impact of using a better sea state at the surface, the better sea state we have at the surface, and the better ocean key parameters we will get in the ocean. So, and this is an example on the top. We have the impact of using wave forcing with the improved sea state and without using wave forcing on comparison on the ocean mixed layer. And you can see clearly when we add the waves in the ocean that we enhance the ocean mixed layer in the Southern Ocean, and there is a dipole variability, and also we shorten near the marginal ice zone the ocean mixed layer. On the bottom, it's a verification on the left side, the bottom, without any coupling from the waves with the improved sea state, and on the bottom to the right with the wave coupling. And we can see clearly here in the comparison to the current intensity, we improve significantly the current intensity when using the wave coupling in the tropics and also particularly in the Southern Ocean. So some key messages here. So we have really a success story in spectral assimilation for the global and for the EB. And really we want to extend the use of such a assimilation system in the other MFCs, the Arctic, the Black Sea, in the Med. This is really important to provide the best wave product for user application. So satellite directional wave observation are really skilled to better forecast sea state in extreme conditions. And also in terms of wave reanalysis, we are also preparing a new version of reanalysis, EB and wave rates for the global. And this will use directional wave observation from CFOSAT, Sentinel-1. And also we can exploit past mission or SAR missions, which is like the one of EnVisat. And really I want to highlight that because we have a very long record in terms of directional wave observation between 2002 until 2012, which is really important in terms of studying wave climate and also some trends related to the waves in the global scale. So improving the ocean wave coupling in CMAM's MFC related to this kind of directional wave observation. And finally, some expectation for the future missions. We have ongoing works to Sentinel-1C, so this is to the agency, and 1D. We are waiting for that, and really we hope that we can get this directional observation to keep on this kind of assimilation and harmony. But until now, there is no follow-on for CFOSAT, so we don't know the future, but probably we wish that we can have some follow-on for this instrument. Thank you.
Thank you, Lotfi. Thank you very much. So, the second aspect of the session will be Giampiero Cossarini from the National Institute of Oceanography and Applied Geophysics in Italy. Giampiero is responsible for the biogeochemical modeling component of the Mediterranean Copernicus Marine Service, and he will present us about the impact of Argo floater networks on physical and biogeochemical models. The ground is yours.
Thank you. Good morning, everyone. It's me before the era Argo. Yeah. Okay. Thank you for taking this picture. Okay. Oh no, I just want to start acknowledge all the co-authors of this presentation. They helped me in assembling the slides and sharing comments and discussion. I think part of the success stories from them. I will briefly introduce the fact that Argo and biogeochemical Argo have been a revolution in observing, monitoring, and then forecasting the ocean interior. I will show some examples how Argo and biogeochemical Argo are key components of the Copernicus monitoring forecasting system in validation, model development, and data assimilation. And I will like to say that there is an interconnection between the observing systems and the prediction systems, and I will give you some conclusion at the end. First of all, I would like to say something obvious, that the ocean is a three-dimensional environment, and that models are very useful too for monitoring the health of the ocean at surface and in the interior. A first revolution in modeling or in prediction system was the introduction of the satellite observation that covers the surface of the ocean with spatial and temporal high resolution, high temporal observations. Computer science, computer power increased the resolution of the model. It's been the second revolution for modeling capacity. And the third revolution was the introduction of the observation of the ocean interior, thanks to the autonomous sensor like Argo that measure temperature and salinity profiles, and the biogeochemical mission that measure chlorophyll, nitrate, oxygen, and other optical variables. They increased a lot the number of observations along the water column profiles, as these two figures show, starting from 2003-4 for physical variables, and in the last 10 years for the biogeochemical components. These observations are a key part of the Monitoring and Forecasting Center in Copernicus. Two important tasks are used with this data, validation and model optimization. All the Copernicus systems that have Argo in their domain use temperature, salinity, chlorophyll, nitrate, oxygen for validations, but also mixed layer depth and velocity, taking advantage of the Lagrangian component of Argo, are used in some physical system. And for biogeochemistry, also backscattering power and carbonate system reconstructed variable through neural network are also used for validation. Looking at the assimilation, which is the other task that use Argo, I would like to say that together with the altimetry data, all the physical systems use temperature and salinity profiles in their simulation schemes. For biogeochemistry, as we saw this morning, most of the systems are ready or are ready to incorporate in the operational system the assimilation of biogeochemical profiles. In the next slide, I would like to show some example how Argo are used for validation and assimilation. An example is from these two figures that show the time evolution of vertical profile or root mean square differences in the global and in the Mediterranean Sea. And they provide information about the capability of the model to reproduce the spatial temporal variability of temperature in their domain. And they have different color scales, but the key message is that the models are good, and the higher uncertainty are in the simulating the thermocline during summer period, the red area in both figures. A second example is the use of Argo for validating derived variable like the mixer layer depth. In this case, for the Arctic, there are two regions. The bias is computed for two regions. In the Black Sea, the bias and the root mean square difference in blue and red over the domain of the Black Sea. And key message is that the models are good in reproducing mixer layer depth during summer period with a higher error, higher uncertainty during the winter period. Metrics are really good for informing on the quality of the forecast or the forecast of the model output, but also visual comparison can be useful for looking at how the model reproduces coupled physical biogeochemical processes. In this case, in the Iberian Biscay Irish Sea, at the two locations for two floats, one in the North Atlantic and the other in the Mediterranean, chlorophyll and oxygen from model are compared with the Argo, with the time series of Argo profiles, and we can assess how good the model is in reproducing important biogeochemical processes like the winter bloom at surface or the onset of the deep chlorophyll maximum during summer, and the following oxygen subsurface maximum in the oxygen part. On the other side, a very good example comes from the Black Sea, where from January to December, the vertical profiles show how the model reproduced the vertical structure of oxygen with a very peculiar condition in the Black Sea of the presence of an oxy layer below 200 meters. And in this case, the model is good in reproducing the seasonal cycle, but is a bit too high to depth with respect to the biogeochemical floats data. Argo are used for validation, but also for assimilation in constraining the model evolution to get better results. In this case, for the Mediterranean Sea, very good example because of the high density of floats profiles. The new system that will be put in place in next November will include the assimilation of temperature salinity profiles together with the sea level anomaly. The system already has assimilation of sea level anomaly. And in the next November, the new system will have the assimilation of temperature salinity profile also in the Atlantic part of the domain, and increasing number of profile also in the Mediterranean because of improved pre-assimilation quality check. And key message that we can learn from the profile of root mean square bias of temperature in the two areas is that including more data, we can have a lower a decrease of the value of the root mean square and biases, and this improvement is mostly in the subsurface layer below 500 meters. Mediterranean offer another good example for the assimilation of biogeochemical Argo float. The biogeochemical model has a variational scheme that assimilates ocean color since 2013, and starting from 2020 assimilate also chlorophyll and nitrate profile, and very recently, last November, also oxygen profile, thanks to an increase of the near real-time quality check for oxygen data. And different color indicates the profile or root mean square error of the model at the different versions, and the most recent one are the light blue, green, and orange, and they show how the assimilation greatly improved the model capability in subsurface layer below 500 meters. We can consider that it is very important for biogeochemistry, the euphotic layer between 0 and 200 meters. And also important correction are in the deep biases in the nitrate and oxygen. In the global ocean, the reanalysis performed with the GLORY system, that is a NEMO and a reduced order Kalman filter, assimilate the sea surface anomaly, sea surface temperature, ice concentration, and also temperature and salinity profiles. And the time evolution of profile or root mean square differences show that starting from 2004, the error, the red pattern, became yellow, and showing that the error decrease, and there is a clear correspondence with the increase of the number of observation assimilated, and that's corresponded to the inclusion of the Argo data in the reanalysis system. And this is achieved when the density of Argo profile reach the number of 1 float per month per box of 3 degrees. It's important to say that model benefit from the new development plan of Argo program in terms of increasing the capacity of observing key areas like the Southern Ocean, for example, and also the new biogeochemical and deep missions of Argo. On the other hand, in this positive feedback cycle between the observing system and the prediction systems can provide useful information for designing the next generation of observing system. And on the other hand, since they use in a real-time condition data, they can provide best practice for quality check and also for analysis of the intercomparison and interoperability between the observing system. In the next 2 slides, I would like just to show a couple of examples. First example is the positive impact of the new mission of Argo, the biogeochemical mission of Argo, in allowing a new way for improving model parameterization and tuning. In this case, Argo biogeochemical and Argo data are used in a 1D configuration of models. The physics is constrained by the Argo data, and so the biogeochemical variable can be used for model improvement. In the case of the ARTI, the Cosmo model improve the parameterization of phytoplankton productivity with in the bottom right, with a decrease of the root mean square difference of the simulation of winter bloom and the deep chlorophyll maximum. The the dark red area disappear in the root mean square plots. In the Iberian Biscay and Biscay system, particle filter algorithm is used to tuning model parameter with the use of multivariate input data. A last slide to say that models can provide the feedbacks for observing system in terms of complementary of the different observing system, satellite and the Argo profile. In this case, the global GLORIS system is used in observing system simulation experiment. Synthetic observations are generated by a realistic run and then are assimilated in different assimilation run with different combination of the different observing systems. And the metrics that are used to evaluate the different impact of observing system is looking at the variance of temperature computed at different spatial and temporal scales. Different spatial and temporal scales are computed using a filter of the model output with the different running bin windows. And the key message is that altimeter is very important to constrain a model to reproduce the variability of temperature in the intermediate scales, while the profiles are very important for the large scales. And to conclude, observation of the ocean interiors is complementary to the observation of surface. They are really important for modelers in terms of a better quantification of the model uncertainties at the different temporal and spatial scales. Model physical and biogeochemical greatly benefited from vertical profiles in terms of better reproduction of vertical structure and vertical dynamics. And Copernicus prediction centers collaborate with the observing system in different projects, international programs, and this collaboration should continue because it's very positive. Yeah, and thank you.
Thank you, Gianpiero. Thank you. So we have a third expert, which is my colleague Elisabeth Remy, that should be connected online. Elisabeth?
Yes, can you hear me?
Hello, bonjour. So Elisabeth is head of the Service Observation for Analysis and Forecasting System, which is focused on studying how ocean and in-situ satellite observation can improve the ocean analysis and forecast. And today she will present us the impact of Sentinel 6 and Sentinel 3 and the altimeter constellation physical model. So the ground is yours.
Good morning, everyone. So I will first give you the context before going into showing the impact of altimetry, the sea level data on the physical models, the physical running in the MFCs. So today, for the first time, we are 7 altimeter missions that are available through the in-situ, through the sea level TAC. So the Sentinel 6A was the latest one and is now the reference mission, as it was JSON 3 before. And in addition to the Sentinel JSON, we also have the CryoSat, Altica, the Indian mission, and also the Chinese Ayang 2B mission. Next slide, please. So here it's just to show you that 3D altimetry is used by all the MFCs and all the missions except just the Chinese one for some of us. And JSON 3 in its new orbit, as well as the Sentinel 6A, are already used and assimilated in the different MFCs today. Next slide, please. So now it's an illustration of the monitoring and real time of the systems in terms of SLA. It's coming from the global system. So the map on the left is showing the difference between the observations and the analysis for the global 1/12 system, and it's the standard deviation over 1 year. So the main feature that is the highest misfits are found in mesoscale rich regions, and so meaning the western boundary current and also the Antarctic synchro polar, and we have much quieter and lower level of misfits in the interior of the gyre. So if we now look at the curves on the right, it shows the time series, the evolution of the misfit between the analysis and the different missions. So the colors are representing the different missions. And what we can see is that the Sentinel mission, as well as JSON 3, has the lowest level of error with LTK, as CryoSat and HY2 has the largest errors. So, and sorry for this statistics are coming from the linear box. So where you can see the level of the misfits is between 2.5 and I would say 3 centimeters. So it's more or less the level of the observations error. So really showing a good accuracy of the systems. So next slide, please. So in terms of how the altimeters are integrated in the MFC, so as you've seen from the timeline of the constellation, there are often changes. So first, the sea level TAC made available data set to test for the MFC, so to have their feedback. And then the MFC can do a double simulation in order to test there is no problem with the data set and discuss with the sea level TAC. For the Sentinel 6A, it was at the end integrated by all the MFC in October 2022. And in addition to those kind of routine, I would say, integration, there are also specific studies that are conducted by MFC to assess the impact of a given mission. So it was the case for Sentinel 3A. And the last year, we did it also for Sentinel-6A, and I will show you the results next. And for just to mention that for JSON 3, when it was moved to its new orbits, it was just reintegrated without any specific studies. So this impact assessment is done by running what we called OSI, for Observing System Experiments. So two similar data assimilation experiments are compared, and the only difference is that a given data set is denied from the analysis in one of them. So in that case, we removed Sentinel-6A in one of the experiments and compared to the simulation with all the altimeters assimilated. Next slide, please. So here it's an illustration from a previous, so Sentinel-3A with the global system. And the maps show the enormous difference between the simulation with and without Sentinel-3A, sorry. And we can see that the reduction of error was the largest in Western boundary current, and there was a reduction quite everywhere in the globe. And in terms of explained variance, the reduction is quite homogeneous and reached 10% over the whole ocean. Next slide, please. So concerning the observing system experiment running for Sentinel-6A, most of the systems that were able to do so as those data in the region run those OSSE that I will show the results in the next slide, please. So here it's for the Black Sea. Those curves are showing the evolution of the errors in SLA between the simulation with Sentinel-6 and JSON 3 in orange, and in blue, and in orange without those two additional altimeters. So we can see that there is a RMS error reduction over the last period, because before it was not completely homogeneous, so after May 2022. So next slide, please. So now it's a different view of the impact of Sentinel-6A and now on the Mediterranean Sea analysis. So on the left, we can see the map of the differences in SSH for a given date. And they are mostly at mesoscale. And on the right, left surface height and right, the temperature. So they are not only changed for the sea surface height, but through the covariance of the model, we have also temperature change at depths here at 50-meter depths that are still kind of at mesoscale. And in terms of SLA misfits, there's a slight improvement to the other altimeter observations, so showing a good coherency. So here it's a kind of illustration that by having more and more altimeters, we're able to have finer scales that are changed. Next slide, please. So here, still the impact of Sentinel-6, but on the Northwest Shelf system. So I will more focus on the map. So again, there is a change really at mesoscales, but not so clear change of the overall statistics for the RMS and bias over the entire domain. Next slide, please. So before I showed you the, the impact of just adding one altimeter, but during those last year, there was many changes for the sea level observations that are provided by the sea level TAC in terms of correction, but also the resolution. So they were coming from 14 kilometers to 7 kilometers. There are also updated MDT. And here it's an illustration for the MED system that all of those changes really lead to an improvement in terms of the assimilation of sea level anomaly. And there's a decrease of 10% in RMS. So here just for the MEDC, but it's also true for other MFCs. Next slide, please. And now looking at the future, so it was just launched. The first data are really promising. And there is the wide source altimetry is also considered for the Sentinel-3 next generation constellation. So here is just an illustration of a study that was done with simulated SWOT observations and to assess their impact on the global system. So, and from the top curves, we can see the variance, the error reduction in variance for the analysis if we consider only altimeters with altimeters mission, SWOT, or the combination of both. And we can clearly see a big improvement where both are considered. And we also looked at diagnostic to assess the impact that are more related to applications. So, for example, drift of particles. So here, a drift of particle was simulated, and we looked at the error in distance that, depending on the experiment and the data that were assimilated. So we're able to show that after 7 days, with the nadir, there are 56% of particles that are still within 50 kilometers of error. And this number is much larger when SWOT is also assimilated. So next slide, please. So as a conclusion, the integration of Sentinel-6 was successful in the different MFC systems. We found that the level of error was really coherent with the other altimeter data sets and even lower. And for the dedicated experiments, they show a slight improvement in SLA in some system and also change in the mesoscale structures. But point to say that it's quite difficult to assess the mesoscale differences because it requires high resolution observation. So it's more specific study in given region where we have these possibilities. And in terms of system performance, they are continuously improving with the system and observation evolution, such as new SLA treatment, new MDT, improved assimilation strategy, and with also the model that are integrating more and more processes and smaller scales. And of course, for the future, the arrival of WISOS altimeter will revolutionize the future of altimetry and of course for the MFCs also. So all of those, so in the provision of the analysis and forecast is more and more accurate now. Thank you.
Thank you, Elizabeth. So thanks to all the speakers for the interesting and inspiring presentation. So we can say that it's clear that Sentinel are providing a huge quantity of data that are positively impacting CMM Copernicus Marine product. It's also clear that in-situ observation are of paramount importance for the service, and also they have, because they can monitor the interior of the ocean, and they have a general positive impact on our products. But now it's time to take a look at what the future holds for observation. So we start the first roundtable of the day. It's a pleasure for me. It's a pleasure for me to have with us today the representative of the organization we work with to ensure that observations are always up to date and correctly flowing toward the service. So I welcome Inga Lips, Secretary General of EuroGOOS, Lieven Bidekekke, Copernicus Program Manager at EUMETSAT, and Craig Donlon, which is the head of Earth Surface and Interior Section at European Space Agency, and Pierre-Yves that will co-chair the section with me. So I think we can all take a seat. You should have a microphone that are already on. So, okay, so, well, as the time is running short, let's start with the first round of questions. I start with Lieven. So, we know EUMETSAT has been so far the key reference to provide the data which are needed for the development of our products. I can mention Sentinel-3, Sentinel-6, but also our other contributing mission. So I would like to invite you to briefly summarize EUMETSAT perspective on how the Copernicus space component will evolve during the coming years. Should be probably.
Thank you very much, Antonia. First of all, let me say it's really a pleasure to be here. It's in a beautiful room, and I find myself with an amazing audience as well, amazing group of people. As you know, we work quite closely together with CMEMS on different topics. We have regular meetings and so on in order to discuss exactly these changes and evolutions of the space components to make sure that we at EUMETSAT are exactly delivering what you need. So I think there are three different aspects to those evolutions. First of all, there's of course the current generation of the Sentinels. So we currently operate Sentinel 3 as well as Sentinel 6, Jason 3 as well, with KINES. And there, of course, they have been launched for quite some time now. And we're looking already to renew the current constellation. So first of all, we have the Sentinel 3 C and D units, which are about to be launched in a couple of years' time, of course, as well as for Sentinel 6B. And Sentinel 6B, as you know, is a multi-agency effort. And Sentinel 6B is planned for launch by NASA in the end 2025 period. So that is the first of the long-term continuity, I think, that can be guaranteed through those recurrent units. And together with Craig, we've already been, or Craig was actually starting the discussion on the tandem as well for the Sentinel 3 units, which I believe will be very important in order to guarantee the quality of those data. Secondly, we also have been working quite a lot on product evolutions, and I think some of them were mentioned already this morning. So we're looking at not only improving the quality, looking at improving the screen, the cloud screening, atmospheric corrections and so on, but also looking at new products. For example, the level 3.5 Hertz product, which we hope that we can actually deliver by the end of the year. And then also a new product called CI's surface temperature, which we have pre-operational, but we intend to implement in an operational scheme. Then secondly, that's more related to your question, of course, there are the new missions, and they're the two main aspects as well. So first of all, there are the expansion missions, there are 6 of them. At EUMETSAT, we're involved in 3 different ones. So for the first is CO2M, very challenging mission, very challenging timeline as well, but maybe less important at this point in time for CMEMS. And we're also heavily involved in Crystal and Simmer. So those 2 missions are primarily polar missions with objectives to monitor the ice caps and the White Ocean. But we at EUMETSAT, we will be responsible for the development and the operations of processing chains for the global aspect. So that means for Crystal on global topography, on altimetry, producing sea level products as well as winds and so on. For Simmer, it will be slightly different, and there we're looking into producing products also at global level on sea surface temperature, for example, but also on salinity and other types of things. The second part is when those missions are actually right now being developed by ESA, and we're actually quite advanced. I think maybe Craig will say something more about it later. And those are normally planned for 28, 29, so more or less. When we look much further into the future, we get to the next generations of what is relevant for EUMETSAT is Sentinel 3, the Sentinel 3 NG series, and those have been decided to be split into 2 different satellites or satellite series. That is the Topo one, and there's also the Sentinel 3 NG Opt. And Opt is, I think, still quite far away. It's in the early 30s, so it's almost a decade away, where the definition is about to be started. And we, from EUMETSAT, we will also share our expertise in operating Sentinel 3 into the definition and the requirements definition of those missions. Sentinel 3 NG Topo, I think, was also mentioned just before. It promises to be a very challenging mission at the moment. It's maybe even a game changer, where ESA is currently also looking at the wide SWAT technology in analogy with what is done with SWAT. Of course, there's still a long way to go there, and there's still long things to be proven. So, in a nutshell, that's a little bit the what's coming from the EUMETSAT side.
Thank you, Lieven. and thanks for the nice overview and for the good news about Sentinel-6, the follow-on that is secured. This is, I mean, we know the importance of the reference mission, and it's important to know that this will be continued, at least for the next 10 years or more. Okay, so in a similar spirit, ESA is providing unique satellite data for many missions to our production center. So again, Craig, I would like to invite you to tell us about ESA priority action to improve the Copernicus space component in the coming years.
Okay, thank you. Oh, great. Great to be here, great to see old friends and new faces for what's really a wonderful community dedicated to oceanography. And one of the things I want to say is that when I look at the way we present CMEMS today, we have the white ocean, the blue ocean, and the green ocean. But the big sell is the deep ocean, because that's what you really do. From space, we can see the surface ocean, and we can see the surface ocean very, very well. And we need to connect space observations to what we see at depth via the in-situ component, which we'll talk about. But the model is the way to do that. And I think that's a trick that's missed a little bit here. And perhaps in future, you should think about adding the deep ocean to your portfolio. Leiden gave a great introduction to where we are. Our job at the European Space Agency is to develop the spacecraft and the payloads that serve this community, as well as others around the world, for a suite of observables that are required in everyday life for people living and working on the ocean, but also for policymakers that need to understand how to set policy, how to monitor the policy impacts that they've set, not just in Europe, but across the rest of the world. And that means we need good evidence. We need good evidence-based observations that can be trusted, that you can rely on to do your job. I don't need to wander through all the spacecraft that Leiven's talked about, but there are some key elements that are very, very important. Continuity is what we're about at the moment in Copernicus. We need to make sure that we provide continuity of the observations that you've received from the first series of Sentinel satellites. And we've been listening very hard and working closely with EUMETSAT, the European Commission, and all the services in Copernicus to make sure that we can go beyond what we have today. And there are significant gaps, and there are significant missions that will bring about big changes. Since the early days of CSAT in the late 70s, we had microwave radiometry. And Ian Robinson, which many of you may know as my old professor, alma mater if you like, he always said it's a silver bullet for oceanography. And that's what we're bringing together with EUMETSAT and the Commission today through the CIMA mission, the Copernicus Imaging Microwave Radiometer. This will bring you, for this class of mission, very high resolution, so 10 kilometers after gridding, sea surface temperatures every day, together with salinity at 35 to 40 kilometers, together with estimates of the wind vector, all contemporaneous and co-located. The sea ice is a primary driver, and I think someone said a great phrase earlier today. If you know the temperature of the ocean, you know where the freeze should take place. It was, and that's really important. So the CIMA mission will give you 8 passes across the Arctic Ocean every day, once on orbit. We have 2 of those being developed right now, and the first launch should be in 2028-29. They work hand in hand with the Crystal mission that was mentioned before, next generation dual frequency Ka and Ku band altimeter. And together, those 2 missions will give you an unprecedented picture of the sea ice. We heard a lot about the synthetic aperture radar. We will bring the Roselle mission into the fold, an L-band SAR mission that will work seamlessly with the Sentinel-1 next generation mission, giving you the conventional C-band SAR. So we'll have a great picture of what's taking place in the White Ocean and globally, just at the time when we expect from our IPCC colleagues to see the demise of the Arctic sea ice in the next 20 to 30 years. That's what I mean about bringing observations to bear on policy making. We know that the Arctic is changing dramatically. We need to observe it and bring the observables, the evidence-based observables, that allow our policymakers to do their job. And CMEMS is fundamental to all of the work that we're doing here. I can go a little bit further because we're not alone in the way we need to work with the land. SWAT has been mentioned, but there are other missions that are coming. which will enable us to have a better view of the hydrology cycle and the carbon cycle. The CHIME mission will give us multispectral capability over the land and over the coastal zones. The next generation of Sentinel-2 will give a slightly wider swath with more bands. The next generation of Sentinel-3 will provide continuity and, all being well, up to 200 bands of multispectral observations at 300 meters globally. This is what we hear from you. This is what you need to do biology in the ocean, to make the green ocean work, to make the white ocean work with the green ocean, and to bring it all together with the blue ocean. And never forget, it's the ocean at depth that you bring that is quite unique. And we need you, and I think you need us. So we have a very, very rosy future ahead of us.
Thank you. Thank you very much, Craig. So, well, thank you for both for the comprehensive overview. It looks that the evolution in space component are going in the direction of what also the service is going, with higher resolution and much more data. We will have different frequencies and much more observation. So now it's up to us, as you told, to make the best out of this data for the interior of the ocean. And I think we move now from space again. We go in the interior of the ocean. I leave Pierre.
Yes, I will just introduce and ask the first question to Inga on this in-situ observing system. Craig mentioned this, explained this observation of the ocean interior, the deep ocean. So Copernicus Marine has a high dependency on the in-situ observing system just to observe the interior and then to constrain our model. Satellite plus model is not sufficient to monitor and forecast the deep ocean, and this was well explained today in the different presentation. Still, we know that the in-situ observing system is fragile, and there are many issues and gaps. So we need to work together. To improve it, because this is identified today as a risk, possibly a high risk for the Copernicus Marine on its long-term evolution. So the first question I would like to ask you, Inga, as a Secretary General of EuroGOOS, but also actively involved in the European Ocean Observing System initiative, is what do you see today as the main gaps that we have for the in-situ observing system?
Okay, thank you very much. Does it work? So it seems that we all need to use the same microphone. Good that we are out of pandemic. Okay, I would also like to thank for this invitation, because I really need to mention that for EuroGOOS community and Copernicus community, I think there is no difference. So we are one community all, and we have been working since the beginning of the days. And of course, there are a lot of gaps and a lot of challenges in our work, what we do. And if we talk about the gaps, I think we have to bear in mind that the gaps can be very different. One part of the gap is that, we might miss observations in the deep, as was mentioned by different panelists, but also not only in the deep ocean, but also in remote and hard to reach regions like the polar regions. We also have technology gaps. So even the technologies are advancing quite a lot during the last decades. We are still struggling in observations under ice or in deep waters, so we are developing the deep Argos further. And we also have, let's say, sustainability and resource gaps. So there are different types of gaps, but I don't want to stay in a very negative side, because I think that we have to be positive. And if we have a gap or a challenge, that also means that that pushes us towards innovation, and it also pushes us towards finding solutions. And as being also representing here today the European Ocean Observing System, EOOS, I would maybe like to take two words from our implementation plan, which I would like to elaborate a little bit further to show you what kind of solutions we might have to overcome the different challenges we have. So, and those words would be the visibility and communication. We have heard in different panels and in different presentations that we need to collaborate better, and we need to, do things together. But if to take the word visibility, then I would say that it's really difficult to improve something that you do not have full picture of. And it's also very difficult to collaborate if you do not know what the others are doing. And what I mean by that is that in the next 5 years in the EU's strategy implementation, we are aiming to facilitate further the development of the monitoring of performance of our assets, so that monitoring of our capabilities, because what we can see in many places are the static maps of assets that are in the water, but we often lack the information about how many days these assets have been taking measurements, how often they are deployed. We can just count the numbers from that particular part, but the question is always that even we can count the assets that we have in the water, not all the assets are delivering the data. So there are different types of gaps and challenges we need to overcome. So we need to be able to monitor our capabilities better. And if to talk about that, we need to know what others are doing, is that we really need a pan-European platform or a tool where we can all report our ocean observation plans, meaning that we make our plans available to everyone so that we can more efficiently use the resources that we have. Like I mentioned in the beginning, one of the gaps is also resources. And it doesn't only mean the financial resources, but it also means the human resources. And I think that nowadays the human resource is quite limited already, because the advancements of technology, it doesn't mean that if you have the autonomous devices, you don't need the humans anymore. So those devices do not work without us and without observing community. So there are different aspects. If to talk, can I continue? I can talk until the evening. If to also talk about the gaps, then very often we do not have observation gaps, but like I said, that we do not have access to data. So there are different projects that we are using to get better access to data, but also we need to think about better incentives for the data providers, so that we really need to better implement the credit system for the data providers, so that they are acknowledged for the work that they are doing. And last thing I would like to maybe emphasize here, that ocean observation is not just for the observing community, it's not just for us. It's a shared responsibility of the entire society. And we need to engage better the private sector and the public. And as a very positive note, which I will end my intervention, I would like to give you an example that currently many of you probably are also following. There is an ocean race going on, started last year, and currently they are in Aarhus. Then the next leg will end in Hague, and eventually by the end of June they will reach to Genoa, to the final destination. And there are 5 IMOCA sailing boats who sailed around the world, and all of those boats carried some measurement or sampling devices on board, so that they made observations, they collected samples, all those data will be delivered afterwards to the Emodnet database. And they also deployed Argo floats, weather buoys to the Southern Ocean. So this is a shared responsibility that we have to take advantage of.
Okay, so I think we have a little bit of time for the last question for Craig and Lieven, but it's about a subject which is actually growing interest for the space data users. So the emergence of the private space industry, which I think many of you may be heard as new space, is becoming more and more common, spanning areas that goes from the private launch of a launch system to small satellite constellation, or even suborbital tourism. So this space tech support the client to, let's say, to reinvent the traditional space industry supply chain. So I would like to hear from you, how do you see the future role of as contributing mission of the new space in complement or versus the Sentinel, the classic or the Sentinel mission that you are planning? So,
okay, I'll start. So what we call new space is this idea that we can bring the private sector in, and we have some very successful examples of that in Europe, ISI, for example, with very cutting-edge SAR technologies. In the context of Copernicus, we have to think very carefully about how such activities are sustained in an operational manner. How would small satellites be replenished in due time to ensure that we have the capability maintained, but also the quality of the observations? That also needs to be important. I mentioned earlier that if we're to provide evidence-based observations, they need to be of a very high standard. And I understand what you said about sailing boats making good measurements at sea. That's great, but I want to see the quality of those. One measurement can ruin a whole series of measurements if not treated accordingly. So the concept of fiducial reference measurements is very, very important in establishing good baselines. But new space can bring dynamism. It can bring solutions where the larger spacecraft, for example, the next generation gravity missions, which are fundamental to what we do in altimetry and also Earth's mass balance. Here, that's probably not one example where new space would make a grand contribution, but leveraging that information is very important, and here new solutions could be found. We had mentioned earlier the Harmony mission, which is a passive SAR listener satellite, which will work together with Sentinel-1. What can we do about altimetry and ocean waves? We need more altimeters or solutions such as the CFOSAT follow-on to make sure we have an ocean wave spectral capability that we've now learned to live with the CFOSAT mission, but where's the future? What about densification of altimeters? Can we get small satellites to do that? And we see examples of that emerging in the new space environment. So I think horses for courses. There is clearly a niche, and where the European Space Agency's member states wish to move in that direction, of course, we will assist. That's our job. And I think there is a great space for complementing the workhorse sustained Copernicus operational capability with small satellites that bring high resolution, specific measurements of very good quality.
Well, similar for me, indeed. I mean, I don't see new space versus Sentinels. I think that's the key message. New space can be a great way to fill some data gaps and to make sure that we have data where we are not able to get it with our Sentinels. And I believe at EUMETSAT we have also some experience with that, but not in the marine environment, but mostly on the radio occultation, where some time ago, a couple of years ago, we decided indeed to procure, to buy some of the radio occultation data on the commercial market, which has been proven very useful as well in order, because the quantity of data basically fed into the different models and really added something extra. Now, for Copernicus, I'm not really sure if it's a good analogy, but I see more the Sentinels as lighthouses, and I think the you can question the analogy indeed, but it is a reference mission. There can be reference missions, and just the example of Sentinel-6. Sentinel-6 is really the mission against which all of the other altimeters are calibrated against, and that's absolutely crucial. So the two aspects that come back, what also Craig mentioned, is first of all on the quality. The quality is amazingly important, because that is basically giving you the value also in your models, in your products and so on. It's an absolutely critical part that we can guarantee through the major investments that we do with, or that is done with the Sentinels. And the second aspect is as well is continuity, so the long-term availability. And that makes, both of those makes a reference mission, I believe, which I think can perfectly coexist with new space initiatives. Not really sure in the marine environment, at least for the areas that we are active in, so more global type of sea surface temperature, Sentinel-3, Sentinel-6 alike measurements. that there are many upcoming missions, but I really see them potentially in synergy.
Thank you, Lieven. So, thanks to all. I will maybe leave Pierre-Yves to draw some conclusion of the session.
Yes, thank you. So we are just at the end of this roundtable. First, I want to thank Inga, Craig, and Lieven for your intervention on the excellent messages that you convey through this roundtable. And I want also to re-emphasize that at the level of Mercator Ocean, and together with all Copernicus partners, we are really committed to support first the European Commission for the design and providing all these user requirements for the future Sentinel mission. And of course, working very closely with ESA and EUMETSAT to ensure the uptake of the expansion missions that will come at the end of this MFF, and also to prepare the new generation. This is really extremely important to us, and to have this regular dialogue with the space agency, because we also know that it's often in the details of the implementation and development of those missions that will matter the impact on the services that we provide. In-situ is also a big concern to us, so we are very committed also to work in the framework of the EOOS together with EuroGOOS, also with the support of the European Environment Agency, which is in charge of the Copernicus in-situ coordination. We also know that many of the challenges that you mentioned, Inga, they have to be addressed at international level, so we expect also a lot of all the new initiatives as part of the UN Decade of Ocean Science, and we also will make our best to contribute to all this discussion, because we really have a clear concern for the in-situ. Just also to remind that as part of the activities that we have with all our production centers, I mean, that we were presented today, I mean, it's actually mandatory to them to assess the impact of the observing system on the quality of the products they deliver. So this is something that we manage as part of the Copernicus Marine. We'll continue to do so. Together with Antonio, we will, on all the partners, we will organize workshops this year to refine the requirements we have for the in-situ observing system and for the satellite, including the new generation of Sentinel mission. We also participate to the different MAG. So this is clearly a very important activity for us, because we really want to make sure that all this very nice evolution we'll have in the observing system, in particular for satellite, will feed the service that we deliver. So it's quite important to us. It was so good to have you, three of you today for this short discussion, but quite useful actually. So thank you. And it's time, I think, to go to lunch.
Thanks to all. And I think this takes us to the end of the morning session. So we convene here again at 2:30 with the next session. Thank you very much.
So let's start. So thank you, everyone. So thank you for joining this Marine Data Store and User Service Achievements session. So I am Renaud Dusurget. I'm Head of Operational Engineering at Mercator. And I will today make a talk about the Marine Data Store and User Service Achievements. So this session will be split in two presentations. So the first one will be done by myself about the Marine Data Store, and the second one on the users, tools, and user service. That will be presented by Laia Romero from Lobelia Earth. So we'll try to save time for one or two questions at the end. And in case you had any question online for the people attending online, so please come back to us after the event, so we will be pleased to answer your questions. So I will be starting my presentation on operating and modernizing our Marine Data Store. So I will start with the current status on the Marine Data Store. So as you may know, the system is currently composed of two main components since early 2022. The first one is the dissemination unit, which is the core component of the current operational system. And we had on this component 4 service releases over last year, plus technical updates, mainly focused on the infrastructure side and the security layer. On top of that, we've added AirDAP and OpenDAP technical interfaces, plus retired some legacy interfaces. And in November 2022, we had quite a challenging service release with about 70% of the catalog that was fully renewed, and quite a significant increase in terms of data volumetry on our data store. But still, the EOOS system proved to be stable and was able to produce operationally for the vast majority of products and datasets. Second component is the data replication and access service that is granting Wikio with a direct and tailored access to Copernicus Marine data. And early 2022, we started with the replication of data on the Wikio infrastructure and deployed an opened-up server there. And by second quarter, the service was fully operational and fully implemented and connected on Wikio side by the end of 2022. So that's the status for the operation. So now we are moving to the more interesting part and challenging part of our current work. And we are basically, maybe we should move to the next slide, which is, yes, but it's showing the right slide on my screen, but not on the one. Okay, thanks. So, okay. I'm trying, there's a lag between both screens. Sorry for the technical issue. I'm trying to move. Go to next slide, please. Yes. No, the one before. Okay, sorry for the issue. So where are we today? We are completely renewing our marine data store, and we're moving towards a fully new system that will be more scalable, interoperable, and with improved user experience. And we already started with preliminary developments to improve the current system, and having a novel marine data lake that has been delivered by end of last year for the first version. And we've been working on the optimization of the storage layer and data formatting and packaging, basically. And now we have moved towards developing a demonstrator of a fully rebranded backend system for Copernicus Marine data. And we are basically focusing on renewing the whole software stack and rethinking the whole infrastructure design. So what are our primary objectives? So first, we want to do the same, but in better, with better technologies, more modern technologies. And aside of that, we are waiting for higher resolution data sets and even ensemble data sets that could possibly reach the petabyte size. And on top of that, we also want to add cloud computing capacity. And having this system ready, fully ready to answer the request for a future digital twin of the ocean. Our objective is to move the system into production by the end of this year and implementing new functionalities over the next 2 years. So where did our journey begin? Actually, everything began in 2020, when we were envisioning the future digital twin of the ocean and trying to identify which were the key concepts and the key technologies to be deployed in this context, so that for the start of Copernicus 2 phase in 2022, while we were continuing the service, we were redesigning a fully new prototype. And once the Wikio was fully connected to Copernicus Marine data, we start completely overhauling the system and having a completely new system. And today, this system is under final qualification. And we have serverless access to the data through the Marine Data Lake. And we are looking forward entering into service in the coming months. So a few things about the consortium who has been working on implementing that new Marine Data Store demonstrator. So the consortium is made of 3 members. First, Lobelia Earth, which is the technical lead and responsible for the redesign of the core data and software environment. Then we have Acri ST, that is responsible for the syncing of data from the dissemination unit to the new Marine Data Lake, plus developing a data approximate computing platform, and having Cloudflare as a cloud provider, a cloud infrastructure provider. 2 milestones. So we've kicked off this project in early October 2022. And by mid-February, over our annual review, one of the key services, the main service of the new system, was already in preparation mode. So just a few things about how the system is actually shaped. So today, we have the data that is being pushed by the production centers, and that is being delivered to the dissemination unit, and Copernicus Marine users the Copernicus Marine users can access the data from the dissemination unit technical interfaces. From there, from the dissemination unit, the data is being synced to the Marine Data Store, and the data flowing into the Marine Data Lake. And all the services are built around this Marine Data Lake so that users from Wikio can connect indirectly to these technical interfaces through the Wikio environment. And Copernicus Marine users may access proportional versions of these new Marine Data Store services directly from the demonstrator. So just a few, two plots in order to highlight how high was the availability and how low was the latency for accessing the data within the Marine Data Lake over the past 2 months. So this is quite performant. So I will start going to the main features that have been developed actually. So one of the first features is the serverless access to native data. Basically, this is a cloud-based drive for accessing the Copernicus Marine data, and basically the original files that are produced from the production centers. And from so the same file that you could actually get if you today go to the Marine Copernicus FTP that is hosted on the dissemination unit. So since February 2023, the consortium achieved the full coverage of the Copernicus Marine catalog. So all the data from Copernicus Marine is there already. And we believe this will clearly improve the user experience on accessing the data through, for instance, as an illustration on the right, a way to browse online the files that are actually in the system. So this is a prototype of what could be implemented in the future data portal. And there comes really the core of the innovation in this project. This is the serverless access to Argo data. So Argo means that the data is basically ready for being ingested into modern data analytic frameworks, and the data is being optimized for making the most of the cloud infrastructure and the underlying power. So to achieve that, we rely on two main technologies that are the OGC-ZAR file format that delivers Copernicus Marine data packaged in 2 ways so that it can optimize the response time for data access requests. And aside of it, we have the stack metadata catalog, which will improve the way that all information and metadata associated to the ZAR files will be used by all the technical components from the Copernicus service and can be programmatically accessed to deploy better data access pipelines. So since the last months, actually, the team, the Marine Data Store team, actually reached the 80% coverage for Argo data. And it actually includes model data, satellite data, as well as in-situ data, and other specific data sets, such as ocean marine indicators, or static data sets, such as this global bathymetry from the global forecasting system on the right side. And now the team is focusing more on the remaining Arctic products and sparse data sets such as in-situ data and along-track data such as along-track satellite altimetry, for instance. So there are a few other services that are coming as well as with this Marine Data Store demonstrator. Among those, first there's the WMTS ONZAR service, which is already under pre-production, and which we believe will improve pretty much the performance and the interoperability with JS tools or data visualization frameworks. And then the consortium also did the clear demonstration that they were able to develop and deploy a data proximate computing platform on which basically a user can connect and with a minimum of 0 configuration can run its own data processing flows, so it can process data with an unprecedented performance. There, the users will be helped by getting template notebooks and predefined workflows that it could adapt to fulfill its need and get advantage of this very interesting and performant feature. And then finally, we have been working also on the monitoring and reporting service, specifically focusing on the system health for sure, but on the data usage monitoring and basically how to monitor which bits of data were actually downloaded and how they were used by all the users getting access to this new marine data source. So it really gives us a really detailed vision of how the data is being used. So for the next steps, the team is really trying to reach the highest possible coverage for serverless Argo data, ideally going to the full coverage target. And they've spent quite a time on intensively testing the performances of the system as well as its cloud agnosticity, so it can be deployed in a totally independent infrastructure, so its ability to be deployed in an independent infrastructure. Then we'll be starting supporting the users with getting access to these new interfaces and as well as taking advantages of these new services. And for instance, going through deeper integration with the data web portal at first, and also with the development of a fully new Copernicus Marine Data Access client library that will help the users to browse and access the data from command line interface or directly from their scripts. So, conclusion, as you could imagine, the last period was really dense and exciting. We were faced with many technical and organizational challenges, and we are quite happy that today the service was up and running for the whole year, and we have a brand new system that is already on the shelf and ready for being deployed in operations by the end of the year. And now it's really the time to set a new scene for the Copernicus Marine Data for the next years and tackle the new challenges that will come with the DTO and other advanced applications in the future. So we could be shipping the users with new features and improved experience. And I'm pretty sure that Laya's presentation just after that will give you a good glimpse of what can be already achieved and what is in the developer bags for the coming months. So thanks for listening to me, and I will leave the floor to Laya.
Okay, thank you. So yeah, my name is Laya. Thank you, Renaud, for the introduction. I will be talking, let me see if I can do this. Okay. I will be talking about the MyOcean Data Portal, a little bit on the past, the recent past, the present and the future evolutions that are planned. The MyOcean Data Portal being the web portal, but specifically the viewer and the catalog. And so as you know, in the last couple years, we started in actually 2020 with a small prototype of a viewer that allows graphs and data explorations, like making graphs and animations of the entire catalog, that has different projections, That includes an integrated service desk and an integrated catalog. And that, well, that I think that it became an important improvement in terms of data exploration visually of the CMEMS catalog. And last year, the last release included a standalone catalog that was also integrated seamlessly with the viewer. Here you can see how the subset and the download was also deployed in the viewer. You can discover products and so on and so forth. Let me see. Can I go to the next slide? Or I will. Okay. Okay. So right now, we're working on 3 main evolutions of this viewer and the catalog and the data portal. And this is a roadmap that has been put together in order to make use of this optimized data that Renaud was explaining in his presentation. And these 3 main evolutions are on the improved data experience. On the in-situ exploration and on the dashboards. So for the improved data experience, what you will see, and this is in order, in chronological order, the first things as users that we will be able to see is that we will be able to make time series not only on a point, but also on a line or on any given polygon on the map at full resolution of the data, like true full resolution, even for the high resolution large data sets, and also maps in an instantaneous way. So the performance will be greatly improved for the data exploration. Also, there will be zoom-dependent overviews so that we get more information as we zoom in as users, and different implementation improvements that will be also ease the user experience. Then the in-situ exploration, and this is very important, I know, for a lot of us here. So in the next future, we will be able finally to see the whole CMEMS catalog in the viewer, including all the in-situ data, to be able to compare the observations and the model data as overlays in the same space, and also to click and get the time series and the profiles as graphs of the in-situ data. And then the last thing are the dashboards. We're working on the development of dashboards so that a user, being a journalist, a scientist, a decision-making, any user, can create their own dashboard from different cards under their user account. And this dashboard that can be made with numerical values or a region of interest, or different regions of interest, or the state of the ocean for a given time, can be checked by them in their user account whenever they need to. This is the further evolution in the chronological order. So we will need to wait a little bit more for this. And then I want to make a point on the current catalog. My colleague Guillermo Grau, who's been working a lot on the development of all these fantastic tools and visualizations, will be doing a demo. The current catalog as it is now, and this is maybe a detail in the user experience, but it's an important detail about the philosophy of the user experience. So the current catalog now includes many different styles, has technical issues because some images are blurred, some images have no data or no image available, some are identical, so it's very difficult for a user to actually browse the catalog and from the thumbnails get an impression or look for the data that they're willing to find. Because not all users know as much as people here know about the CMEMS catalog. And so we've developed a way to display catalog thumbnails that follow a certain convention that we're still discussing, and I will explain the convention. So the goal was to have a catalog that includes thumbnails that are distinguishable, but that are consistent enough. so that it looks professional and very solid and mature and operational, and that a user can actually learn a code for browsing the catalog dataset that is based on what I will say now, but that it makes it easy to learn. So there are 5 different visual elements that we are following. There's a little tool that we developed to create these thumbnails, and those elements are every thumbnail for each of the datasets shows what you get. This is the basic, no? So global, it will be a global dataset, Arctic an Arctic dataset, and so on. Number 2 is the base map. All of the near real time and the forecasts will be on a dark base map in the thumbnail, while the multi-year will be on a light base map, and the in-situs on a bathymetry baseline. And then there's other details like the ocean color that accounts for a lot of data sets that has like a slightly different color on the ocean. Then the color map. So for the thumbnails, the variables will be associated to a given color map. So here you have the physics, the biochemistry, the ice, the wind, the waves, the currents. And this will be also consistent through the catalog. And then the data gaps, whether there are gaps for certain data levels or there are no gaps for other data levels. And finally, the tags. We have implemented and hopefully we don't go, oh. I see them okay, but no, sorry. This is the color maps. And this is the data gaps for the different levels of data. And then the tags, that hopefully we will not go overboard with the tags, which is a little, I mean, it can happen, it's a challenge. The tags are to differentiate between products that may look very similar on the thumbnail. So here, an ensemble that is low resolution versus the ensemble. That could be a good use of the tags, or here to group products together when the thumbnails are different, but we want to actually express that all of those thumbnails belong to the same type of product, in this case, the SST. And this is it. So this is a very brief example of the current status of the user tools and services. And now Guillermo will do a demonstration, which is a video to avoid problems.
Thank you. Thank you, Laia. Okay, so I'm going to present the end-to-end user experience of the upcoming version 9 of my Ocean Data Portal. This, just a small disclaimer, this is under review right now. It will come early July. So there might be some small changes in the meantime, but we wanted to share it with you, taking the occasion. So how does this work? Okay, so this is the main catalog of the portal that many users start their visit on. You may have seen that it is divided in multiple sections horizontally, with the most popular products at the top, then some of the products that you have already viewed, some thematic sections, blue, white, green, ocean, a lot of different sections, and inside each one there are multiple products, and you can scroll horizontally to find the ones that you need. So as Laia was explaining before, we have created a new design for the thumbnails that is more consistent and at the same time relates better to the data inside the product. And let's zoom into 2 examples and see if we can interpret the thumbnail correctly. So this, for example, covers the Baltic Sea, that is evident. It has a dark base map, so it is a near real-time product. It is green, so it must contain some biogeochemistry data. So up to here, it's simple enough. Let's have a look at a second example. This one is for the Mediterranean Sea. The base map is light, so it is a multi-year product or a long time series. And the color map and this small tag indicate that it is an SST product. It also has gaps, so it is a level 3 product rather than level 4. There are some parts of it that are missing. So we believe that these visual elements are really not very complex to learn, and they will help a lot new users when they visit Copernicus Marine for the first time. So let's say that we are interested in some particular variable, for example, salinity. We can use the filters at the left-hand side to narrow down the catalog and look for the products that contain this variable. So we get a lot of physics products with different domains, all more or less in the same color map, because they are somehow related. We are interested in the NRT product, so we choose this one. And this brings up the new add layer functionality of version 9, which directly suggests the layers that contain the variable we're interested in different time resolutions. If we still don't find what we're looking for, we still have access to the previous user experience at the bottom, in which we can navigate all the data sets and all the variables, but this, of course, requires some more advanced knowledge. So for initial use for new users, it's much simpler to use the new approach. So if we go back up, let's say we want the daily salinity. So we click on Add to Map, and there it goes, it is on the map. So the nice thing of the new version is that we are using the ZAR data cubes already. So it is very performant and very fast to explore data moving in time and in depth. We can either use the sliders at the bottom and on the right, or the arrow keys in the keyboard to move step by step. But you'll notice the new performance. And one thing that thousands of users do every week is just to click on the map, because they are interested in time series, depth profiles, and other kinds of plots. Or they use the geometry tools to draw lines and areas to get other types of plots and insights on the data. So this, for example, would get, if you define an area, you get a histogram of the values inside that area of interest. A new feature of version 9 is the ability to change the base maps. Now we have dark, light, and the bathymetry one. The bathymetry one uses the JEPCO data, and also a digital elevation model. So it is simple to adapt to your personal needs. And of course, we've had maps since the beginning, since version 1, but now maps are much more performant because we are accessing the data directly and not relying on intermediate services like WMS that might be slow today because there is a lot of traffic, a lot of demand. Another new feature is that we have support for static variables like the bathymetry or the MDT. We just add them to the map as normal. And the same applies to ocean monitoring indicators. If we go to the catalog, so a second. If we go to the catalog, we can filter by OMIs. And all 95 of them are here, and for those that have geographic dimensions, they can now be visualized just as any other variable. In the following versions, we will also add support for time series OMIs and also the capability of exploring the actual data in those OMIs. Okay, and finally, subset and download. This is a functionality that is very, very much in use. The way that you use it, this is an alternative way that maybe you have not discovered. You can draw first the polygon and then link the polygon to the subset form just by hovering on it. Then if you tweak the form of the polygon, then the bounding box adapts. Then you just choose the date range you want, click on download, and after a few seconds you get the data. So this is more or less the end-to-end user experience from the catalog to the download of version 9, coming out early July. And if you get your hands on it and use it, please send us your feedback. We will be listening. So, thank you.
So thank you, Guillermo and Laia, for this very nice presentation. I think it's really impressive to see how much interactivity you could get on this volume of data. So now we still have a few minutes for 1 or 2 questions. So if anyone has a question, please raise your hand and we'll be pleased to answer. Okay, so I have 2 questions from Dominique and Vittorio on my right side. So Dominique, let's go first, and Vittorio will follow. Is there?
Yes, I wanted just to know when you go from the visualization to the download, at which point do you need the user to register to enter his account? Because you said that then you have a direct link between the catalog, the visualization, and the download. So when do you need? When does the user need to register to have the data, to get the data? When you click on download, then you need to register. Okay.
Something else. One perhaps is something that would it be possible to add a chance to select dates without having to scroll? Because in this moment, to have a given date, you just have to find it by clicking and then scrolling, which frankly, it's a pain.
Okay.
So it's very simple. I know it's fancy, but it's hopeless. Like if I want the 12th of September of 2005, I have to hover, find it, then click it, and it takes forever.
Okay, we know.
Yeah, no, so perhaps I'm the only one that has this problem, but I find it hopeless.
It's on the roadmap, and we take a note, because actually, one of the most difficult things of these tools are to represent a very wide variety of users. And that's always been the driver. But
I understand.
I agree, and it's on the roadmap.
Thank you.
You have too much data. Maybe a last question over there.
I have a question. How you just mentioned the description of the data set. Actually, you want to be common. I mean, to become not diverse. Since every data is different, actually, also we want to highlight the specialty, let's say, of each data set. How do you design all the description? You will talk with the data producers, or you think that from your experiences is better in this way instead of that way? Do you do the user survey for this kind of design? Thank you.
In this case, in the particular case of the thumbnail, we didn't do a user survey, but we are working more and more, also CMEMS and in Wikio, and on user surveys, and actually with dedicated people that are looking at the experience from a completely agnostic angle that has nothing to do with the thematic. And actually, it's a very good point, because we, and I think everybody learns a lot from that. I agree, and I think everybody agrees that you want the things not to be too consistent. Too consistent is not good. But also there is a compromise. And we define these conventions, and we are discussing them with Mercator and with more people. And that's how it goes so far.
Because definitely everybody wants their data to be, visible, more usable. We have been thinking maybe when data is not used by users can be, maybe we didn't give the description of the data set precisely. I mean, that's, for example, if just you're thinking that our example of the reanalysis, for example, we produce ensembles just because we can produce uncertainty information. In that case, we want to highlight this information instead of just tell them, this is global reanalysis, instead of how to say, satellite data. So very specific information, I think is important for the producer to add instead of, very common names.
Completely agreed. And this is why we actually have the visual elements and then the tags. So if there is something that needs to be highlighted, it can be done in different ways. But also, I think that Laurent and Arnaud and the team has also a lot of feedback on this.
Yeah, for sure. Maybe just to before Laurence, I think it's really important that every expert on the data can provide their feedbacks to these new tools actually in order to improve what's actually being what has to be shown to the users in first. So any feedback is really welcome. So we encourage you to play with the interfaces and to come back to us. To Mercator and to Lobelia to try to improve the way we are describing the data sets in the catalogs. And so, Laurence.
So yeah, to complement, there is a setup process in order to collect the feedback. So once this new version is going to be online, the existing process is going to apply to this new viewer, meaning that we are going to be collecting your feedback, but also the feedbacks from all the users. So this is the work which is being done by the team from Corinne, and Valentina is here to centralize all the user feedback. So this is really a process that we have and that we are going to apply to this, and which we apply to all the things we are doing. Coming back to highlighting one product regarding all the other ones, I think it's a good thing that we make the catalog something homogeneous, although we know that each product is unique. So it is also, there is some other communication media that we really need to organize better to highlight better one product that you think is unique. So please do contact us if you think that we need to highlight better one of your product. It's not necessarily in the catalog that we are going to do that, but we have other communication channels where we can do we can do articles and so on. And again, this is the team from Gratian. I don't know Gratian if you are here, but it's Corinne and Gratian and Cedric
in the back
who are going to do that. Okay.
Okay. Thanks. I think we are 10 minutes late, so we will move to the next session, the poster session, I think. So thanks for listening, and in case you had any further questions, we'll be there for answering your feedbacks and questions. Thank you very much.
We are together again for the last session of this General Assembly. So it's going to be a 2-hour session, which is going to be split in 2 sessions. The first hour is going to be dedicated to user presentation. I'm going to start with an overview of how we are serving the European policies and the user needs. And then we are going to have 5-10 minutes presentation from users of the Copernicus Marine Service data. And then I will invite, together with my colleague Angélique Mellet, we will have together a roundtable in order to talk about how we are developing a user-driven service from user needs up to service evolution. So let's start with this first overview, serving European policies and user needs. So I will quickly talk about the Copernicus user uptake landscape, how the Copernicus Marine Service is driven by the user needs, and how we are serving European policies, and also, of course, all the other user communities. So first, a few words about the Copernicus user uptake landscape. So this is an old slide, actually, from 2021, but which is basically showcasing the landscape, the Copernicus landscape of all the Copernicus user uptake activities. And this is showcasing that all the user uptake activities which are conducted at Copernicus Marine level, they are not the only ones. There are many, many other initiatives and many other actors which are trying to trigger uptake from the Copernicus data. So there is DGDFIS first, which is having a lot of activities with thematic workshops, with the Copernicus User Forum, with the FPICUP with the member states. There is also the Copernicus Academy, the Copernicus Relays, which are really developing actions in order to develop the uptake of the Copernicus data at large. Of course, there is the Copernicus services and the interested entities, and Mercator Ocean and the Copernicus service is one of them. There is also USPA and Cassini, which are two new actors in the uptake of the Copernicus data, which are developing the uptake from the commercial sectors. And there is the KCEO on the left-hand side, which is the Knowledge Center for Earth Observation, which is really gathering the needs in terms of Copernicus data in order to answer policies and environmental policies. So it's KCEO Knowledge Center for Earth Observation is interviewing all the DGs, all the ministries, in order to gather their needs on Earth for Earth observation in order to answer the policies. So you can see that the activity I'm going to be showcasing today are not the only ones. There is a much wider ecosystem. So you can also see that the platform which are distributing the Copernicus Marine data are very numerous. There is, of course, the Copernicus Marine Service web portal, but there are also many others, such as the Copernicus Wikio. There is a new platform which is developed by DGDFIS together with ESA, which is the Copernicus Data Space Ecosystem, which is embedding all the former called DIASIS platforms. In the future, we might have the digital twin of the ocean and the editor that is going to be distributing as well the Copernicus Marine Service data. We saw yesterday that we are launching the Copernicus Coastal Hub, which also has within its catalog some of the Copernicus Marine data. We will be launching the Arctic Hub very soon in the fall. And ECMWF will very soon be launching two other hubs for energy and for health. And there might be other hubs in the future, as Muriel showed yesterday. So you can see that there are many, many platforms where you can find Copernicus Marine data. So how do we make sure that we satisfy our users and we make sure we understand the need of our users, and how do we make sure that the Copernicus Marine Service web portal stay the reference for users who would like to use marine data? So the key things is to get to know our users better so that we can serve them better. And if we make sure they have the best services on the Copernicus Marine Service platform, we are going to be sure that they will be coming to this platform and not to another one. So knowing our user better is the key. We call that ocean intelligence, and we are really developing this ocean intelligence and this ocean user intelligence at Mercator Ocean and within the Copernicus Marine Service. It means knowing how many users are using this kind of data, how many users are using the viewer, how are they using it, what do they prefer, what they do not like, and so on. And we are also committed to meet with the users, understand how they are developing their own services to change the way we provide them our services. So in order to better know our users, we need to drive the service by the needs. And this is the process I was referring to earlier this morning. We have a user-driven service where we are collecting and centralizing all the user requirements. So we have many activities. including training, attending events, organizing events, participating to events, hackathons. We have the user support activities, which is also interacting with the users. We have questionnaires and surveys. We have interaction with the DGs, with the ministries. We have the Champion User Advisory Group. We have the Marine Forum, which we talked about yesterday as well. And we have you, the producers, that are also in contact with some of those users. So we do collect all the feedback that you provide us, and all those communities are providing us into a centralized database. All those feedback, they are being collected and analyzed, and we discuss internally together with Angelique, and this will be part of the discussion we are going to have later on in the roundtable, but we really try to make sure that what the users is asking is going to be fed into the evolution of the coming years. So this is also summarized in the infographic that you see. You have the Copernicus Marine offer, which is providing with data, but also with services such as the viewer, the download protocols, and so on, and all the documentation, all the quality documents, the product user manual, and so on. They are part of the offer. So this is the offer we provide to our users. And then we, in many ways, we interact with those users to collect the feedback so that this is fed into the new science which is being developed and into the new services which are being developed, including the viewer, for example. So all the new versions of the viewer that were showcased earlier on, they are being fed by user feedback. So, and the two Champion User Advisory Group that we have are really key to do that. So we have two Champion User Group, one for the Copernicus Marine and one for the Copernicus Wikio. They gather 20% on the one hand and about 15% on the other hand, and they are meeting regularly in order to talk about new products, new services. They're also talking about product quality, and it is very important to have all this interaction on a yearly basis in order to feed the evolution of the Copernicus Marine. So this is the kind of synthesis which is being made internally, which is gathering and synthesizing some of the feedback that we have. Here in the case of products, new products or updated products, there is need for higher resolution, but there is a need for updated biogeochemical data or new in-situ data and so on. So this is just an example. So now let's see how we are trying to serve better the European policy. So we really need to strengthen our policy-driven services. So for this, we have set up the Marine Forum group that we talked about yesterday, but we also have regular meetings with regional sea convention, so meaning the HALCOM for the Baltic, the OSPAR for the Atlantic, the UNEP map for the Med Sea, the Black Sea Convention for the Black Sea, and I'm forgetting one, the HALCOM maybe for the Baltic, which I forgot, maybe I mentioned it. We also have the National Collaboration Program, which we talked about yesterday. We are also further developing our support to international initiatives like the UN Decade 2030, for example, and we are also collaborating with different groups such as the European Investment Bank, the FPCUP, which is a Copernicus initiative together with member states in order to develop the Copernicus update. We also develop different instruments, which we talked about this week already yesterday. So the thematic hub are one of the instruments to strengthen these services. The evolution of the way we display the catalog and the viewer is another one of them, and we talked about just earlier. the development of dashboards, which was displayed also earlier, and new APIs and tools that we would like to develop in the future. I'm a bit repeating myself here, but we need to better listen to the needs from the policymakers. So the Marine Forum is one of the groups to do that. The Champion Advisory Group is another one, together with the Scientific and Technical Advisory Committee, to make sure that things are feasible on the short term and on the longer run as well. And the link with the Knowledge Center of Earth Observation is also key. So, and now at large, how we are serving all the user communities. So we talked about yesterday developing training and capacity building, but we are also developing a lot of e-learning materials, which includes, for example, Jupyter notebooks, and a lot of video tutorial for GIS, and plenty of other tools through tutorials and videos. So we have the webinars and the training workshop. We are also much more and more involved into MOOC, massive online open courses, and hackathons. So we are not only participating to, as we were doing in the past, but now organizing our own hackathons, which takes a lot of organization to do so. So we have invested quite a lot of energy in that. And of course, we are collaborating with USPA and all the other uptake initiatives. Of course, the user support is key in order to liaise with the users. And we have developed a help center which is gathering so far 130 articles, but which are really key for the users, because this allows for 96% of the users to find the answer themselves to their question. So they are really independent. They go to the help center, they ask their question, and 96% of them find the answer to their question, which leave the 4% of them which are liaising with the user support and have an extremely expert answer to the 4% of the remaining question. So user support and the help center and all the tools which have been developed with the chatbot and the help center, they are really key for the user support and for the user satisfaction, which is 4.7 out of 5 that we saw yesterday. And this is another slide with a few comments from users that are extremely satisfied with the answer which are provided to them. Last but not least tool that we are using in order to widen data uptake and promotion of the Copernicus Marine data is ads campaign. So we have a dedicated amount of the budget, like for example, you see on the lower left, we spent less than 10,000 euros for a paid campaign on the social media in order to advertise for the launch of the Copernicus Ocean State Report. And this really allows to reach out to a lot of new people that don't know about the Copernicus Marine Service, that don't know about the Ocean State Report. And through the social media, through Instagram, through Twitter, they get to know us. And for this, we are using the paid ad campaigns. So either for the Ocean State Report, but that could be to promote for a coming event where we would like to reach out to new communities. So this is a very useful tool in order to reach out to new communities. And with this, I'm going to end here. And I would like now to invite 5 users to present their application and explain us how they are using the Copernicus Marine data. And I'm going to start with Fergal. Please, I'm going to misspell your name, so I'm going to let you spell your name and introduce yourself, and I leave you the floor.
Thank you so much.
Thank you.
Hi, my name is Fergal O'Donoghue. I'm a research scientist at IBM Research Europe in Dublin. What I want to do today really is touch on 3 points. So one is give an overview of IBM Research, give an overview of how we use Copernicus data, and give a perspective on our perspective on the industry and the technology and where we see the space going, so to speak. So to begin with, just to give a very quick overview of IBM Research, we're about 3,000 researchers distributed across, I think we're 16 locations globally at the moment. So that gives us that truly gives us worldwide collaboration. So it means I'm based in Dublin, but generally our projects are global. Our focus areas, our vertical focus areas are pretty much around AI, cloud, or hybrid cloud, which is enabling users deploy their software on any cloud, whether it's AWS, Azure, Google Cloud, etc. Semiconductors are the hardware side, and quantum computing are the future of computing, so to speak. Across that, then we have different horizontals where we use these technologies for impact. So sustainability is a core focus there. And what we do is, how do we use technology to enhance efficiencies, help users, help customers improve efficiencies, do their operations better, and naturally now, how do we help to decarbonize and progress towards net zero? So we just give 2 very quick examples here, just to give an overview of our role from a climate and sustainability perspective. So one on the left, and both of these are in the last month or so. One on the left is a recent technology that we released at our annual Think conference in Orlando at the beginning of May, which is around geospatial foundation models. So that is really our first foray into the space of using foundation AI for sustainability or for geospatial applications. So it's very much a research project at the moment. What it enables is using a single AI model to address multiple aspects related. It's geospatial, but in this context, land surface. So enabling it to address multiple tasks related to flood detection, flood prediction, wildfire detection, agricultural processes, etc. That is very much a research project, but we see very significant opportunities in that space of foundation AI across these, across many applications. The second piece is a new climate action center that has been launched in Governor's Island, which is an island in New York. It's being led by Stony Brook University and a consortium of global universities, and IBM are the technology partner there. And again, what we are aiming to do is, how do we bring together these different technology components to enable deep scientific progress and to enable the development of new technologies and capabilities to address the climate challenge. So this gives a brief overview of some of the areas that we work in Dublin related to the broad space of oceans and sustainability. So these are areas that we heavily use Copernicus data for. We've been using Copernicus data for a large number of years. It started with fish farming. Now we're using it for biodiversity estimation. We're using it for shipping, and especially for route optimizations of shipping. And how do we combine ocean data, weather data, etc., to inform around route optimization, but considering it from the multimodal perspective of water-based transport plus land-based transport, and how do we develop optimization solutions cognizant of those and cognizant of the environment, the disruptions that can take place and the disruptions that often do take place. So just to give a very brief overview, some of the products that we use, so we heavily use the reanalysis and forecast products is I would say the core product that we use within all our projects, so to speak. More of a focus in recent years, in the past 18 months especially, around sensor and observation data, especially from the perspective of biodiversity and sustainability. So if I was to give one, not growth area, but one area that we are getting a huge amount of focus now, it's those two spaces of global biodiversity framework and ocean health and restoration. How do we use technology and how do we use the data that's available to address these core challenges? How do we transition industries from a net negative on the environment to being truly restorative, positive components? So that's around fish farming, that's around nature-based solutions. So one body of work that we're doing at the moment is around engineered artificial reefs, that we're working with a partner on that. And how do we monitor the MRV aspects of engineered artificial reefs? How do we measure, report, and verify the contributions of nature-based solutions such as engineered artificial reefs, mangrove forests, etc. So it's very much a combination of biogeochemical ocean data. It's very much a combination of how do we develop these transparent, defensible metrics, and how do we do it at a global scale? So, and how do we build on learning so that it could be applied in multiple geographical regions with the complexities that entails. So I'm not going to dwell on these because really what we're focusing on here is developing the core technologies that enables this to scale and enables it to scale and transfer across multiple different locations. So route optimization is something that we've been doing for many, many years. I think the challenge that we are seeing now is how do we get a better understanding of the implications of different decisions that go beyond the purely just-in-time arrivals, or that go beyond the purely service level agreements of this, and how do we understand the implications of different decisions in terms of efficiencies and the different decisions in terms of pollution in a broad sense, or pollution in terms of acoustic noise pollution, and how do we integrate with the other systems, etc. as well. So in terms of the core areas that we see, I mean, when we talk about improvements needed, I guess there's always the easy answer of saying we need higher resolution data that is more accurate and that is available everywhere globally. Where we are seeing very significant disruption in recent years is very much around the foundation model space. And what drives a huge amount of that, or what I would say what drives the entirety of that, is the work that's been done around the open source and scientific community in that space. So really things like ChatGPT or Google Bard, etc. There's been, I guess, a confluence of three things really that has driven a lot of that disruption. So one, there is the technology or the science piece around improvements from an algorithmic perspective, such as namely the transformers architecture that came from Google in 2017. The second piece was around the pre-trained model that allows people to download a model from anywhere and use that space. And the third piece is around the ecosystem that is primarily driven by Hugging Face, which is a startup that was founded in 2016 by 3 French entrepreneurs, and that's now valued at $2 billion or euros. What that allows people to do is download the model, download generalized pre-trained models, apply them for their own use cases, applications, etc. And it has led to a huge ecosystem of innovation, etc. Since ChatGPT was released, for example, there's been over 100,000 machine new models added to the Hugging Face platform. So that's where I think there's where we'd see a huge opportunity or room for improvement here, or opportunity here, is how the services that Copernicus provides in terms of data, etc. How do we broaden the number of, how do we broaden the ecosystem around that, that is building on top of that, that is creating new models on top of that, where those models can be shared, reused by others, and where there's that continuous iteration and building on solutions. And from our perspective, the really big opportunity that we see there is around foundation models. And similarly to how we engage with language now through foundation models such as ChatGPT, how can we leverage similar technology to engage with ocean data? I don't envision foundation models as being a digital twin of the Earth, but the data that is coming from digital twin of the Earth, how do we engage with it more seamlessly, more naturally, and enable it to be accessed by anybody through these technologies and capabilities? And that's summarizes everything I wanted to say. Really appreciate the time.
Thank you very much, Fergal. I know you have to rush to catch your flight. And Fergal is a member of the Champion User Advisory Group, and is really key for us to provide us and to guide us with new feedbacks. So now I would like to invite Anna Cilio Calzada. I hope I'm not misspelling your name, who is going to talk about the remote sensing applied to aquatic ecosystems. So Anna is from IH Cantabria. So please, Anna, you're welcome. So you have the remote here.
Okay, and
this is the green button,
okay,
and the red one to go back.
Well, thank you. First of all, thank you for inviting me here to present part of the work that we do at the, okay, it's here. Part of the work that we do at EH Cantabria is the Environmental Hydraulics Institute. And even if I'm here standing for my colleagues, this is the examples that I'm going to show are basically the product of many people in the Institute. So the IH Cantabria is a public research institute that groups more than 200 people from different backgrounds, and this heterogeneity of backgrounds has allowed us to generate, for the past 15 years, more than 1,000 projects, distributed all over the world, but basically more than 60 countries, and being our activity mostly located internationally. Our goals basically are both to promote the multidisciplinarity and collaborative scientific excellence and knowledge transfer. And as part of, in order to sustain or promote the sustainable goals, development goals, right? So I'm just going to show some examples. So our market sector is multiple, but the ones that I'm going to show you here are linked to the marine spatial planning, the operational systems for prevention and management of oil and chemical spills in the marine environment, right? Port and harbor operability, the marine, as well, an operational aid system for marine works. So again, in order to help the operability within the ports, we have an interesting one that is rapid environmental assessment that is basically used by the Spanish Navy we do a bit of everything. And then the high-risk coastal flooding forecast by storm attacks. So what our users are the people that we deal with? Well, basically they are port authorities and harbor stakeholders, construction companies, the Spanish and NATO Navy, civil protection, defense. Well, we have a multiple, our array of stakeholders is quite wide. This is just an example. So basically what we do is we try to go from global to the coastal zone. So for that we need the high resolution data, and for that we use the downscaling strategies. Well, the first example that I'm going to show you is related with marine spatial planning, and it's basically focused on the development of ocean aquaculture and renewable energy opportunities. So basically, by just analyzing the habitat adequacy of different species and the type of cages that they need in order to be cultivated, and then if they can be joined by renewable energies, what we create is a co-location of opportunities. So this is an example of an atlas that we did. What it shows is, well, we focus on 7 marine fish. So we contemplate all the biological suitability, the structural suitability of the cages, as I was saying, and the operational suitability linked to the conditions of the ocean meteorology, met-ocean conditions. So the other example is, well, this is regarding the renewable energy, the location of adequate, the adequation of places where these renewable energies can be placed. So together, if we combine both of them, we can extract those locations in which you can combine both, and the impact is much less of what would be if in case of being separate. So, well, for that, we use global ocean, sea surface temperature, salinity, the wind, and it is not there, but the waves as well. Another example is related to marine pollution, and is about these integral systems for prevention and management. So starting by the data providers, I mean, you guys, with your fantastic numerical modeling, hindcast and forecast and satellite and in-situ measurements, together what we can do, and is us as intermediate users with our numerical models and statistical methods, we can provide to the end users the information that is needed in order to proceed in case of oil spill or to prevent the oil spills. So, for example, as part of this system, there's the prevention of the accidental spills. So for that, the whole system is quite simple. We take the mid-ocean forecast. We provide the suitability of the operational conditions. for loading or downloading chemical spills, chemical products or oil. And we set a warning criteria and recommend the measures that should be followed. So we have like a traffic light. So in red, no way, stop the operations. Orange, it's risky, so it's up to you. And unless it's green, don't proceed, please. So for that, what we do is we need a dynamic downscaling of the regional data in order to convert it into a 100-meter spatial resolution data, because otherwise it would be too coarse to be used for this type of operations. Then we have the response. The response is basically based on the modeling that we do. We know where the spill has been done, and we can forecast the oil spill, where it's gonna go. So for that, we provide the information in order to to aid the stakeholders for decision making. Another one also related to, well, in this case is related to ports, is basically based on all the work that is being done constantly in the ports. So as the new necessities of bigger ports and larger data, larger ships and so on, there's a constant need of improving the already existing ports. So what we do, oh, it's not showing the video, it doesn't matter. Basically what we do is we analyze all the conditions in the port. And similarly to the work done for the oil spills, we said, guys, this is good, you can go on, or no way, I mean, it's too risky, you might end up having losses. Yeah, another one also related to port management and is basically to set up as well the conditions, the best suitable conditions for operating in ports. So at the time of the download of the data, or for example, the ferry boarding, that is quite complicated. And so we provide as well by using Copernicus data, we transform it into information for the port authorities. Then here comes the Army thing. This is exactly the same, but specifically for the Army. So basically what we provide them is with the conditions, the adequate conditions, and the locations where they can safe landing or navigate or things like that. And another thing that we're currently doing is basically we're working on a high-resolution coastal flooding forecast for storm attacks. These videos are actually from 2 beaches near, well, in my city, in Santander. So with the current climate change, what we have had is an increase of extreme events. And this is something that, well, before you could have it once every 50 years, now every 2 years we have extreme events. So yeah, we're now working on that in order to help manage the situations and prevent all the losses that are associated to them. In terms of the improvement, well, one of the things that we miss is the estimation of reliable coastal shorelines and an associated quality flag. In terms of the coastlines, I must say that they need to be dynamic, as the whole system is dynamic. It cannot be a frozen coastline to be used somewhere else, because this is part of some other research, but what we are observing is a huge change in terms of the coastlines. And it's not even that the beaches are losing their sand, but it's also in terms of the cliffs, the houses associated to them, the losses, the economical losses. So we're working on that, and it would be fantastic to have something, a coastline, high-resolution coastline, dynamic one. It doesn't have to be every month, you know, but please have a year. In terms of the improvement of services, well, it has already been mentioned, the Copernicus Coastal Hub. And for us, it's an urgent need. We're really looking forward to have it and to give it a go and use all the fantastic data that I'm sure is going to be provided. So the needs, in terms of the improvements of this service, obviously is not a surprise if I say that we need high temporal resolution and high spatial and temporal resolution. Everybody wants that, but I have to ask for it. As I said, the reliable dynamic coastlines. We will also like to have in this coastal hub, a coastal fringe, like a land fringe. Why? Because you cannot understand the coastal processes without knowing what's happening in the land. And I know that the Copernicus Land Service has something close to a coastal hub, but obviously it doesn't tackle the necessities that us as oceanographers or marine passionates, we would need to do our research. And I'm bringing this because I'm an ocean color scientist. I would love to have optical watercolor variables. Yes, I'm there. Benefits multiple. I mean, we could not be doing all the work that we do without you, without the data that is being provided by the Copernicus Marine Service. And in conclusion, well, what can I say is that the Copernicus Marine Service is an invaluable and extremely useful data provider. And I'm sure, I mean, it's not perfect, but it's the best that we can ask for. And it allows us to think big and do the research that we would like to, you know, with the combination of variables and things. Well, it allows us to do things that otherwise would be feasible. Thank you very much.
Thank you very much, Anna, and you're going to be back later on for the roundtable so we can discuss further with you. Without any waiting much longer, I would like to invite Briac Levu from Amphitrit, who is going to tell us about providing ocean data for operational decision at sea. So the floor is yours.
Thank you, Laurence.
So the remote is here.
And the green is me. Hello. My name is Briac Levu. I'm the co-founder and also the production manager at Amphitrite. And I would like to thank you to give me the opportunity to present our activity. Amphitrite is providing a solution based on intelligence artificial intelligence, yes, and also the fusion of multiple layers of data. And this to give to allow better decision at sea. Indeed, the Amphitrite ambition is to create and provide a new generation of oceanic data with high reliability and high resolution. And this is yes, but it's not only about data, it's about also we develop software to take the most of this data. Okay, some information about the small company. And I put an illustration of, to explain, to give you a very small clue about what I mean when I'm talking about data fusion for us. So here is the same area for 3 different sensors at the same day. So you have altimetry, SST, and also chlorophyll. All give different information and also at different resolution, but all these parameters are forced by the same physics behind. So with a smartly trained artificial intelligence, you could guess the physics behind and create to reconstruct surface current of this physics. The sector we address is first the shipping, but our technology is able to provide solutions for also environment monitoring and defense. We identify different level of user, and some of them we are collaborating with. So some users are only interested by our current surface data, like solution provider, but we can provide the software solution for shipping company, for example, in terms of voyage optimization. So a few words about the green shipping. As you may know, the International Marine Organization is pushing really hard to gradually decarbonize the sector, and this is can be achieved in a long term because it takes time, of course, and the achievement of that is with a drastic change of all the fleet or the propulsion. So, but what we can do right now, it's without changing anything in the fleet, is to apply optimization, voyage optimization. So Amphitrite is proposing one of these solutions in this sector. Our research development is based on 2 different axes. One is to continuously improve the reliability and also the resolution of our product. And the second one is to develop a short-term forecast product based only on Earth observation and neural network. So no numerical model, 3D numerical model. Okay. So to talk now about the data Copernicus Marine providers, we use in 2 ways. We have one is as an input of our model. It's mainly satellite data. So we use altimetry in L3 and L4. And also we use L2 and L3 SST and ocean color images. The second usage of the data provided by Copernicus Marine is to validate our output product. So it's mainly with, for example, with drifters. So this is very important for our product to be validated that way. It allows to fine-tuning our model. Okay, I'm a simpler user, but I can list some improvement our purpose need. So I list here about the product some improvement that is in line the improvement you mentioned yesterday or this morning. So it's basically the improvement of the resolution of SST and global color file, and also the quality control of in-situ data. And I would say, because I could find more result data in US, this year I work with US data. It breaks my heart. Okay. Other suggestion, so we don't use for our product forecast, but we use them to compare, to intercompare with our model. So as a simple user of forecast, I could suggest it would be nice or interesting to have, let's say, a period of with a nice or big, I don't know the criteria of reference data, in-situ data, which you could compare the different different models and different versions of the model. So through some metrics you have to establish. Okay, a point about the difficulty to stay up to date in this big catalog, but this is the price to pay. And for example, yesterday I heard about the numbers of EAN, or about the metrics to know to better understand the quality of the model. So it's nice. I will have a look as soon as possible, and it could maybe answer or give some element about the last point I want to focus on, the uncertainties of data and model. The benefit. After, let's say, I don't know, about 5 years of daily request of data, I don't have number to give you, but it must be a huge number of requests. I can say it's obvious, but high quality, state-of-the-art data for free. It's gold for us, really. And a point I want to mention also, it's high quality of the service level agreements. As far as I could think, I didn't remember the last time I couldn't request the server, but last month, actually, it happened. Okay. It happens sometimes. And this is my last word. Copernicus Marine Service is our best and the main data provider for satellite data. As long as, and it will stay like this, as long as you stay at the best quality and the best resolution we can have. Okay. And just last point about a question, an open question to discuss with you. So, how could what could bring our data, our reliable data we do at Amphitrite, to improve the calibration, the validation of your model? So I will be happy to discuss about that with you. Thank you again to invite me.
Thank you very much, Briac. I would like to invite now Michel Kochnek from GTT, who is going to talk about the operational needs for a shipping weather routing system. So please, the floor is yours.
Thank you, Laurence. I'm very pleased to be here. My main responsibility is to develop a routing system for shipping industry. I come from GTT Group, which is a leader. Which is a leader to design the membrane cargo containment system. So this is mainly gas carrier shipping. So, and it has been decided to develop the digital part, mainly focused on energy management. At that time, GTT Group has to forecast liquid gas evaporation, for instance, the boil of gas, and to estimate sloshing effects, so possible damage and risk to tanks. I had to develop such application, Fleet Navigation Center and the Operation Department of CMA CGM in the past. And what does it consist of? It consists to develop algorithm with a massive use of forecast data in order to save bunker. You must know that an international company like Maersk Line, CMA CGM, has to pay about 4 to 6 billion US dollars per year just to pay the fuel of the vessels. So around 500 to 600 vessels. And the challenge is with a team of 10 people and with new algorithm, how to monitor all the vessels. You have time-chartered vessels, liners, like a container carrier, for instance, car carriers, or chartered vessel, so it's a spot voyage, a spot contract. In fact, tankers, so gas carrier, bulk, and passenger vessel. Users are mainly ship owners, responsible for the maintenance and for the safety of the vessel. So they use weather data for the safety. On the other part, you have the charterer. The charterer is responsible to instruct the vessel, departure port, arrival port, and is responsible and has to pay the fuel. So we are going to use weather data, routing system, to save bunker. So the main users are ship planners, operation manager. In this company, on-board captains, supported by a lieutenant, usually a navigation officer. And between ship owner and charterer, usually you have vessel routing providers. I'm going to speed up maybe because I think we are running time. So there are 3 objectives for the industry is optimizing cost. So fuel monitoring. First focused on speed, and then we realized that it was really better to focus on deviation, route optimization. So imagine 3 to 5% of fuel cost saving with a team of 10 person. We save about 47 million US dollar per month in this company. So we prove that using with a massive use of forecast and data, we can deviate the vessels, saving costs, saving dollars, but also contributing to decarbonization and so and so. And the first aim, ensuring the safety of the vessel, the crew and the cargo. So mainly real-time application with the weather routing, but also we use data to forecast, to establish the schedules of the vessel. So 1, 2 weeks forwards. And for liners, we have to establish a yearly port of calls. So we can use, in fact, climatology statistics for long-term planning. The voyage duration is about a few weeks, usually less than 1 month, 1 month and a half. So we need to use a forecast at the maximum time span, and then we chain with statistics, climatology, and so. So I'm not expert in oceanography, so sorry if there is some wording confusing. We realized that in some regions of interest, there is a lack of accuracy on surface current. So we decided, either in a shipping company or in this, we decided to partner with some providers to create blended models or local models strongly driven by measurement. For instance, Gibraltar, Yucatan, Gulf of Mexico, South Africa, and so, Kuroshio Current, and so. Anyway, at the end of the voyage, we need to produce, as soon as possible, a post-voyage analysis. This is a claim management at the end of the voyage. So we use, at that time, no cast as in-cast, but we will prefer to use in-cast if it is possible in the future to produce quicker. So we use weather data for safety first. So mainly, I'm going to speed up for this, total wave, maximum significant wave height, direction, and peak period. For the safety, we try to evaluate the motion risk, mainly on a large container carrier, the parametric rolling risk, and the synchronous rolling risk. So we assess on one port what is a stability module, the natural ship period. We compare to the swell period. Exactly the encountered swell period. So depending on the heading of the vessel and the speed of the vessel. We really need to avoid tropical cyclones to define no-go area. So at the end, we would like to have just one source of weather forecast, not to have on one part tropical cyclone, on the other part worldwide forecast model. We need to fuse them. There is a real commercial strong pressure on captains to arrive on port with a minimum underkill clearance. On vessel of 400 meters long, sometimes the UKC is only 0.5 to 1 meters. So we need very accurate tide height in port, including surge. Imagine just a few decimeters on the loading, on the vessel loading. It's a few million US dollars per vessel. I'm not specialized in ice, I sail, but so globally we need thickness and concentration for ponant. For instance, we monitor ponant vessel to define no-go area. We use wind gust forecast as a trigger for crane operation. It's completely useless to optimize at sea if we stay a long time in port. So we have to forecast operation in port, and we send back to the vessel. We slow down the vessel if there is a risk of crane failure, of wind gust for crane operation, and so and so. We use also visibility in port. Some ports have some difficulty to accept vessels, like Shanghai. I remember receiving a Prime Minister of China, explaining to him, your port is unable to receive our vessel if there is a bad visibility. So they sent us back Shanghai government, and we managed to. Our algorithm look for strong discrepancies in order to deviate vessel. So we look for surface current gradients. We look for tidal currents. So this is the figures that we use afterwards. So the key point of routing a system is to estimate the speed loss due to the wave factor, depending on frequency, depending on the wave height and the wave direction. This is the most difficult part, in fact. So we mix physical model with machine learning. This is an example to show that there is sometimes some non-intuitive physics. We observe stronger pitch sometimes for quarter head waves, stronger than facing to wave. Sometimes lower frequency or higher frequency seems to create an additional resistance. So more and more we will use peak period, total wave peak period. And we study like that resonance for the vessel between the length of the vessel, heading, and the swell period. What improvement for products to merge tropical cyclone forecast in the global forecast. Otherwise, we have to do it by ourselves. At that time, we know that in the model, global model, there is an underestimation of maybe 5% around and between 10 to 15% in the middle of a tropical storm. So we do it by ourselves. We decide, okay, we decrease the speed like that. But it will be preferable that you provide the data like that. So tide, we have spoken about that. I don't know if surge, meteorological surge are included. So we pay for some providers to do it. We would like to have a rogue wave probability. I remember a few years ago to work with a novelties company to just maybe probability of weak probability, medium probability, and high probability. And we will use high probability to define no-go area. And for incast, so we really need monthly incast. I have just checked, in fact, you are going to do it at the end of the year in November, I think. So we need hourly tidal current, all included in the same system, and local high resolution models. So at sea, we can observe sometimes a lot of discrepancy between sensing and forecast on the current. So there is a real focus to do it on that. 40% sometimes of measurement out of forecasted direction plus minus 40 degrees or out of current speed plus minus 30%. That's a lot, huh? We use a different model, NOAA, US, but we will prefer to use Copernicus model because they provide forecast until 15 days, 16 days. Maybe it's not very reliable, but anyway, we have afterwards to change with climatology. So what to do? What is the best model? There is a real need of explanation, of pedagogy, because we would prefer to use European model. We know that they are more reliable, and we observe it. But you have to extend the time span. Our algorithm must provide solution to captains in a few minutes. So if we integrate more accurate data, local data, coastal data, we have to take care with the volume, the data volume. So just integrate in some region of interest significant data. So this is my colleague. I just let you read, but this is mainly about downloading a big amount of data when we have to study some things. But I can understand that you take care of that. So at that time, we are very pleased for reliability and accuracy of the worldwide model. We are pleased to have a redundancy compared to US model. Thank you very much for the outline. with Mercator Ocean, because this is really good things to learn about, because we have to convince our user and customer, and it's not very easy to understand what are the difference between NOAA models, NEMO, I don't know, WaveWedge 3, and so and so. And thank you, and a wish is you should really enlarge user invitation maritime companies to explain and to confirm that they need something like that. So, in conclusion, integration of tropical cyclones, reliability of currents, surface current positioning, so, and maybe early incast, otherwise we will use no-cast. We want to have the best real-time forecast for European model, but we have to prove it. And we think so we have to work together more and more like that with the industry. Thank you for your attention.
Thank you very much, Michel. Let's go for the last 10 minutes talk before the roundtable. So I'm pleased to welcome Daniela Yasilo from Planetech, and she's going to talk about the Rheticus Marine for Indonesia coastal monitoring. So a new area, geographical area. So please.
Which is the bottom?
So the green.
The green, excellent.
Okay.
Okay. I wanted to start introducing very briefly Planetech Italia. Planetech Italia is a 29 years old company that works to provide a solution based on satellite data to the different kind of users. We are not specialists in providing only marine solutions, but we are quite active in all kind of application, because our way to work is to analyze what user needs and try to find the right solution based on geospatial data. For what concerns marine application, we developed some years ago a platform called Rheticus Marine, and through this platform we provided water quality parameters and other kind of indicators to users. Usually I present this platform applied on Italian or Mediterranean seas. But today I decided to present a different application located in Indonesia to address a specific market and a specific problem. The market is the ones to support the policies related to the sustainable development for the food and aquaculture policies. Which is the problem? It is well known that in Indonesia, but also in other South Asia countries, in the past 30 years, a lot of mangrove forests have been cut to create along the coastline shrimp ponds. And these cause some problems. First, of course, the coast remained vulnerable to storms. Second, there are some intrusion of salt waters in inland. And last, the high level of nutrients of the ponds caused the eutrophication of marine waters. For this reason, the users that is the Asian Development Bank, supported by the LAPAN and by the Indonesian Meteorological, Climatological and Geophysical Agency, asked to do an analysis of this phenomena in 5 different areas located in Indonesia, area with different characteristics, to demonstrate which are the capabilities of Earth observation services to support the creation of future investment plans. So we use the SQ Technologies Earth observation and also Copernicus data. And to address this problem, we created 3 different line of products. First line specific for inland part related to land cover maps. Second, an analysis of the past 20 years of the coastline. And third, specific for water side, the implementation of platform to provide the water quality parameters for 5 years. Today, I will enter in details related only on water quality parameters. But of course, if some of you is interested to have more details also on the other component, feel free to contact me. Okay, so what we used? We used from CIMEM's satellite data related to global data set and in specific way variables such as chlorophyll, transparency, turbidity, and surface temperature. What we did is to create a platform on the 5 user-identified areas. And on this platform, we calculated this indicator for 5 years and integrated with also other indicators such as turbidity index, trophic state index for water transparency, trophic state index for chlorophyll, trophic state index monthly. And we also classified the coastal zone in oligotrophic, mesotropic, eutrophic, and hyper-eutrophic. And we also calculated the environmental status. Before to show you an example of the analysis done, which are the improvement for products for the future. For sure, for this kind of product, it will be good to have high-resolution products because we use global product and it's not enough for coastal areas. And for what concerns the service component, it could be nice to have the access through using international standard, for example, as OGC. This could be very helpful to do programmatic research and identify data set, and also to learn about the covered time range with periodically change for near real times product. Which are the main benefit for the user of this activity? First, we will be able to provide a complete characterization of the impact of the shrimp aquaculture on the shoreline and on the coastal ecosystem in those areas where in the past mangrove forest was destroyed. And now, in many of that areas, mangroves are replanted. Second, this information can support the local governments in preparing investment plans for a sustainable development of the aquaculture, because it is well known that aquaculture is really important for the market of South Asia, but it is also important to preserve the natural resources. Third, we did an extensive capacity building activity to adopt Copernicus Marine and more in general Earth observation services. And we organized at the end of the project in 2021 1 week training session for about 80 people that come from different governmental organizations in Indonesia. And we also put all the training material on a MOOC for their open usage. This project ended in 2021, as I mentioned, but now this year we are starting a new activity with the same user, and now they understand that this kind of data could help in their work, and asked for a platform where they could be in autonomous way use but also create a new algorithm to process the data. Just to see what was the main result, they received an access to our Rheticus Marine geoportal, and through this portal they can consult water quality maps, but also statistics and temporal evolution. For example, here there is one of the 5 year analyzed, and through this analysis it's possible to see not only daily parameters but also monthly means, and it is possible to understand which are the status of the area, and understand which is the influence of the internal anthropization of the area and also of the rivers on the status of the water quality. And these, of course, can be used for a lot of internal environmental analysis, and using the indicators, it is possible also to support the creation of a sustainable plan. This is all from my side. Thanks a lot.
Thank you very much, Daniela. So we had a very nice set of 5 user testimonies, and we would like now to proceed with the roundtable. So I would like to invite all the speakers for the next roundtable. We are running a bit late. We are sorry, so we might end the day with 15 minutes late. So we are going to close at 5:15 or 6:15, sorry. So thank you to all the speakers to take a seat. Please go ahead. Yes. Yeah, so we have Carl Stromsen from Oftech online. So in a nutshell, this roundtable is really to illustrate the process that we have, the user-driven process that we have, which you can see here on the screen, where we are going from the user feedback up to the evolution of the Copernicus Marine Service. And so the roundtable in a nutshell is really to provide you with an example of this process. Maybe you want to tell us, maybe Angélique, about how the roundtable is going to be structured?
Yeah, sure. Sure. So the roundtable will be organized with 3 main questions that we will ask first to our user representative, and then to producers and staff members of our Mercator management. So basically, we will start with a question on what are the main gaps in terms of user needs that the Copernicus Marine Service need to address in the coming years. So first, in terms of dataset and product, and we will go a little bit more in depth with this question, and then we will discuss the needs in terms of data quality, and finally on services. and we will have the producers that will answer in terms of what is already in the pipe to answer those user needs.
Okay, thank you. So maybe we can start maybe with a round table introduction of all the speakers. We have one speaker online and I don't know, 8 speakers here in presential. So maybe I'm going to start with you from the left to the right. So Vittorio, please introduce yourself. You might have a mic.
So I had a chance to introduce myself earlier. I am the TAC leader for the ocean color activities within the Marine Service, and I'm based at CNR in Rome, where I also do a lot of other research activities related to ocean color at different scales.
Okay, so can you pass the mic to Daniela?
I am Daniela Iasillo from Planetech, and my work is to develop the Copernicus market for end-user applications.
Hi, I'm Ana Silio Calzada from the Environmental Hydraulics Institute of Cantabria, and I'm a researcher and part of the Remote Sensing and Copernicus group, the newly created group.
I'm Laurent Martineau from the NASA Center in Bergen, Norway, and I'm heading the Arctic Forecasting Center.
So Renaud Dusurget from Mercator Océan. I am in charge of the part of the data production for Mercator Océan, as well as the definition of the data dissemination system for Copernicus Marine.
I'm Lasse Rabenstein. I'm founder of Drift and Noise Polar Services. We are a spin-off company from the German Alfred Wegener Institute for Polar Research, and we have an app supporting Arctic and Antarctic activities, and we also do consulting to support Arctic and Antarctic activities.
I'm Pierre Brasseur, senior researcher working at IGE Grenoble, but I'm here invited as member of the STAC, the Scientific and Technical Advisory Committee of the Copernicus Marine, which is chaired by Neville Smith, but I think that Neville has left already. I will provide some ideas about what STAC is considering for this user relationship.
Hello, I'm Marie Drevillon. I'm in charge of coordinating the product quality cross-cutting activities in the Marine Service, working at Mercator Ocean.
Okay, and last but not least, Carl Stromsen from the Off-Tech company, who is a user of the Copernicus Marine Service. Please introduce yourself.
Thank you. I'm sorry that I cannot be there in person. I would love to meet you all, but thanks for this opportunity to participate. I see the big picture of myself, so I get a little bit embarrassed here, but I'm Carl Strömström from Off-Tech. I'm a user. So I'm using the data for different type of design, offshore aquaculture, offshore floating wind, offshore oil and gas, and production systems. I design mooring systems, and I use this data to provide design input for all the work I'm doing. Thank you.
Okay, thank you, Carl. So without any further waiting, I would like to ask the first question to the users. So we have 4 users here. We have Lasse, we have Anna, we have Daniela and Carl. And maybe I'm going to start with you, Lasse. I'm going to ask the 4 of you the same question. What is, according to you, the gaps in the Copernicus Marine product offer? Could you advise us on, help us on highlighting those gaps?
Yeah, so does it work? Yeah. So the task to find the gaps in the Copernicus Marine Service actually is much harder in 2023 than it was in 2018 when we had the first contact with Copernicus Marine. And I have to say, I almost had to say, no, I cannot provide feedback because the Copernicus Marine Service provides so much data now that actually we at our company have to do our homeworks first to include all the data or the data we need into our service. But when I start thinking about, of course, you always have a wish list. So what our users need mostly is they want to find way through the ice or around the ice. Then thickness. Thickness is still a very critical parameter. I know it's already included in Copernicus, but it could, for example, it's not included in summer. I know where that problem comes from, but so that's definitely a gap. Then morphological features of ice would be an interesting product because ice is very heterogeneous, and even an icebreaker can get stuck in ice, and if you have costs like 100,000 euro per day and you got stuck in an ice ridge, which is not on any data at the moment provided by Copernicus. So I'm really nitpicking, I have to say. So I'm very satisfied with Copernicus as it is now, but I just give you a wish list. Then what would be very nice would be in-situ data for the wide ocean as well. So just this morning when I opened the data catalog and I clicked in-situ, and then suddenly I couldn't find wide ocean any longer. So there's so few observation points in the Arctic and Antarctic that even the few, like some of the met stations in the Arctic or so, if they could just measure thickness every day, and this could be in a database, that would be already wonderful. So we are so many people. I think I stop here, but
Thank you, Lasse. I'm going to give the floor to Carl online. Same question to you, Carl. Could you please highlight a few gaps in the products from the Copernicus Marine Catalog that you would like to be shown?
Thank you very much. Unfortunately, I didn't hear the last speaker very well, but to be quite short, since I'm doing a lot of design, one of the gaps I have identified is detailed bathymetry, because when you're designing marine system, to have the correct depth, etc., is very important. The other thing I'm lacking is more detailed information when it comes closer to shore. When you're in the fjords of Norway or in Scotland or whatever, and you're trying to design something, the resolution is too big or too large. So what I had been in Norway now, they have implemented the ST wave or the SWAN model, which are running with the forecast, which means that we get a very detailed forecast and information about the waves in the fjords. That is something I would like to see here also. And if it's possible to have a database with bottom conditions, because if you are mooring something, it's always nice to know what you're mooring in. And I know that is very difficult to come by, but these are the real gaps for me, what I would like to see, if it's possible to get it in.
Okay, could you...
Last thing, actually, and that is, since I'm working with fish farming, any information about incidents that comes like jellyfish or anything that, you had this red algae that suddenly blooms up or something like that. I think some of it might be in there, but more detailed information about that would be something that would be of very high value for us.
Okay, thank you, Carl. You were mentioning a database earlier. I didn't catch what you were saying in terms of database.
No. Not database. That comes later. But bathymetry and soil conditions. And we are in Norway now. I can get the ST wave or SWAN modeling of local waves in the fjords. And something like that to be running on top of the Copernicus service would be of very, very high value when you're coming close to shore, because the bathymetry in the global models are very, very rough, and you cannot get the kind of detailed information you need when you're coming closer to shore. Okay, and then finally on the biology, like jellyfish or anything like that.
Okay, thank you very much, Carl. Same question to you, Anna and Daniela, maybe a bit quicker, because we've been hearing also your request during your presentation, but please, the floor is yours. It's working.
Okay. I'm going to be real quick because I just provided a talk, so I don't want to repeat myself. We at the Institute were really happy of the data provided by Copernicus Marine Service, but I coincide with Carl in the sense that we need the coastal adapted data in order to be able to provide, to go a step further, to provide a better assessment of the processes that are happening. And also with the terrestrial, I mean, that coastal data should be, should include the terrestrial fringe and the coastlines, dynamic coastlines. And I don't want to repeat myself.
So, yeah, exactly. Just this microphone is not working for people online, so we will use another one, apparently.
From my point of view, it should be very helpful to have a tailored product for specific kind of users, because there are a lot of potential users of this data that not only are not aware of the potentiality of the data, but they speak a different language. So we should in some way reformulate this product with a specific nomenclature, with specific measurement units, also with a specific appearance, to reach also this kind of users and simplify the access of this data.
Okay, thank you very much, Daniela. So in a nutshell, if I want to synthesize, I'm hearing that there is a need for in-situ CIS data, there is a need for CI thickness, there is a lot of needs for coastal data, there is a need for bathymetry, coastlines. This was included in the coastal data for me. So now I'm turning to my colleague Angelique, and how can we provide this in the coming years in the Copernicus Marine?
And actually, it won't be me answering, it will be directly our producers. So I might turn directly to you, Vittorio, first, to answer what is going on in Copernicus Marine, and especially for you, for the Ocean Color TAC, especially regarding the coastal area, perhaps, as we heard many needs.
I said that in the coastal area, we, as I mentioned today during my talk, we've been introduced since 2021 the Sentinel 2-based products, 100-meter resolution, but we also, and we do also have the 300-meter product based on Olci Sentinel 3. And so those two products still have space for improvement in the data that is available and the variables that we derive. And of particular use may also be our ability to uptake the service evolution project that is currently being carried out, which is called multi-res, and that speaks to our ambition to have a multi-resolution product. So a product that in the middle of off-shelf, in the middle of the oceans, the data can be served at 4 kilometers, but then we get to 1 kilometer, 300 meters, and 100 meters as soon as we come close to coast, but with the same level of accuracy as possible. And so that's where I hope that by 2025, 26 we'll be there. Will not be easy and will not be fast, but that's really our ambition in how to be able to address these data needs.
Thank you, Vittorio, and thank you for mentioning Service Evolution Project. Indeed, we had several ones, including Horizon project to address also development for the coastal zone. We are now moving to the polar user needs. So, Laurent, could you please answer regarding the Arctic data?
Yeah, thank you. So thanks, Lasse, for giving me this reminder that there's something I didn't mention about the ridging in the ice. So ridges are very difficult to observe. You have to be a very well-trained analyst to recognize one on a SAR image. But from the model, we plan to put out the, say, an indicator and, say, volume fraction of ridged ice from the model. And that, knowing that there's been winds going towards the coast, it could be a good, say, rough indication that there's areas that should be avoided in terms of ridges. So that's something we plan actually to put out on this year from the next SIM model. The question of the in-situ CIS data, that say is it's true that there's no it's a red spot on the service today. That there are I can count 4 or 5 institutes that do have in-situ CIS data. That they sometimes have data outside open, sometimes they don't put out their data. So it will take a bit of diplomacy to go around the providers, possible providers, but that's it should not be impossible. Say in I don't know which time frame, but it should. I would insist as well that it's quite important. Yeah.
Thank you, Laurent. We are now moving, because we've been hearing about different user needs for different applications, including in the last session. But in addition to those user needs in the private sector, we have many users that are also coming from the public sector and public institutions, academia. So I would like now to give the floor to Pierre Brasseur as a STAC representative to also give us a broader view on the planned evolution and needs in terms of scientific evolution to better address user needs. Thank you, Pierre.
Well, the STAC is indeed in charge of, let's say, providing advice essentially to Mercator Ocean to define the strategy for the service evolution in order to better meet the user needs. And we had a meeting, well, a few days ago, and we discussed together. There are 5 members of the STAC available here, and we discussed with Neville. And basically, we were quite impressed to see the progress made during the past years in terms of, let's say, data products, in terms of, let's say, resolution in space and time, timeliness, availability of data. That's quite impressive. As you said, many gaps are already filled in. There is also a very strong effort in terms of data quality that was quite well documented this morning in the presentation, and that's quite essential. It's really important to focus and to keep on top of the agenda this question of, let's say, accuracy of the data, just because essentially the data from the CMEMS will be used for, let's say, training models. So we need to train models with, let's say, appropriate data. It needs to be trustable. The trust in the service will be through the data, and it's really important not to avoid misleading users. So that's really an important point, and strategically that's really important. The next steps is probably to go one step further, which is, let's say, to progress in terms of quantification of uncertainties. We have seen from different user testimonies that making available information about uncertainties is important for decision making. We cannot take decisions without this information in terms of probabilistic view. And this has started. It's actually underlined in the research and development roadmap, and we have several research and development projects that will address this aspect. So it's a first step. It has to be continued as an effort, and probably it's still a bit patchy yet at the scale of the overall service. So probably having an overview on how to address this question of uncertainty from tax to MFC products is an important step that is still ahead. A second point maybe is we have seen that we'll have many requests from institutions to solve problems, actually. We need data to solve problems in terms of pollution, in terms of preservation of biodiversity, in terms of managing aquaculture, fisheries, and so on. So we need new tools to do that. Some of the tools are already available. Well, we have tools like marine protected areas, which are ways to manage things. There is a new project ongoing supported by Horizon Europe, which is Necton, that will address some of these themes. It's very important. And basically, it's a very good step forward, and we can expect a lot of new things from this service evolution. But it's also raised a number of new questions. For instance, we are moving in a direction where, for instance, the question of managing fisheries is important, but we need data, new data, which are probably less available. We are not in a situation where we have deluge of data for, let's say, fish biomass or things like that. We have also a service evolution project, which is on the Sargassum propagation, and we see in that case that we are lacking independent data for, let's say, validating the information which is coming out of these projects. So we are moving in an area where it's not so obvious that we have lots and lots of data. That's one point. A second point is that probably we are moving to a world where we'll have to have more complex models to deal with. And the question of how to best deal this complexity issue is important. Probably we could also imagine that we are going to have to simplify models in such a way that we can run what-if scenarios. We will not be able to run many what-if scenarios with the current chain of, let's say, physical, biogeochemical, fisheries models in a complex way. So simplification is probably one of the aspects that will have to be addressed in the future, and probably we'll also have to include the human component. I was quite surprised to see how close the objectives and the perspectives that were delivered yesterday in terms of we need to have progress in knowledge and progress in action, okay? And this is actually the core of one scientific discipline, which is sustainability science. And we are not really connected with this community. It's a community that exists in the US for, let's say, more than 20 years. It started being developed also in Europe, but maybe in the future we'll have to be connected with this community in a perspective to really solve problems in a way that we can increase knowledge and increase action to be effective in the future. So that's probably putting, let's say, some question of this relationship that exists today, which is very good between users and producers, but probably we have to move to a situation which will be more complex in the future with that.
Yes, thank you, Pierre, for this comprehensive answer and broader view. Before moving to the next question, I would like just to say on the coastal issue, because we've heard about that and we presented earlier the different actions that we are undertaking in Copernicus Marine to build this coastal extension and the interfaces with more local national systems operated for member states, for instance. So this is something that will be coming with different actions that are already in place and being developed. And one last word about bathymetry, because we've heard about that. This is something that we are starting working on to provide in the next few years satellite-derived bathymetry product in cooperation with Emodnet as well. So I now move to our second question, and first addressing users, which is the same question basically. What are, according to you, the main gaps in Copernicus Marine that we need to work on in the coming years in terms of data quality and the way we assess it and provide this information? So anyone who wants to answer first?
Okay, let's take the same order again. Yeah, in terms of data quality, I mean, a lot has improved. I learned that the next model for the Arctic, so all my answers are a little bit for the wide ocean here, so I cannot speak for all the other communities, of course. So I learned that the next model is I mean, it's already there for a while now. That's already in a resolution improvement in model compared to the Topaz 4. Still, I can always say we need better resolution in time, although it's hourly. NextSim is also hourly, I think, yeah? So it's already perfect. It's so useful for us already. But let's say it would be perfect on my wish list if the models, for example, would be in the same scale as satellite images. That would be perfect if you could really model. I mean, one of our concerns is trafficability in the ice. So we need features in the size of a ship, of an icebreaker. leads, open leads, for example, and so on. So that would be good. In terms of accuracy of data, that's of course always an issue. So I can tell you how our users or like judge accuracy. If a forecast is wrong for 3 times in a row, then they consider that data set as rubbish. So for example, this morning I looked in a data set of ice age. I think it was age of first year ice. I don't know which ones the data types it was. And then north of Greenland there was a lot of very young ice, and I was kind of confused. Can this be? Because north of Greenland is where usually the oldest ice is. And then on another data set there was very thick ice at the same time. So that for example, is a moment where, maybe a skilled user with a science background knows how to handle the model data, but an end user, for example, would be frustrated probably a little bit. And I have no solution to this. So how can you give a model an indication, maybe something like an error flag, or maybe there are measurements we can, or quantities which says this model forecast actually was difficult, and this time it was very easy for certain conditions or parameters for certain reasons. That would be help. So if any kind of flag which tells this is high quality model forecast, this is low quality model forecast. Yeah, and probably they're easier. There are easier weather situations to forecast, there are more difficult weather situations to forecast, etc. I know that's not easy, but that would be nice, of course. Data quality, maybe that's also more a service. I know that you would definitely get way more users if more data would be drag and drop ready to QGIS, for example. So, the net CDF format is a scientific format, which is standard in the science community, and we use it, we know how to use it. But I know a lot of users download data and then they want to drag and drop them in their QGIS. And if all the data would have this in Copernicus, I think you would have more users. Yeah.
Thank you. Does someone else? Yes, Daniela, please.
When we speak with the end user and ask what they need to adopt this kind of data for their normal working procedure, they very often said that they need data that are certified. Of course, we can open a discussion about this topic, but what we have to understand if is the validation that is done for the data, it's enough to give this kind of certification for end user. But this is a really important point that affects the data quality, and it's really important because sometimes users need to take some decision about the value of the data. And this is, for this reason, the data quality have a big impact.
I'd like to also point out something that maybe is not very politically correct, but I think that, the data quality is paramount. It's something that we have to trust the data, because otherwise it's not going to be used by neither of us or the other communities that are the stakeholders, that they would trust the satellite data or the model derived or whatever. It's something that is a trust that it has been built, it has taken a long time to be built. And it's something that I think that the European Commission is doing something really interesting, and is the introduction of the essential
climate variables or environmental variables or whatever as indicators. We know, all of us that we have worked with remote sensing data, we know that the error bar it might be quite challenging. And the reduction of that error bar in some cases is just fantasy. Because we don't have, I mean, in the case of the coastal waters, we don't have global coastal reliable algorithms. So we have to trust the data that we are receiving as indicators. And actually yesterday I had a really interesting conversation with Vittorio about it. And I think that to put on the emphasis on the data and absolute value or whatever, it's going to be quite challenging. But the data that we're receiving has already such a amount of value, because it's given us something that we're not receiving otherwise. And it's a synoptic view, and it's, I don't know, it's...
Yes, perhaps, yes, Carl, we see that we want to complement that as well.
Yeah, thank you for that. I'm coming from a background where you're designing oil and gas platforms using fetch analysis. So the data quality of the Copernicus to me is just fantastic. And I also think that we have to bear in mind that we have to accept that everything we do, there's a certain uncertainty in it. So for me, I think, yes, the better resolution it is, the better time resolution it is, the better it is, but the data as they are of now, the usefulness of the data that I can get access to through Copernicus is fantastic. Just a few comments to the quality. I know that the Norwegian Met Office, they, at least on the weather forecast that we receive, everybody can have a look at the internet. They do a quality measure to say that it's certain, uncertain, etc. So I assume that it would be possible to do that also for the forecast that has been running for different type of products. A little bit about the access to the data. From my point of view, I'm using point data. So when I'm going into, say, for instance, finding a location for a fish farm, or putting into a location for an oil and gas platform or a wind farm, I want to get all the data I can get from a coordinate, latitude and longitude coordinate. And the way I've done it until now is that if I'm using the global data, I have downloaded the complete global data Hindcast data set. So I have 40 terabytes of data here, and then I chew through everything in order to get the one point I'm interested in. So for me, a procedure where I could actually put in a latitude and a longitude and specify which kind of database the data should be collected from, and that Copernicus on their side could just run the process and then pull out the time series, interpolate it to the point I'm looking at, would be a fantastic tool. It might be that something that exists. I think, from the visualization tools, you can do something like that. But for me to actually input a coordinate, ask for the data, and then we go and have a coffee, and then the data gets sent afterwards, that would be a fantastic tool. Thank you.
Thank you, Carl. It's already 6 o'clock. It's been a long day for everyone. So for the sake of time, I will directly ask Marie, as a representative, Marie de Revillon, as a representative of and leader of the Product Quality Working Group of Copernicus Marine, to please say what we are doing in terms of product data quality assessment, and what are the coming evolutions as well. Thank you.
Yes, thank you. So as presented yesterday, we work hard on documenting each one of our products in terms of product quality, of course. And this might not be perfect, but of course we are happy to get feedback from you users and to improve this. And we are working on a product quality dashboard, which is a website that we update on a monthly basis. And the plans are to really improve the user experience on this website, to connect it better with the main catalog, and to improve the visibility of this of all the product quality information that we already develop. The interactivity also of the access to this product quality information will be improved in the years to come. While we also, today, not all the products are centrally monitored on this website, but we continuously improve the number of products that we monitor. Of course, I'm sure, well, Pierre has already mentioned that we are going to move towards uncertainty derived from ensembles in the future, and so this is also, maybe Laurent will complete this information, so I won't get into the details. But as I said yesterday, we're also working on, so the accessibility is also working on the content of the documentation and working on summaries to make the information more digestible and easy to understand. We are adding progressively uncertainty data sets. It's not already, so I mean for the analysis and forecast, because observational products, some of them already have uncertainty data sets together with the products. So we're going to add some uncertainty for analysis and forecast, which are not already derived from ensembles, but are already interesting, maybe as a preliminary information. And maybe also I can mention that we are working on defining fitness for purpose information for each of the products. First, it will be based on our producers' confidence on what we are delivering, and progressively we can improve this fitness for purpose information together with the users. So maybe that will be the summary.
Thank you, Marie. So you mentioned indeed that in terms of data uncertainty characterization, we are slowly moving towards ensemble forecasting. Laurent, could you please briefly complement and tell us what is going on with the ensembles? Thank you.
There's say, diversity of advancement in ensemble techniques between the different MFCs, but there's a working group that was established last year, was it, Sylvain? And then we meet regularly, and we will all produce some degrees of, an ensemble to demonstrate what we can do with an ensemble. It's different in different regions, needs are different. But from, my experience, I can answer to what, something that Lasse alluded to, the errors of the day. So when we have an ensemble, we examine the spread of the ensemble. Most often, where you have the spread is where the forecast has most errors. So that's an indication that would be more complete, more systematic than just asking someone, what do you think the errors are today? And the second thing you alluded to was the 3 times the user misses data. That's biases. And there's one service evolution project that has a poster, it's called COSY, and it's how to learn from the systematic biases to correct forecast. And you'd have the forecast and the unbiased forecast as from the systematic errors. Yeah. So that's the avenues that we will pursue.
So thank you very much, Laurent. So for the sake of time, the last question, we are going to do it very short. The last question is going to be for you, Renaud. And it's more about the gaps in terms of the service. And if I summarize what we've heard today from Carl, from Daniela, Anna, and Lasse, there is the need for new formats. We have NetCDF. What kind of new format are going to be provided in the future? And we heard also from Carl the need to have the possibility to download data on single points, for example, and to extract the time series at that one latitude-longitude point. So please, Renaud, tell us what's going to be next in the Marine Data Store.
Okay, so thanks. Thanks for all the feedbacks. I'm very happy to be here with the and listening to all the feedbacks from the users and from the community. As presented earlier, clearly we have a strong need on our side in order to better fulfill your request, actually to slightly modernize the way we are managing the data ourselves. So to go into and starting implementing more advanced functionalities for getting access to the data. And I also take the words of Pierre on saying that we have more and more users trying to run complex processing on the data, and we really need to tackle down this complexity from the technical point of view to have the users in capacity to easily implement complex things from our marine data store. So that's one of the first things we clearly need to have to go a step further on that, and clearly the future system will help that. We also, on the other side, we also have more and more data in terms of diversity, but also in terms of resolution and volumetry, so that we really need to deliver the users with a homogeneous way to access and process this data. And this has to be robust enough to scale up to very large volumetries and to deliver reliable information, still deliver reliable information to the users. So that's two key things I think that are really important on that. And the fact that we have more and more big data and AI players that are digging into our data sets is really encouraging us into moving this step forward. And in the end, I would briefly say that we clearly need to start moving from the purely data production and data delivery paradigm to a more advanced paradigm where we could deliver the users with the capacity to generate data from data or even information from data. And I think that's, well, going into the analysis of ensembles or looking at cross comparisons of data sets, for instance, for qualifying the differences between different data sets on the same region in a very localized way, because our systematic qualification is not always able to get into the detail from the field, actually, the level of resolution we need to go at on a single day and given with a given time. So providing the users with a way to run scientifically qualified and technically trustable algorithms in a very simple way will definitely help our users to have a better understanding of what the data is made of, actually, and what is its accuracy overall.
Okay, so thank you very much, Renaud. We are going to end here this roundtable. I would like to thank you to all the speakers in presential here, all of you, and also to you, Carl, online. Thank you very much. I mean, this is really grateful to have all those feedbacks so that we can think about what we can and what we need to implement in the future. This is really key for us to have a user-driven service that is going to be useful for action. So thank you again to all of you. Thank you, Angélique, my co-chair. And Pierre-Yves, maybe we need to give you the floor back for the wrap-up of those 2 days. So thank you to all of you.
J'ai essayé de mettre des trucs, mais ok, non, ça n'a pas marché. Okay, I think it has been a long day. I mean, we started very early this morning, and it's up to 15 past 6. But I think it was very useful day, and it's time now to conclude this open session of the 2023 General Assembly of Copernicus Marine. I think these 2 days I've provided, I think, is a very detailed and excellent overview of the Copernicus Marine achievements and plans for the coming years. So again, thanks a lot for all speakers, panelists, and participants for the very good discussion and exchange. We actually had a lot of exchange during coffee break, lunches, and poster session, and I mean, these really are invaluable, I mean, for us to interact with all of you. We had almost 200 people here in Brussels, and that was quite satisfactory to have most of our contractors here today. And yesterday we had up to 700 participants online, and up to 400 today from more than 120 countries, which I mean is a good demonstration of the international impact of Copernicus Marine. I mean, all this discussion and the very good input discussion on exchange that we had today are really, I mean, essential to us to provide strong motivation to continue to run this very ambitious program that we have in Copernicus Marine, and make sure to continue ensuring this state-of-the-art and fit-for-purpose Copernicus service. So, last but not least, I mean, I want also to thank for the overall organization of this event. So, as you all realize, we are here in a very nice place, and we are excellent local organization. So, both the choice of the location, all the events. So, a big thank here to Vincent and all the Mercator. And all the Mercator team and also the local organization, I mean, working for this first selection and having everything going fine. As always, when I am in a meeting with Vincent, I feel very relaxed, and he knows that. And so it was quite, and actually it was an essential ingredient for a successful General Assembly, to have a nice place, nice people, and so on. So this, I think, closes this open session of General Assembly. So we'll continue to work in internal meetings the next 3 days with our producers, I mean, advisory committee for science and user. And this will help us to fine-tune all our activity for 23 and 24. So, but officially, I think we can now close the open session. And I invite you already, I mean, all people, participants online as well, for the General Assembly next year, 24, which will be almost at the same time in